Hi, my name is Kirill Simonov. I am competitive programmer coach at St. Petersburg State University, and I'm excited to welcome you in this course. First of all, a couple of thoughts about why learning competitive programming is good for you. Competitive programmers write reliable and efficient programs, and so it may help you in getting a job, or if you're already in a job which handles large amount of data. Competitive programmers also are very motivated to learn and practice different algorithms. And if you didn't get enough time for do it before, with competitive programming you will do it easier. In competitions, there is also a very limited time, like 2 hours on a lot of problems. And so it will gain you time management skills. So you could do things efficiently under stress in limited time. And it all, algorithms, efficient programs, and managing time is like things that could be very useful, not just in life, but also, for example, on job interviews, where you get asked algorithmic questions and need to answer rather quickly. Another good side in competitive programming is that its community consists of very motivated and smart people, and so it's a lot of pleasure being in the community and communicating with them. And also, solving problems is just fun and captivating by itself. So competitive programming is like both a mind sport like chess and a way to gain useful knowledge for your everyday life and job. In this course, we'll cover basic skills and tricks which may be needed for a competitive programmer, and also some common algorithmic ideas, so you could jump right at competitions when you're finished with this course. In the first week, we'll introduce what competitions and problems on them are, what are their specifics, and we'll also talk a bit more about how to test your programs. On the second week, we'll talk in detail how to write code that it's correct. We'll also talk about the idea of brute force algorithms, which could solve basically any problem, only it's usually slower than needed. But sometimes it's the right solution. And we'll also talk about time complexity, meaning that how you could estimate will your program pass or not when you submit it. On the third week, we'll discuss issues that could be with handling numbers in programs, and in competitions these issues really could show up. And we'll also discuss how to, if you get stuck on some program when you have an implementation and don't know what to do about it because it doesn't work, we'll talk about a few tips about how to get out of the situation. On week 4, we'll talk about an idea of greedy algorithms, which is, first of all, a common type of algorithms, and there are also a lot of pitfalls. Correct solution and incorrect solution here are separated by a very close gap. So here it's important to get the right idea and prove it, or see otherwise that it's correct. We'll also talk about specifics of different languages, so which one, for example, you should choose for use in competitive programming. And we'll also cover a useful data structure called a segment tree. On weeks 5 and 6, we'll talk about dynamic programming. It's a very common idea, like many algorithms could be reduced to it somehow. We'll cover some common problems, for example, edit distance, which is like what you should do to get one string from the other by insertion, deletions, and swapping characters. Knapsack problem and other problems which are like classic and basic. And along the course, you'll hone your skills gathered at lectures by solving programming assignments, which are very similar to actual computation problems. So that's what we'll be doing in the course. In the next video, we'll start with specifics of competitive programming. In this video, we'll discuss specifics of competitions. What's the difference of competitive programming to other kinds of programming? We'll start with what competitions actually are, so it's fine if you haven't taken part in them. Competitions are always strictly timed. The duration may range from 2 to 5 hours, but it's always mandatory to end after a certain time period. You can take part individually on some competitions and in teams in others, but it's always strictly regulated by the rules. The most common competitions are individual, and sometimes, for example, it's a team of 3 members. But always, individual or team, you won't get any help from the outside. It's against the rules. Competition consists of several problems. They are more or less separate, and you should just solve them one by one, usually in any order. Sometimes all problems cost equal amount of points, sometimes the harder problems cost more points. But overall, the more problems you solve, the more points you get, and the higher place in the ranking you also get. There are no jury votes or something about what program is better. All solutions are tested by an automated testing system. So they are all in identical conditions, and it also means that you won't get much help from it in getting your solution accepted. The problems in algorithmic competitions are quite specific, so let's discuss them. First, in contrast to problems in industry, where the parameters could always be altered a bit, problems here are always strictly formulated. It's often done through some real-world legend, which offers motivation and illustration for what's happening, but it's always some mathematical model which underlies the problem, and it's always strict. Because everything is done automatically, the input and output format, and so on, it's all is also strictly formatted, and it's described in a statement of the problem. Another thing, each problem also has time limit and memory limit, so solution must fit in an allotted amount of time, and it also must not use more memory than is given. The time limit is usually about a second or 2, and memory limit is like 512 megabytes, for example. So it's really important to pay attention to performance of your program. And often solve a problem somehow is easy, but solve it fast enough to fit in the time limit is what's really hard. And you often need to know some common ideas and algorithms to be able to invent a right solution and make it fast enough. Many algorithms from basic to advanced in different topics will cover in other courses of the specialization. Now, as we know what a problem is, what is a solution to it? It's actually a program in one of the supported languages. What languages are supported may differ from one platform to another. Some may be less, and somewhere may be more languages. And the most popular set is C++, Java, and Python. These languages you'll find mostly anywhere. And so we'll give examples during our course in these 3 languages, but you could do assignments in several more languages also. And we're talking about short programs. They're usually about several dozen lines, while the hardest problems may get like 200 lines at most. And so, as programs are short, they are expected to fit in a single file, which you will submit to the testing system. This program, which you write, must read input data as text in the format described in the statement, which is very strictly described. It should do so from either the standard input or from an input file of some fixed name, which is given in the statement. The output, as it's checked automatically, should also be strictly formatted, and it's also described in the statement. You submit program to the testing system, and here it's automatically tested against prepared test set, meaning that there is several dozens or 100 of tests, and they are getting fed to your program one by one. Each test you should solve in a given amount of time, for example in a second per test, and you should output a correct answer to it. Because your solution runs on a remote testing server and not on your computer, it's subject to strict regulations. It should not get to the internet, write to other files than the output file, use additional libraries, and so on. In the end, your submitted solution receives a verdict, which is shown you either right after submission or at the end of the contest, depending on the rules. Usually, your program is either tested until the first error, and that error is shown to you. So, what types of verdicts there are? They actually illustrate what does the testing system check about your solution. The first possible error is compile error, and it means that your program doesn't compile if you get that. It also usually tells you a message of the compiler why your program doesn't compile, because the versions of the compiler could be different on the testing system and on your computer. Of course, this error makes sense only for languages that are compiled, for example C++ and Java. The next error is a runtime error. It means that your program has crashed on some test. So it started working, started reading tests, and then something wrong happened. For example, you go out of array bounds, or divide by 0, or so on. Next kind of error is time limit exceeded. It means that on some test, your program just didn't terminate it in the fixed amount of time. So it worked, and the time ends. Similar is the memory limit. If on some test your program eats up more memory than it's stated in the statement, then it gets terminated and you are shown the memory limit exceeded verdict. If your program didn't crash and did not exceed time and memory limit, the testing system checks your output. One kind of error you can get is presentation error. It means that your output isn't formatted to the rules. The test system just couldn't check if it's right. It doesn't understand it. Another, maybe the most common type of error, is wrong answer. It means that your solution successfully exited, writed output, the output is correctly formatted, but it's just not correct. The final and the best verdict for you is accepted. It means that all tests were passed, your solution didn't crash, didn't exceed either limits, and the output was correct in all cases. You can see that verdicts are tested somewhat sequentially. You won't get your output even don't get checked if you get a time limit exceeded. And if the format is not correct, the checker doesn't check that your output is correct by itself. You are also given a test number with the verdict, except of course verdicts like compilation error, because it's before any testing, and accepted because every test has passed and there is no information in test number. All other verdicts will show you on what test exactly did your program fail. And that may be useful for debugging. You could track your progress, or for example, if you failed on the first test, then it's something completely wrong with your program. Another useful thing to know is what test cases could be. The good thing is they are always of certain specific format. You have no need of checking some typos, different errors. You won't need to handle errors like in real-life applications, and so on. You are guaranteed to have the input of specified format. And its size and range of values are also limited by the statement. So you know what large tests you will be handling. However, in a real world, you can make a lot of useful assumptions about the data. For example, people's names are usually short and real-looking, search queries are usually similar, and so on. But on competitions, any assumption about the data, except for what's written in the statement explicitly, is false. So, any test which is good enough according to input format of the statement could be fit to your solution, and you should be able to solve it. So, problem authors usually try to get tests of every possible kind, with every possible extreme condition or so on. And usually, competition rules are so that your solution must pass all tests to get any score. So it's very important to see some special or pathological cases to your solution. In the next video, we'll illustrate all said before with an example problem. In this video, we'll look at the statement of a simple example problem. We'll identify different parts of the problem statement and what their purposes are. Structurally, all problems are similar, so it will be very helpful in understanding other problems. The first part is the legend. Here we know that we are given a list of contact names and should sort it alphabetically. The next part is input format. Here we know that we are not just given a list, but each name goes on its own line. We also learned that names are just sequences of lowercase English letters, and that their total length is no more than 10,000 characters. The next section is output format. From here we learn that in output we should print the names in the same format, one on its own line. And the last part are sample cases. Here we have one sample input with 3 names in it, and we see also the correct output for this input. Now, let's look more closely at the purpose of different statement parts. In a legend, you are given formulation and motivation to what you exactly need to do. Here, sorting a list of contact names really looks like something you may need in your real life. For example, if you write an application which imports contacts on your phone. Other problems often have similar real-world motivation. Because of that, problem statements could be actually quite long, unlike this particular one. And you need to focus on important parts, where something gets formulated like constraints or restrictions or conditions. Any assumptions that are not strictly formulated and you just get from the fact that the data is from real world are actually wrong. And later we'll see what that means for this problem. Next, input format. It describes in detail what exactly are we given. In a legend, we see that we're given on a list without any details about it. But from the input format we know that the elements of the list are delimited by line breaks and not just by commas or dots or anything else. But what's maybe more important, we also know constraints and limits on the input. Limits are particularly important because only by them you will know is your solution efficient enough or not to pass? And we already saw that efficiency is very important in competitive programming. And the additional constraints may also help you. For example, here, the fact that the names consist only of letters helps greatly with reading. It's important that only what's explicitly stated in the statement is true about the input cases. Any other assumptions could not help you, because any test which formally fits to the input format section could be given to your solution. When thinking about this problem, you probably depend on some real-world intuition about it. For example, you may think of the names as, well, being short, real-looking, distinct, because they're like names of contacts in your context list. But such assumptions in competitive programming are wrong. Also, they could help you in real problem when, for example, developing an application for importing contacts. Here, we are not guaranteed that the names are actually real people names. So the test like ABCD, AFG, and AAAAA is perfectly valid test. The names are delimited by line breaks, they consist of lowercase English letters, and the length is small enough. It's also not stated that the length of names is somehow restricted, besides the fact that the total length is no more than 10,000 characters. So one name of 10,000 letter A's is also a perfectly valid test. Also, you probably wouldn't name a contact in a list with such name, because it's maybe tiresome to type. But for the problem, it's fine. It's also not guaranteed that names are distinct. And for example, 10,000 names of one letter A is also a good test. The names could also have largely different lengths. For example, one name of 5,000 letter A's and 5,000 names more of one letter A each. Where did you see such contact list, you may ask? But in competitive programming, it's important not that we are treating real-world datasets, but instead that we are satisfying to some well-defined conditions. And that is not just crazy as it may seem, because when you write a piece of code that satisfies some well-defined conditions instead of some hidden dependencies which you just assume, that piece of code could be easy to work with, or it could be easily integrated somewhere, and so it helps not only just for the purpose of competitions, but also for writing code that's easy to work with. And so the bottom line is, on competitions, you should look for any test which is good enough to fit in the input format, and not just this that looks general or somehow real world. Next, your output is tested by a program, so you couldn't just output something readable to a human. Your output must follow precise format described in the output format section. And it's usually not that hard. You just need to remember it, because if you don't follow the format, your solution has no chance of being accepted. Next, sample cases are also very important. They allow you to verify what you understood from the statement. If you feel that something is not right about the statement and the samples, then you need to read the statement, because that's a clear sign that you've understood something wrong. And in that case, solving a wrong problem could be very bad for your results in the contest. When you've implemented a solution, sample test cases also help in testing it. They are already given and with the correct answer. But you shouldn't test only on samples, because they hardly ever cover everything. Later this week, we'll talk more about testing. Also, samples help to catch some general errors. For example, you will likely get an error on the first test if you print output in wrong format or parse input wrongly. And the good thing is that the samples are usually the first test samples. So if you get a wrong answer in test 1, you know that it's on the first sample, and so you know a test on which a program doesn't work. this video, we'll talk about process of algorithmic problem solving in general, identify the steps of the process, and discuss them which could not seem obvious enough. Well, what could be the steps? Surely you start with reading the statement, and that we already done with the example problem earlier. After that, it may help to formalize it a bit. If the statement is long enough, it could be good to have a clean, short mathematical formulation of what's happening. After you get a formulation of the statement, you should invent a solution. Of course, it's not a simple step, and there is no general algorithm of inventing the solutions. But knowing different ideas and algorithms helps, and also experience in having many solved problems in your past life. After you invent a solution, you in fact should prove it and not just implement right away. It may seem not obvious, but on the next slide we'll discuss why the proving is important in competitive programming. After you're sure that your solution is correct, you could go and implement it. After that, you should thoroughly test the solution you've implemented, because you may have gotten errors somewhere in implementation or in before steps. If you found some bug, you could, with the usual means of debugging, find the place of it and fix it. After all that, you could submit your solution to a testing system and hopefully get accepted. If not, then you may test more and get another bug and fix it. Or you may check that all steps before you've done correctly. So you've read the statement correctly, you've invented a correct solution, and you've implemented it just as you invented it. Okay, so one of the questions you may ask could be, why do we need the proving step at all? Why don't just implement a solution which we invented? On our previous problem, we didn't see much need for proving something. But it turns out we often base our solutions on assumptions which are not correct. It may be assumptions about data which are not actually stated in the statement, but we just imagine. But it also be some ideas like, this surely will work, or this surely will work fast. So both correctness and efficiency of your solution depends on what ideas you use. So if you assume something, or if you use any idea, it should be either written in the statement, or you should prove it. Of course, if it's something well known, like a theorem in math or something like that, then you need not to prove it. But anything you should be sure of. Of course, there is no universal algorithm, not only in inventing solutions but also improving them. But later in this course, we'll discuss how to prove greedy algorithms, where the proving is probably most essential in the basic problems. And we'll also learn how to make time estimate. So when you invent a solution, you should also check not only that it works, but also that it works fast. And there is a technique for that. Next, imagine a situation where you found some test case on which your solution is not working. The usual thing to think is that the error is somewhere in the code, but in fact it's not just that. The error could be on any step of those which we seen earlier. It could not be just in implementing, but also in understanding the statement or in inventing a solution and improving it. And if you detected an error on some step, you should fix it in the first part in this step, and then on all other steps, getting on them one by one. So if you found an error in the proof, then you fix the proof, and after that you fix the implementation of the algorithm based on it. And if you found an error in understanding the statement, you should first fix the solution, then reproof it, and only then re-implement parts which get affected by it. Starting from the wrong step could be disastrous. Let's say, for example, that we write some program which takes an integer and outputs an integer. And we've thought that on a test when the input is 5, it works incorrectly. So we might just plug an if statement in the code, which says if the input is equal to 5, then print the answer to it. But that will most likely be a bad solution. It will just hide the fact that your solution is not working on some test cases, but it won't get your solution generally correct, only correct on that particular test case. So in fact, you should, if you see such test case, you should test that your proof of the solution is correct, and if it's incorrect, then change it, and only after changing proof, change the implementation that corresponds to it. In this video, we'll talk about other things you need to keep your mind upon, aside from just solving problems. Since you probably just begin your way in competitive programming if you view this course, then it's completely fine for you to be stuck on something like a hard idea of solution or some non-trivial bug in your implementation which you couldn't find by yourself. And if that happens, it's a good choice to ask the community for help. There are a lot of people which would like to help you if you ask right. So, where to ask questions? First, there are forums here in this course where we encourage you to get help, but there are also forums on different popular resources committed to competitive programming, and we'll discuss those resources later in this lesson. But when asking questions, you should respect competition rules. For example, it's cheating if you want to get help on a problem from an ongoing contest. And you should not also discuss examination questions and something like that. But everything else is fine. If, for example, the contest has ended, then you have all rights to ask something about the problem. So, if you decided to ask people about something, it's very important to do it well, so people would like to answer you. First of all, you should put a title which perfectly summarizes what you are asking about, because it's the first thing that the people will see. You should also format your question and coordinate it well, so the people could easily understand what you've written. And you probably should insert just enough code, so the problem would be reproducible. Because if you just put 200 lines of code and ask where is the bug, then no one would be able to help you. In fact, on competitions, there is also a chance to get help, but only of particular form. If you don't understand something in the problem statement, you could ask the jury for clarification. That is, you could submit in a special place a question which assumes answer yes or no and is about the statement. Most probably, the answer to it is already written and you just didn't get it. But it happens that something is not clear in the statement and that the jury could fix it by answering your question. Of course, the jury will not tell you anything about your solution or other people's solutions, only about the problem statement, because helping you get the correct solution is not their task. You must do it yourself. That's the competition rules. But if you're seriously stuck on the problem, you might just wait until the end of the contest and then answer the community about your problems. Another important part that people often miss is establishing workflow, meaning that as time means everything on the contest, you may probably want to do routine things faster, like creating projects, testing, debugging, and so on. So first of all, it's good to get to know your IDE or text editor well, so you could fast create projects, open new files, debug, and so on. It also is good enough to have a template code. So you not just start writing every solution from the scratch, but from some already written code like popular includes or some functions you need or something else. It's also a good thing to find a way to manage your backups of your code and tests, because it's often needed to, well, you could write something correctly, then delete it, and then wanted to return it back. So backups may be helpful, and there are different ways to do it. For example, syncing folders or versioning system or just manual copying. You could choose any one of them, but you should not spend many time on it. In this video, we'll discuss what else to do besides attending this course. Because to be a good competitive programmer, it's not enough to just study. You must also practice on real competitions. So the first thing is, you could participate in competitions. It's good that there are a lot of them nowadays. They are usually online, so you don't need to even get out of your house. And they're usually not so long. Individual competitions usually are about 2 hours long. Important thing to note is that you should not just take part in competitions, but also work on your results thereafter. For example, reading the tutorials of problems, so you would know how to solve problems which you didn't get during the contest, and solving them after the contest, so you could get better at solving them. Another thing, you could just solve problems outside of contests. There are a lot of resources with just hundreds or thousands of problems which you could just solve without the press and the time limit of the contest. But you should choose difficulty well, because solving too hard problems for your level could be very annoying and demotivating. There are also times when after the contest you read the tutorial and see that some problem has really simple solution. You only didn't know the right algorithm for it. So it may be a good idea to learn algorithms by yourself if you feel the need. Meaning that if, say, you've stumbled upon 2, 3, 4 problems which needed that algorithm and you didn't solve them just because of that you didn't know it. And there are a lot of materials in the net where different algorithms are finally given to you. So, what competitions are there? Probably the most well-known competition is ACM, International Calligraph Programming Contest. Here, teams of 3 people get contested. They have only 1 computer per team, and the contest is quite long, 5 hours each. You should send many solutions to the same problem, and they are all tested right away, so you get your verdict in about several minutes after submitting. So you know if you solve it correctly and could move to the next one, or if you should debug it, fix the bug, and send again. All problems, in terms of results, are considered equal, so only the total number of solved problems is counted. But if this number is equal, there is also a second parameter that's called penalty time, and it just depends on how fast did you get accepted and how many incorrect attempts you wasted in doing so. So the less time and the less incorrect attempts, the better. There are also eligibility rules, meaning that, for example, you have to be a student pursuing some degree in order to enter the ACM-ICPC contest. And another thing is that these contests are purely on-site, meaning that you can't write them from home. You should get first to the sub-regional contest, which spans several not large regions, then the regional contest, and then the Grand Four finals. So in total, in ACM-ICPC, about 50,000 people take part each year, despite eligibility rules and also the complexity of finding 2 more people to compete in your team. Next, technological companies are very interested in competitive programmers, so they have their own championships. Probably the most famous are Google Code Jam and Facebook Hacker Cup. The convenient thing is they are individual and there are no restrictions. Anyone can participate. They are usually held once a year. Google Code Jam starts usually in April and Facebook Hacker Cup usually in January. And another good thing is that all rounds except the final are online, meaning that you just need to have a computer and a place to sit. You don't need to come somewhere. A peculiar thing about the format is that here you do not submit your actual code to the system. You need to, when you are ready, you need to download the input, and in like 6 minutes you have to download the output back. So you may use any tools or languages or libraries necessary in computing the output. And of course, as the companies held the championships, it's in much part is in purpose of recruiting new talented programmers. So if you want to get a job at Google or Facebook, it may be a chance. Well, what if you don't want to wait the whole year to take part in the contest? There are places where contests are held like often. Probably the most important is Topcoder, where there are single round matches, regular competitions which are held like 1 round in 2 weeks. There are usually little or no prizes here, but there is a rating system, where after each round, depending on your performance in it, your rating changes. Just like, for example, in chess, where after the match, rating of 2 players gets changed. There is also an interesting thing called challenge phase on Topcoder rounds. After you've solved some problems and sent some solution, there is a phase where you should find test cases which break other people's solutions. So it's a good practice of testing your own solutions also. And there are also like championships and prize rounds. For example, Topcoder Open, which is held annually and consists of several stages, just like any other championship. There is also a resource called Codeforces, where there also are regular rounds, rating system, but there are also prize rounds, which are held by companies smaller than Google and Facebook, but maybe just as great as them. And there is also a big and motivated community. There are a lot of useful blog posts on forums here, and it's a good place to ask for help in anything. There are a lot of other resources with emphasis on different things. For example, job recruiting or learning or just fun challenges. You see some list of some on the slide, but there are also many more. You could just try them and see if each of them suits you. And for start, you might just start with like anyone, and then you see if it's good for you or not. So, that's all for the first lesson, but hope to see you soon. There is yet a lot more to learn about competitive programming. In the next lesson, we'll find out more about testing programs to prepare you for these insidious test cases in algorithmic problems. So, good luck. Hi, in this lesson we'll talk about testing, an important part of problem solving. Testing is when you take an already implemented solution and run it on some tests. So, why bother with it and not just send the implemented solution to a testing system? Usually, contest rules are so that incorrect attempts are penalized. Either it's some penalty time or other penalties, or it's just that your solution isn't counted at all if the testing happens after the end of the contest. And even if you can afford sending an incorrect solution to a testing system, even that you get only a verdict, which will not provide you with much useful information about what's wrong with your program. What could help you is a test case on which it doesn't work, but that you could obtain only by testing. And testing is itself designing and running different tests. So we'll cover common types of useful test cases. We'll also talk about how to organize testing workflow in general, and we'll see a powerful technique of automating testing called stress testing. First of all, a little bit about what we should check at all. The most direct thing to do is to just run your program on some input and check if the output is correct. For that, you need to know the answer. You could obtain it by manual computation, or if it's a sample case, you just know it from the statement. It's also useful to check that your program works at all, meaning that it doesn't crash on some test. And the good thing, you don't need to know an answer for that. You just need the test case. And connected with that is a powerful technique of inserting special statements in your code called assertions, which test some invariant and throw an exception if that invariant is not satisfied. So, if your code is covered well with them, then you may check its correctness also by simply checking that it doesn't crash. You could also run your program on some really big input to see whether it exceeds time or memory limit or not, without wasting attempts on the testing system. But it also gives useful information about what to do next. Say, if your program works too long, is it just a little too long or like 10 times time limit? In the first case, you could just optimize a bit, and in a second, you probably have to come up with a completely different solution. So, testing on large tests could give you such information, and the testing system won't give you such information. So that's one more reason why testing is important. Now, on what to actually test your programs. The first thing is sample test cases. They are already given, so why don't test our solution on them? And the good thing with them, the answer is also given. So you could make an error while computing it or understand the statement incorrectly. It's guaranteed to be correct, and it's very good to have such guarantee. The sample cases are also needed to help you verify your understanding of the statement. So you could not just test your implemented solution on them. After you read the statement and before even inventing a solution, you could see sample test cases and determine if you've understood the statement correctly. If, after checking the output of the sample input with the statement, you get a correct answer, then you are sure that you got the statement correct. And if not, then you need to reread it, because there's no point in solving a wrong problem. You could also apply that to inventing a solution. Right after you invent it and before implementing, you could manually run this imaginary solution on an input and see if the answer is equal to sample output, so that you won't be implementing wrong idea. And these tricks could actually save you a lot of time, because a lot of contestants end up implementing wrong solution or just solving the wrong problem, while they could have just checked the samples. And what do the samples actually check? Well, it's usually like the general case of the problem or some special cases, but hardly ever everything. But as sample test cases are supplied by problem authors, it's in their power to bias them. For example, miss some special case, or put some special cases and miss the general case in all. So that means that sample test cases couldn't be trusted. You could also invent some of your own tests to test your program on. And that is what we'll do next. Usually, the simplest kind of cases is the minimal test case, where some or all input parameters are minimized. To clarify, let's look at an example problem. It doesn't matter what happens there, only that we are given an integer n and then a sequence of n integers. In this problem, the minimal case could be something like follows. N is equal to 1, and the sequence consists of only one integer 0. So it's easy to see why it's called minimal. The size of the sequence is as small as possible, and also the value of the element in the sequence. But that doesn't mean that the minimal test is necessarily unique. For example, one non-zero number or several zero numbers could also be treated as a minimal test for this problem. And minimal tests are often special to a solution, meaning that on them the solution works differently. For example, if you need to search for a pair of elements and the sequence consists of only one element, then there are no pairs, and so it may be some special case for the search of pairs of elements. It's also a good fact that such tests are really easy to obtain. You just need to make some values as small as possible. That doesn't require much thinking, and so that could be easily and fastly done. It could also make sense to minimize not only the input values, but also, say, the answer value or the answer size. So it's worth to note that the general idea of minimizing something in order to obtain a simpler but interesting test is also useful. The natural counterpart is the maximal test, where some or all input values are maximized. In our previous problem, the maximal test could be something like this: million numbers, each of value 1 billion. Again, that's not necessarily a unique variant. There also could be million zeros or million randomly generated numbers, or just one or several really big numbers of billion. The issue is, with such large values and large tests, it may be hard to compute the actual answer by hand. But in fact, maximal test cases are used for other purposes. First, your program may be susceptible to crashes only on large tests. For example, when your array sizes are too small, and on small tests it doesn't show. It's natural that your solution have maximal time and memory on a maximal tests. So these tests are also useful in testing your solution whether it passes or not in a time limit. However, there may be such a problem where not every large test is a maximal in terms of time, so you need to think about it. There are also some specific issues like integer overflow, which don't show on small tests but could show on large tests. Integer overflow is when some integer value is too large to fit in the space allocated for that number. It seems that only impacts the answer, but in fact, integer overflow often could be easily noticed. For example, when all your values should be positive and you suddenly see a negative number. That's the clear sign of integer overflow. So, maximal tests help there also. With max tests, there is often the issue on how to obtain them, because you probably don't want to type million numbers. The simplest way is to write a simple program called generate, which just outputs the maximal test to the output. On the slide, you see such program for our example problem. It just outputs million numbers of value 1 billion. So if you have the program, you just run it and save output to the file, and you have the maximal test. Another more lazy way is to just plug in the maximal values inside your code instead of reading. That may be sometimes faster than writing a separate program, but it's also more dangerous, because each time when you want to run your program on max test, you need to tamper with your source. And so it's not convenient, and you may also introduce some bugs in your original program this way. So writing a separate program should definitely be preferred to just inserting the values inside the code. You could improve the previous method by structuring your code. If you have all your reading in one function, which you run at the beginning of the program, then you may just write another function, which just sets the variables to the values of maximal test, and run this function instead of the original reading function. Then it's only one line of your code that gets replaced, and so there are less bugs, probably, when doing it. However, it still doesn't check your input, and the bugs could be also there. So, in the next video, we'll cover more types of test cases. Apart from minimal and maximal test, there also could be tests in testing for the special kind of problems. For example, if the problem is about strings, then maybe test cases where all letters of the string are equal and all letters of the string are distinct may be interesting to your solution, independent of particular problem. We just use the fact that it's about strings. And similarly, if the problem is about divisibility, then prime numbers could be interesting and numbers with a lot of divisors. So it may do good to you to remember both of different magnitudes. And for other kinds of problems, there also could be interesting cases. So when you testing or solving different problems of different kinds, it will be good to remember what interesting test cases have you found. Until now, we've talked about generally interesting cases, but it will be also good to incorporate the structure of your own program in the test cases. For example, if you have a branch somewhere, then you should include two types of tests, where the condition is true and where it's false. Especially if that's like a principal branch, so you have two principally different solutions for the two cases. One particular example of it is when there are different kinds of answers. For example, problem where there is a yes and a no answer, or a problem where you should construct a solution or determine that there is no solution and output something like -1. Then you should test both types of answers independently. You could also use code structuring in testing large programs efficiently. For example, if you run a large program on some case, you will only see the general output, the combination of different parts. But you could just test each part separately. So it's more efficient because separate parts are simpler, and it also makes sense to start testing the part right after it's finished. So when you start writing the next part, you're already sure that the previous are correct. Now, general templates for test cases are useful, but you should also invent your own test cases, tailored for a particular problem and a particular solution. You may just think about what test case would be interesting for the solution of the problem. But remember that what you find interesting not necessarily is for the program run on the computer. In general, you should test different running patterns of your program, different special and pathological cases to your solution. They often arise from the proof, and in fact, test cases when your program doesn't work are usually just missed cases from the proof, so you could find them by making the proof more formal. And finally, you could just combine all of these ideas. For example, take some custom test and minimize or maximize something, or introduce a minimal test case for some part of the program. Next, let's talk more about testing in general. There are two main stages of testing. First, when you just written a program and you want to check whether it's correct, to not waste attempts on a testing system. And second, when you've already submitted to the testing system, but found out that the solution was incorrect, and so you search for a case where it doesn't work, so you could debug. With the second stage, it's really not many choices you have, only searching more for tests on which to debug. But with the first, there is always a question: how long to test before submitting? Of course, there is always a trade-off. The more you test, the more time you spend, but submitting too early will result in incorrect submission. And choosing how much time to test depends on the severity of the consequences. For example, there are different situations where incorrect submission is just some penalty time or some penalty scores, and completely different situation where your solution doesn't count at all if it's incorrect because it's tested after the end of the contest. So in the first case, you may test a bit less, in the second a bit more. And of course, it depends on the complexity of the problem, because smaller and simpler problems require less testing, and big and complex more testing. But no matter the situation, always test on sample cases, because it's very easy to obtain them. You just need to look at the statement, and there is a very big probability that somehow one bug could still be at your program right after when you ended writing it. It could be, for example, wrongly formatted output or some general bug. So it's surely worth to check if the program works at all. And nearly always try to run tests other than sample tests, because sample tests rarely cover everything. Finally, let's talk about how the process of testing should be organized in general. First, when you find a bug and fix it, then you need to test from the very beginning, because the old tests which worked earlier could now not work. So, it makes sense to save all tests you invent somewhere, so if you find a bug and fix it, you could easily restore them from the memory. And it could be convenient to not just run tests one by one, but having a mean to run simultaneously on all tests which you have invented so far. And there are several ways to do it. First, you could save all your test cases in one file, one after another, and make your solution solve not just one test case, but every test case until the end of the file. That way, you just need to run your solution once, and it will be run on all test cases. And it'll still be a working solution, because in actual test cases, there is only one test case, and the solution will do it and then terminate. Another way is to save all test cases in separate files with some extension, for example, .in, and have a script which runs your solution on every file in the folder with this extension. So you could, with running the script, you could test on all test cases at once, and also introduce meanings to a test by giving them meaningful file names. You could also use a powerful unit testing, if you know how to do it. It may be a little of overkill for the competitive programming, but if you're good with it, it could do all the things also, managing tests and running a program on them. So, that's all for testing in general, and in the next video, we'll talk about stress testing. In the final video of the lesson, we'll cover a powerful technique of automating testing called stress testing. It will often help you find a wrong test case when all other means fail, but it's still not a cure-all. The key idea is to have a program which outputs a random test. We already used Git generators for obtaining a maximal test, but now we want a different test each time. And when we have that program, we could just run it repeatedly, feed the test to our solution, and check if it's correct. If all is done automatically, then we could run 1,000 tests per second, and without our attention. The computer does it by itself. Aside from the generator, there is only one question: how to automatically check if the output is correct. If we are testing for crashes, then there is no need in that. We could just run our program on a test case and see if it crashed or not. That's another benefit of assertions. If our code is covered well with them, then we may just test for crashes. It will also test correctness. In a general case, if you want to check the correctness of your program, you need to have the correct answer. And for that, you could write a trivial solution, which is just the translation of the statement without applying any ideas or assumptions at all. Of course, it may be slow, but it doesn't matter. We could run it on small enough tests. And the point is, as the solution is trivial, it's very likely to be correct. So, to check the output of your main solution, you could just run the trivial solution on the same test case and compare two outputs, considering the output of the trivial solution as correct answer. Even if you've placed a bug in a trivial solution, it's likely to be other bug than in the main solution, and the answers will be still different, so you'll notice. To compare outputs, it's often enough to just test if they are equal. That's where the answer is unique. For example, when I'm asked to find the minimum of something or the number of ways to do something. And in other cases, you need a specific program called checker, which will check if the answer is correct, if there are multiple possible answers. For example, if you need to construct a solution, then you need to check that the solution is correct. And in all, it resembles what happens on a testing system, where your solution is also run repeatedly against tests and check correctness of output of your solution. Only in the testing system, the tests are already prepared, and here we can generate them on the fly. Now, we'll talk about how to write a good generator for a stress test. In fact, it's not as straightforward as it seems. First of all, the generator should produce small tests, because first, trivial solution should work only on small tests, and it's also that with small tests, it will be simpler for debug for us later when we found the test case. And it's also good that when with small test cases, everything runs fast, so more test cases per second. And most often, you'll want to generate test cases of certain size, for example, random strings of length 5. So you need to have some parameter with whom you could easily treat that. In fact, it's also very important what random cases a generator produces. Let's imagine a situation where the input to the program is a string and your solution works incorrectly on all strings which have all their characters equal, for example, AAA. Imagine that you generate random strings of length 10 of letters from A to Z with equal probability of each string. Then, finding a string of equal characters would have a probability of 26 to the minus 9th, which is very, very small. So, a stress test with such a generator would run a very long time. But if you use only letters A, B, and C and generate strings of length 5, then the probability will be 3 to the minus 4th. And that means that in about 1 or 200 steps, we already find the corresponding test case. So, the important thing here to note is that special cases are likely to be small, and so you need to have as small tests as possible in the generator so you could find them in a reasonable amount of time. But the generator also should be general enough. For example, if you use only letter A, then maybe the tests will be much less interesting than with letters A and B. There is also a pitfall with random generator initialization. If it's always initialized by 0, then we will have exactly the same test each time we run the generator. So it's a good thing to initialize with something like system time. So let's put everything in one piece. On the slide, you see a script for stress testing in Bash, which tests for crashes our program. And it's really simple. We just have a main loop, which generates test case, stores it in a file named in, then feeds it to our solution, and after that checks if our solution has exited normally. So, if there is a crash at some point, our loop breaks, and in the in file we have a corresponding test. And if there are no such tests, then our loop will run very long time. On this slide, we see an example of stress testing for checking correctness. Here, we also run generator in the endless loop, then feed its output to our solution, but we also run the trivial solution on the same case. And after that, we compare the output of our solution and the trivial solution. And if they are not equal, we found the content test. Here, we compare them by diff, so only for equality. And if you have multiple solutions, you need to write your own checker and plug in inside the diff here. Now, a couple of general advices on how to do stress testing. First, you should do stress test only after sufficient manual testing. In fact, it's only for the cases where you are out of ideas on what else to test by manual. By itself, stress test is quite simple. It's like a dozen-line script, which you could actually save and use in every problem. But there are other parts: generator, checker, trivial solution, which may be not so simple. And so, if they are as hard as your main solution, it's no point in stress testing. You are most likely to place a bug in those parts than finding a bug in your original solution. So, stress test only if you can do it simple. On the first run, produce tests of small size. As we discussed, it's faster and it will be easier for debug. If you generate small enough tests, there's usually no sense in stress testing for hours. A couple of minutes will suffice, because either a content test will be found, or you just have seen every test of this size. Make use of stress testing running on its own. You could do something useful while it runs. For example, review your code or solve another problem. If nothing is found in a stress test, and you for sure know that the problem isn't correct, for example, if you have submitted it to the testing system, then maybe you should make a test larger. Or just rethink the generator. Maybe the content test is somehow special and it just doesn't pop out in the random tests that the generator produces. Remember that if the tests are large, then it's a small probability of getting one particular test. After you rethink the generator, you may start again with stress testing. Finally, let's summarize what we learned about testing. Always test your solution before submitting. And if it fails, test more to obtain a case for debug. Always test your sample test cases. They are easy to obtain, and you should always check your understanding of the statement against them. You should also try to test on some manual test cases. Interesting variants are minimal and maximal test cases, cases special to a particular kind of problem, and of course everything you could imagine by yourself. Test cases tailored for particular solution and particular problem. Use code structuring to simplify your task. Separate your program on small parts and test them separately. If you are out of ideas for manual tests, you could start stress testing, but only if it's simple enough to do. The most important part of stress test is the generator. You must pay very close attention to what kinds of tests it produces, so a special test case on which your solution fails could be found. And that's all about testing. So good luck with Bug Hunt.
Hi everybody, my name is Alexander Logunov. I am a competitive programming coach at St. Petersburg State University. Experienced programmers know that programs almost never work correctly on the first try. For this reason, be prepared to test and debug your program when you are done with it. In this video, we will learn some of the basic practices of writing code that will allow you to catch bugs at early stages. Imagine that your mobile phone or laptop doesn't work. For example, your device doesn't turn on. This usually happens because only one of its parts gets out of order. Battery, motherboard, one of cables, power button, and so on. And more often, you are unable to understand what particular detail has broken down. If you have a good understanding of the structure of your device, you will disassemble your device, inspect each part separately, and this will probably help you to resolve the issue. But if your device is just like a solid brick for you, the most likely end of this story is bringing it to a service center. And now imagine that you have written a code that should solve a complex problem, and you suddenly realize that your code doesn't work. If it is difficult to break your code apart according to its logic, you will have to explore every line of the whole code. Conversely, if your code is divided into several blocks and you have a good understanding of the dependencies between the blocks, you can analyze each block individually. And besides, your code will be clearer to another programmer who may read it in the future. Let's illustrate this with a toy example. You have information about n people. Assume that the information is stored in a text file. Format is not important. Your goals are to compute the number of people that are employed at this moment and to compute the sum of ages of all people. What you see here is a possible solution. Here we actually read data, compute required values, and print them. But don't you think that this code is not perfect? It is not a well-structured code. The data is read, and the number of employed people is computed at the same time. The variables are initialized, and the answers are output chaotically. Just imagine that a much more complicated task is written in the same style. If there is a bug somewhere, it will be very hard to locate it. It makes sense to change this code to make it clearer. And this is an example of a well-structured code. Logical parts are not mixed. The dependencies between the parts of the code are clearly visible. Each part solves its own subproblem. It is very natural to declare a separate function for each block. The name of every function corresponding to the block should help to understand what is happening in this block. Initializing, reading, getting first value, getting second value, printing these values. Let's see how the code looks after this. It makes sense to try to make each block to be responsible for its own simple task and to avoid tasks shared between blocks. Otherwise, it becomes very difficult for you to track the progress of the task execution. It is better to think how each subproblem is interconnected with the other parts of the problem. It is a good strategy to allocate a special block or a sequence of blocks for each subproblem. If your code is well structured, it will make your life a lot easier. For example, it will be easier to locate a bug. Also, if sometime later you decide to improve your algorithm, it will be easier for you to locate parts of your code that need to be adjusted. Note that the structure of blocks depends on many things. There is no general recipe for breaking your code into blocks. Another important thing is avoiding code copy-pasting. The reason is straightforward. It's possible that a copied block of code is buggy, and by copying it, you increase the number of bugs. Each time when you have two almost identical code blocks, it is better to merge them into one, for example, by defining a new function. For example, when you have to display 5 variables of the same time in a very complicated format, it is better to make a function for it and call this function 5 times. Of course, the perfect code structure is not unique. There are many ways of structuring code reasonably. After all, this is a matter of taste. For example, you can choose a structure that is more natural for you, or a structure which can be most conveniently extended if the task becomes more complicated. Sometimes the only problem with code is that its idea is wrong. This can happen when you misunderstand the statement of the task or when you use a known algorithm incorrectly. This is the most dangerous mistake for a competitive programmer. Probably there are no bugs in your code, but it will not work anyway. When your code is well structured, you have more confidence in it itself. This will allow you to switch to thoughts about the correctness of your ideas at the right moment. If you find problems with ideas, it sometimes turns out that it's enough to change or delete only some blocks without affecting others. It's less sad for you and saves your time. Well-written code is easier to manage. Sometimes the task may change. For example, in the case of considered problem, you may be asked to calculate not the sum of ages, but the maximum of ages. If you make these calculations in fixed part of code, you will only need to change this part. Actually, the most important thing is to understand your code. If you feel that something strange is happening in your code, most likely you need to add more structure to it. Let's consider a standard situation. You have written a code and you are ready to debug it. And now you are reviewing each line of your code. Suppose that you see this line. P is set to Q by 60 plus R. Any ideas what is meant here? Perhaps you guessed that the code computes time in minutes from midnight to the current time. Q stores the current hour, R stores the current minute, and P stores the total time in minutes. Note that even in this case it is not so obvious. Even if you guessed right, maybe you've spent some time on it. There could be surrounding lines that could help you to understand this code. For example, you could look at input-output format and somehow realize the purpose of these variables. But the point is that if these variables were given suitable names right away, you would understand the meaning of this line faster. Giving meaningful names to variables will not only help your teammates to understand your code, it will also help you to understand it. Have you ever found yourself in a situation that it is difficult to get the main idea of your own code that you wrote, say, a year ago? If yes, then you probably know already that it makes perfect sense to keep your code understandable. At the same time, don't take it too seriously. Of course, in some small tasks, like short local loops, single-letter variables are more convenient. A few words about code style. Even if you don't work in team, following some reasonable rules during coding also makes your code more clear. That's why it's recommended to use indents, spaces, and so on. Consider the problem of computing the sum of all integers whose cubes are from 1 to 5,000. The upper bound is non-exclusive. It is possible to find a formula that gives the answer, but it is absolutely normal to write a simple loop for this task. But what loop type to use? There are basically two types of loops: loop with a precondition and a loop with a postcondition, and there is a big difference between them. Consider two examples. Here we see an example of loop with a precondition. The precondition here is I cubed is less than 5,000, and it defines what must be true before entering the loop. In particular, if the condition is not satisfied from the very beginning, the loop will not execute at all. Here is an example of loop with a postcondition. The postcondition here is also I cubed is less than 5,000, and it says what must be true for continuing the loop. It means that this loop always performs at least one iteration, because it just doesn't check the condition before the execution of the first iteration. Both types of loops work fine. But what if we change 5,000 to 1? There are no integers that are at most 1 and less than 1 simultaneously. That's why the correct answer is 0. And it is easy to see that precondition loop remains correct. But we can no longer use postconditions here, because a loop will perform the first iteration and add 1 to total sum. We failed in the second case because loop invariant wasn't preserved. A loop invariant is an assertion that must be true every time within a loop. It is associated with a specific position in the loop. In our task, We can come up with two examples of invariance. First, I cubed is not greater than 1 and is strictly less than 5000. Second, sum equals sum of all i's seen so far. Think which invariants are preserved in each case if we change 5000 to 1. In the first version of task with upper bound of 5000, both types of loops preserve this invariance. But when we change 5000 to 1, in the post-conditional loop, first invariant fails. During the first iteration, I equals 1, so I cubed is not less than 1. Because of this, sum is calculated incorrectly, though the second invariant is preserved. This situation tells us that we should be very careful with invariance. Sometimes conditions in loops are more complicated than I cubed is less than 5000, and you need to be precise to write a loop correctly. In other words, you should always convince yourself that the code of your loop matches your logic. Also, be careful with corner cases with empty sets. For example, let's remember the task about the list of people. If there are 0 people in the list, summary age of all people is defined and equals 0, so we should also consider this case. By the way, our solution still works. To summarize this lesson, we have considered several ways to make our code more structured, understandable, and debuggable. On several examples, we've seen that this is really important and shortens the time of getting a working code. In this lesson, we will be talking about brute force solutions. Such solutions are usually slow, but they are clearly correct and, for this reason, can be useful for investigating a problem and debugging solutions. Before implementing an algorithm, it makes sense to first convince yourself that the algorithm is correct. At the same time, during competitions, time is limited. Hence, coming up with a formal proof is usually an unaffordable luxury. For this reason, in many cases, one ends up with intuitive idea instead of a formal proof of its correctness. But often, intuitive solutions do not work. It'd be good to have an approach with a guaranteed success, where you don't have to rely on your intuition. In this lesson, we will consider the so-called brute force solutions. Such algorithms solve a problem in a straightforward way. They just go through all possible candidate solutions. The resulting algorithm is clearly correct, though in many cases it is going to be too slow. Still, such a solution is useful for debugging other solutions and for investigating the problem. To illustrate the approach, consider the following toy problem. Given a list of digits, write them on the blackboard in such order that the resulting number will be the largest possible. For example, the largest number that can be composed out of digits 5, 7, and 3 is 753. Do you see how to solve this problem for any list of digits? Indeed, the solution is to order digits from the largest one to the smallest. Here, the first solution you come up with turns out to be correct, but it's not always the case. Consider another problem. A robber breaks into a shop and finds more loot than his bag fits. How can he decide what to take? More formally, given the information about items in the shop, namely their weights and costs, as well as the capacity of robber's bag. Can you tell what items should the robber take in order to maximize his profit? The best items are the most expensive, but not very heavy ones. It is natural to consider cost-weight ratio as goodness or utility of an item. Items with large utility seem to be better to take. Hence, let's put items in the backpack one by one in the order of decreasing utility. That's a very natural approach, which is probably would be used in real life. Unfortunately, it doesn't work. Let's see that on an example. Here we have 3 items. The first one costs $2 and weighs 3 kilograms. The second one costs $3 and weighs 2 kilograms. The third one costs $6 and weighs 5 kilograms. The weight limit is 5 kilograms. The second item is the best one in the sense of utility. Let's put it in the backpack. Among the remaining items, the second one is the best, but it doesn't fit in the weight limit. So we are left with the first item. Let's put it into the backpack. We got $5 worth items using our approach, but is it the best solution? Well, no. The largest item itself could have done better. Thus, a solution that seemed to be correct turned out to be wrong. How to distinguish between a correct solution and a wrong one? Note that for the robber's problem, we were just given a counterexample for our erroneous solution. In many cases, finding such an example is tricky. Moreover, for some problems it is already tricky to find a solution even for sample cases from the problem statement. Hence, it would be useful to have a solution that is 100% correct. In the next video, we will be developing such solutions. In this video, we will be developing brute force solutions. In many, but not all cases, it is going to be too slow to be accepted. Still, such a solution is useful for understanding the problem statement and for debugging other solutions. Roughly, there are 2 types of problems. Problems of the first type ask you to find an object from some set A satisfying a certain property. Problems of the second type ask for an object from some set A optimizing the value of a certain objective function. The set A is called a search space. Let me illustrate this notion on several examples. You are given m strings and an integer n. The goal is to find a string of length n which contains all given strings as substrings. We will consider this problem for the strings consisting of letters A and B. This is a problem of the first type. We are asked to find an object with a given property, namely a string containing all given strings. Let's look at an example. We are given 2 strings AB and BA, and the required length of the substring is 3. There are 2 possible outputs. The first one is ABA, which starts with AB and ends with BA. The second one is BAB, which starts with BA and ends with AB. We will solve the superstring problem by trying all strings of length n consisting of letters A and B. For each string, we will check if it contains all given strings. The search space here is the set of all strings of length n consisting of letters A and B. Let's see how it works on another example. Let n equals 4, and 2 given strings are BAB and ABB. For each of the 4 symbols of the required substring, there are 2 choices, and that's why there are 2 to the 4th or 16 strings in the search space. Let's look at them. Now we see all the elements of the search space. For each of them, we've checked if it contains BAB and if it contains ABB. We see that the only string from the search space which contains both is BABB. Therefore, it's the only possible output for this example. Consider another problem. We are given an array and are asked to find a subarray with the largest sum. If all elements of the array were non-negative, we could instantly take the whole array as answer. But if an array is allowed to contain negative elements, this solution will not work. Let's take a look at the example. We see that maximum subarray can include negative numbers. Here it's more profitable to take -2 and 3, but it's not profitable to take -10 and 5. Thus, this problem is not completely straightforward. But let's try our technique on it. This is a problem of the second type. We are asked to maximize the objective function. The search space is easy to determine. It's all subarrays of the given array. It's useful to identify a subarray with positions of its first and last elements. Since we understand what the search space is, we are almost done. Enumerate all possible first-last element pairs, compute the sum of the elements of the corresponding subarray for each pair, take the maximum, and this is it. Recall the Roberts problem from the previous video. Let's give a formal definition of this problem. We are given n items with weights from W1 to Wn and costs from C1 to Cn. The task is to find the largest total cost of the set of items which satisfies the weight limit. Recall the example from the previous video. We have 3 objects, and instead of taking the first 2 of them, as we tried to do in the first video, the optimal way to pack the backpack is to put the third item into it. Let's determine the search space for the Roberts problem. It is natural to define it as the set of all possible sets of items. We will associate items with their numbers, and for our example, there are 8 possible sets listed on the slide. To solve the problem, we simply iterate through all such sets. For each set, we first check whether its total weight is smaller than the given limit. If it is, we compute its total cost and update the answer if needed. Let's summarize the observations. For the superstring problem, the search space consists of strings of length n consisting of letters A and B. For the Roberts problem, it consists of all possible sets of items. And for the maximum subarray problem, it consists of all subarrays, or equivalently all pairs L, R. For the maximum subarray problem, the solution is clear since we understood what the search space is. We go through all pairs L and R with 2 nested for cycles, compute the objective function for each pair, and take the maximum. For the superstring problem, it's not that easy. We have to go through all strings of length n. That could be implemented using n nested for cycles, iterating over the set of letters A and B. In the imaginary pseudo-language, the code could look like this. Each cycle enumerates corresponding symbol of a string, and when they all are fixed, we check the property. Unfortunately, you can't write this in real programming language because you don't know the exact number of nested cycles. In the next video, we will understand how to simulate n nested for cycles using recursion. This will allow us to implement a solution for the superstring problem and for the Roberts problem. In this video, we are going to focus on the implementation technique, which will help us to go through search space of the superstring problem and the Roberts problem. That will lead us to the complete recipe for solving a combinatorial problem, which will work almost always. The technique we are going to study is called backtracking, and roughly it's the way of writing the code equivalent to n nested for cycles. With n nested for cycles, enumerating all strings of length n over the alphabet of letters A and B could be done as shown on the slide. The most convenient way to convert that idea into the actual code is recursion. Consider the first for cycle. If we had a function which simulates n-1 nested for cycles, then we could write the function for n nested for cycles as shown on the slide. That leads us to the idea of recursion. Let's start with 3 nested for cycles. The function for 3 for cycles run the outer cycle and call the function which implements 2 nested inner for cycles. The function for 2 for cycles works in the same way, but it calls a function which implements 1 for cycle. The function for un for cycle is just one plain for cycle. From this code, we can observe that all these functions are written in the same fashion. Thus, we will be able to replace these 3 functions with one recursive function. Note that from outside, we should call the 3-fourths function with x consisting of 3 symbols. It doesn't really matter which ones. The recursive function will simulate behavior of 3 functions from the previous slide, depending on the additional parameter first 4. If it's 0, then the function will behave like the function 3-fourths. If it's 1, then it will simulate 2-fourths, and so on. But now, we do not limit ourselves with only 3 cycles. Our function will be able to simulate an arbitrary number of cycles. Since all 3 functions were written in the same fashion, the code turns out to be quite easy. We enumerate all possibilities for the first non-fixed symbol and run the function to simulate the remaining 4 cycles. Recursive backtracking could be viewed as a tree. Each node represents a single instance of the function nested fourth, and currently active call will be marked red. Edges are labeled with letters A and B that represent the value which is fixed by corresponding 4th cycle. When all 3 letters are fixed, we print the obtained string. Then the function terminates, and an instance which called it continues to evaluate the corresponding 4th cycle. In the next iteration, it changes the last symbol to B and makes a recursive call. New instance prints AAB. Then 2 instances terminate, and the second symbol of X changes to B, and so on. Now we can see how the recursion has printed all 3-letter strings over the alphabet of A and B. As you remember from the previous video, the search space for the Roberts problem consists of all sets of items. How to enumerate them? For each item, we have 2 options. It's either in the set or it's not. If we know which option is true for each item, we know exactly what the set is. Thus, enumerating all sets of n items is essentially enumerating all n symbol strings over the alphabet of 1 and 0. Here, we see how it works for 3-element sets. We write 0 in a cell if the corresponding item doesn't belong to the corresponding set, and 1 otherwise. Empty set doesn't contain anything, and it corresponds to the string of 3 zeros. The set consisting of the first element only corresponds to the string 100. The set consisting of the second element only corresponds to the string 010, and so on. Recall our example from the previous videos. For each set of items, we compute its weight, check if it's at most capital W, and take the maximum cost among all valid sets. And since we learned how to enumerate all n symbol strings on a known alphabet, we are done. Recursion saves us once again. The recipe for designing brute force solution is as follows. The first and the most important step is identifying the search space for a problem. The next step is designing the way to enumerate all elements of the search space. Combine the first two steps together and you will obtain the solution. This solution is usually slow, but there is no question about its correctness. This technique is very useful because it's very powerful. It covers almost all problems. The only reason we have to study something else is that the brute force solution can be incredibly slow. If you want to solve superstring problem with n equals 100, your program will work until the end of the universe and never find the solution. More sophisticated, more specific approaches are faster. But of course, each of them covers a very small subset of all problems.
Hi. As you know, in competitive programming, your solution have to pass each test in some fixed amount of time, called the time limit. And they are pretty tight, usually just 1 or 2 seconds. And usually, you do not need only to do something, but do it fast, and it can be challenging. But how to measure efficiency, aside from getting a verdict from a testing system? And how to predict in advance, will your solution pass or not? And also, how to make solutions faster. We'll find out in this lesson. First, we'll consider an example problem. We are given 2 strings s and t, and we need to check if s is contained in t as a substring somewhere. Let's take a look at some possible inputs. In the first, s is ABAC, and t just starts with it. So the answer is yes. In the second, s is CAC, and in t there is only one letter C. So s couldn't be a substring, and the answer is no. And in the third, s is ABAB, and t ends with it. So the answer is yes. Now, let's develop a solution. We denote as n the length of s, as m the length of t. And what is the most simple thing we could do? We could just take all substrings of t of length n, compare them character by character with s, and if some characters do not match, then this substring is certainly not s, and if all characters match, then the substring is s, and the answer is yes. And if none of the substring matches, then the answer is no. Let's see how this algorithm works on examples. As we are interested in running time, we will also count the number of comparisons which our algorithm makes. In the example on the slide, n equals 4, and we start with the first substring of t of length 4, which just begins with its first letter. Here, the character a is matched, b is matched, the second a is matched, but the first character is b in s and c in t. So that's a mismatch. We made 4 comparisons and saw that this substring is not s. So we move to the next substring of length 4 in t, which starts with its second letter. And here, even the first characters do not match. So we made 1 comparison and seen that this substring is also not s. We move to the third one. Here, the first characters do match, but the second don't. So it's 2 comparisons, and we move to the fourth. Here, also, the first characters do not match, and so we made 1 comparison. And finally, the last substring of t is s, but we need to check it. For it, we need 4 comparisons. So in total, we've done 12 comparisons. Is it much or less? To know, we need to consider other examples. In the second example, strings have the same length as in the first one, 4 and 8. But here, t just starts with s. So we check the first substring in 4 comparisons and see that it's the answer. so we return yes. So we've done 4 comparisons, and that's 3 times less than in our previous example, although the lengths were the same. So we can conclude that the number of operations, and hence the running time, may vary from test to test, even if they have the same size. Imagine that you've written a solution and checked it against the sample tests and maybe some of your own, and it worked quickly every time. So now can you be sure, will it pass the time limit? In fact, you can be, because you've checked only some tests, and your solution have to work fast on every test. In other words, in a worst possible test, where the number of operations is maximized. Usually, problem authors try to think about what is the worst possible case for different solutions, and include all of them in a test set. Let's imagine that we are creating tests for the substring problem. And let's think about what is the worst possible case for our previous solution. It makes sense for the answer to be no, so we need to check every substring. And it would be perfect if we need to compare each character in each substring, and the mismatch would be only at the last character of the S. In fact, there is an example just like that. S contains character B, but T doesn't, so the answer is no. And thus, every character of T and every character in S except the last is A, we need to check every pair of characters while checking every substring. In the first substring, we compare 3 A's and they match. Only the B is a mismatch. And the same in the second, and then the third, and then the fourth, and then the last. So we've made 20 comparisons in total, and that's way more than our previous 2 examples. So, to conclude, we've seen that the number of operations could vary greatly even on a test of the same size. So we can just take big enough test as the worst. Finding the worst possible test case could be rather involved. And to measure the number of operations, we need to have an estimated solution. It would be good if we could estimate running time without needing to implement solution beforehand. So we want to estimate performance of our solution on any input without explicitly constructing anything. And that's what we'll do in the next video. In this video, we'll learn a powerful technique for estimating the number of unit operations in an algorithm. In fact, it depends on input, and we will measure the dependence. As in the end, we want to estimate the running time, we want to count unit operations, the operations which take some fixed small amount of time. There are several important examples of them. They include operations with numbers, like arithmetical operations and comparisons, logical operations, which could be found in if statements, and or working with an individual value in an array, defining a new variable. In fact, these operations do not take exactly equal time. Some of them are faster, some are slower, but only slightly, like the slowest of them is 2-3 times slower than the fastest. However, there are operations which may look just as simple, but in fact be much slower. And most importantly, it's operations with some basic structures, like strings or lists. And examples are comparing two strings, building a new one from many elements, or concatenating strings. They are generally slower because strings and lists consist of a number of small elements. And when we do such operations, we need to do it for each element of the big string or list. And so it's in fact not one operation, but many unit operations like comparing characters when we're comparing strings. Now, remember the substring problem and our simple solution to it. The Python-like code for it could look like this. N is the length of S, M is the length of T. First, we iterate over different substrings of T of length N, and it just their positions from 0 to M minus N. Then, for each substring, we need to check if it's equal to S. We just compare characters one by one, and if some pair doesn't match, we break and move to the next substring. And if all are matched, then this substring is S, and we could say that the answer is yes. If at the end none of the strings has matched, we could say that the answer is no. Now, as we have the solution, we could count the number of unit operations in it. But let's look at the following line. It's just a simple if statement, but in fact, here are 5 unit operations. So the issue is, even for the simple solution, it's tedious enough to count all operations exactly. On the line from the previous slide, there are 5 operations, which is not more, but most importantly, it doesn't depend on anything. No matter what the input will be, or which iteration is it right now, it will always be 5 operations. And in fact, the key idea is, instead of counting all operations explicitly, let's just say that there are the constant number of them. So, how could we bound the number of operations in our previous solution? The outer loop does no more than m iterations. The inner loop always does n iterations. And the code inside it does constant amount of operations. In fact, we don't need to count these operations exactly. We could just look at the code and see that this number is constant. In total, there is no more than m times n times constant operation in our solution. In fact, there are also some operations which happen outside the if statement, but the number is also constant, and it's got multiplied only by m. So in fact, it's counted in our bound. And the good thing about that bound is we don't need to consider any explicit examples to get it. We just look at the code. And thus, it's independent of any particular test. This bound works on all tests. So, let's formalize what we've done for the general case. We are getting upper bounds on the number of unit operations up to a constant multiplier. The idea is that constants arising from different solutions are not very different. They pretty much the same by magnitude. But what really impacts the running time the most is the dependence on the input size. Formally, let n be some parameter of the input, like one of the input variables or the size of the input string. And let f be some function of n, for example n squared. Now, to the most important definition. We say that an algorithm has asymptotic time complexity of big O of f of n if on any test it makes not more than c times f of n operations, where n is the parameter of that particular test. And c is the same for all tests, just some constant. For simplicity, there was only n in the definition above. But we could define the same definition with several parameters. And for example, in our substring problem, the solution has complexity of big O of m times n. Now, how to get such bounds for any solution? Let's state some properties of the big O notation. First, there are always upper bounds. We are just saying that our solution makes no more than constant times something operations. But it doesn't mean that the actual number of operations is equal to it. It could be less. For example, if we know that our solution is big O of n squared, it could also be big O of n, if it actually does no more than n times constant operations. And if our solution is big O of n, it's always big O of n squared, because n is less than n squared. We may consider optimal bounds, which are not just upper bounds, but close to the actual number of operations which our algorithm performs on a worst-case test. But they could be rather involved in different algorithms, and there is no general method of obtaining them. But we could obtain some bounds straightforwardly, as we did with the substring problem. And in fact, they could also sometimes be optimal. We will do that somewhat inductively. First, we'll bound the number of operations of a single statement, then of some piece of code inside the loop, and so on. For a single statement, it's actually simple. If it just contains some constant number of operations, like that if line from before, then it's constant time, or big O of 1. If it uses some built-in structures of functions, it depends on them. So you need to know their time complexities in advance, and they can be easily found in documentation. For structures, it usually depends on their size. For example, comparing strings is linear, big O of n, if n is the size of a string. And any operation that iterates through several elements most likely takes at least size operations to complete. It could also be a call to your own function, but then you just need to separately bound the time complexity of that function. Now, let's see what happens with simple loops. Say you iterate until n, and the code inside is big O of f of n on every iteration. So in total, the complexity will be big O of n times f of n plus 1, because the inner part is repeated n times, and so it's not greater than n times f of n. And also, the loop by itself takes about constant times n operations, because it needs to increment the loop variable and check the loop condition. Of course, actually, the code could be faster, as the inner part could break out of loop sometimes, or on most iterations there could be less operations, but our bound is still correct. And to improve it, you would need to analyze the particular code. Now, let's consider recursive functions. Remember the simple recursive backtracking from the lesson brute force solutions, and particularly the problem of enumerating all strings of len n consisting only of characters a and b. We've got a recursive function that looks like this, and how to estimate number of operations in here. In fact, we could just remember that this code does the same as n nested for loops, each iterating over two letters, a and b. And so, the total number of operations is 2 to the power of n. And the inner part is just print x, as x is the list of n letters, printing it is linear time, big O of n, and so in total we get big O of n times 2 to the power of n. In this video, we've learned what are the big O bounds and how to obtain them. And in the next one, we'll see how to really estimate the running time of an algorithm using the big O bound. In this video, we'll learn how to use big O bounds in practice to know if our solution is fast enough or not. The general steps in solving a problem could look as follows. First, you invent some solution. Then, you check if it's correct, because there is no sense in estimating performance of an algorithm which is just wrong. If it's correct, you should obtain some big O bound, as we've done in our previous video. And the good thing is, in fact, we need only the general structure of the code. So we don't need to implement on the stage. We could just keep the most important parts in our heads or write them down on paper. When we've got the bound, we need to somehow know, will the solution pass the time limits or not? If yes, then we could just implement the solution. But if no, we need to think of some other solution, or maybe obtain a better big O bound on existing solution. For now, let's concentrate on the fourth step. How to know if your solution is fast enough if we have the big O bound. The big O bound is a function of some input parameters, like big O of n cubed or big O of n times m. And these parameters are limited by the statement, So you can just take these limits and plug them inside the big O bound. This will get you some number. For big O of n cubed and n is not greater than 100, you will get 1,000,000. And for big O of m times n, and n is not greater than 10 to the 4th, m is not greater than 1,000,000. You will get a number 10 to the 10th. Of course, the actual number of operations is also this number multiplied by some constant hidden inside the big O notation. But we assume that the constant doesn't vary greatly from solution to solution. So for coarse approximation, this number we got is enough. We will just compare this number with the number of operations that could be done in a second. For fast languages like C++ or Java, this number is about several 100 million simple operations in a second. And as the Python is slower, the threshold for it would be less, about 10 million operations. Of course, we should also consider the constant hidden inside the big O. But you could just think that on average it's something like several dozens. So, as we've got our number, we now could check if our solution is fast enough or not. If it's 1,000,000, like in the first example, then it will most likely pass, as even if you multiply it by a large constant like 100, it still is less than the number of operations per second, if you use the fast language. But if this number is 10 to the 10th, then it's no way it will pass, because even if the constant is only 1, which is nearly impossible in practice, you are still above the number of operations per second. So we've got a way to coarsely estimate if our solution will pass or not. And in fact, nearly always this is estimated enough. But what to do if we are somewhere between? Our number is not too small to surely pass, and not too large to surely not pass, like 10 to the 8th for the fast languages. But first, a bit more about the big O notation in general. Asymptotically, big O of n is better than big O of n squared. But that, in fact, doesn't consider constants at all. And what if the first is 1,000,000 operations, 1,000,000 times n operations, and the second 10 times n squared operations, and n is not greater than 100. So in the worst case, the first is 100,000,000 operations, and the second is only 100,000 operations. So the second is much better. Also, you won't really get a constant like 1,000,000 in practice. It's still important to remember that you are interested in estimating the number of operations, not in formal time complexity. So, it makes sense to count large factors, even if they don't depend on the input. For example, if you have two loops, one iterates over n, and the inner iterates over all letters of the alphabet, then formally it's big O of n, as the alphabet has always size of 26 letters. But for the number of operations, you should use not the constant times n operations, but constant times 26 times n operations. Thus, your prediction will be more accurate. When considering constants, it's useful to know that not all unit operations are equally fast. Some of them are fast, like arithmetic operations with integers or logical operations, but some are a bit slower, like taking reminders or making recursive calls, or appending to lists, or using math functions like a square root. And particularly slow are input-output operations. In fact, some ways to do input-output may not just be slow, but like super slow. So later in the course, we'll cover how to efficiently perform input-output operations in different languages. Now, let's return to a situation where we've estimated the general number of operations in the big O bound, and are still in doubt whether our solution will pass or not. Here, it may be useful to think about the constant hidden behind the big O. Is it relatively big or small? If you have just a few light operations, then you may assume that even a larger bound is fast enough, like 50 million. But if there are many operations inside the constant, or if they're heavy, you could receive a time limit exceeded verdict even with smaller values, like 10 million. Here, you should consider only operations really contributing to the running time. For example, taking square root is much slower than summing integers. But if in your program you have 1 square root and a million additions, then it's no sense considering that. All time is spent on additions, and having square root doesn't really change anything. So in the next video, we'll talk more about how to identify frequent operations and how to make solutions faster. In this video, we'll learn how to make solutions faster and how to actually measure the running time. In fact, it's very useful to know which parts of your code are fast and which are actually eating up all the time. And that is also conveniently done by the big O notation. Imagine that you have some code for which you've got the big O bound, and you want to know how much some particular line contributes to the bound. Let's say that it calls some function, do something, and is placed inside two loops, one until n and the other until m. So, in this case, it's easy to see that our particular line contributes big O of n times m times how many operations does the do something function. Then, it may be really important to performance. If the total complexity is big O of n squared times m, and the complexity of do something function is big O of n, then its contribution is big O of n times m times n, which is big O of n squared m, the same as the total complexity. Of course, the whole program may have a larger constant, but you won't get better asymptotically without optimizing this particular line. For example, by repeating it less times, or by making a function do something itself faster. Or it could be not so important. If the overall complexity is big O of n cubed m, then our line is already n times faster than something else. And so, optimizing it is useless. Even if we just take it away, there is still some part which takes big O of n cubed m operations. And in fact, it's this part that's holding everyone back, not our do something function. In fact, knowing which parts are the slowest is very important in making a solution faster. Let's imagine a general situation. You have some solution, but it's too slow. Either you've estimated the number of operations and it's too high, or you just send it to the testing system and got the time limit exceeded verdict. Of course, you could just invent another fast solution from scratch. But more often, you could just improve your current solution. First, you should always try to improve asymptotically. Not the constant behind big O, but the dependence on the size of the input. Because it's only these improvements that are really efficient. And you should try to speed up only the slowest parts of the solution, which have the big O bound the same as the whole solution. Because other parts are already asymptotically faster. If that fails, and moreover, your solution is just a bit slower than needed, for example, 1.5 seconds against the 1 second of time limit, then you might try to optimize the constant hidden inside the big O. But otherwise, it's useless. There is no sense in replacing two additions by 1 if there is 10 to the 12th of them. That will never pass anyway. Usually, there is no need in this at all, as asymptotically optimal solutions work much faster than needed, and the others work much slower. If you've still decided to optimize the constant, you should also do it where it counts. One way is to get rid of heavy operations, or make them less frequent. In particular, you should delete any substantial debug output, as it's unnecessary and really slow. Another potentially fruitful way is not recomputing something twice. If it's really the slowest part, then it could speed you up like 2 times. So far, we've only considered theoretical bounds on the number of operations. But you could also measure the actual running time. But that has one downside. You need to have an already implemented solution for that. It could be done via the testing system. If you just send a solution, you most likely will get the time on the worst case. But it depends on the rules. Some platforms, like Codeforces, even have a remote run interface, where you could run your program as though it's testing. But you could also do this on your own computer. But for that, you will need the worst case test. And in fact, performance on your machine could be different from the performance on a testing system, because it depends on the environment, particular machine specs, operating system, version of the compiler, and so on. However, locally you've got more power. You could measure different parts of your code and do this without wasting attempts on a testing system. Locally, the most simple thing to do is to count the number of times some function is called. You could just take some variable and increase it each time you go in that function. You could also do this just with some particular place in the code. And in the end, you could just output that variable and see the precise number of calls. It could help if it's hard to estimate theoretically. You could measure the running time of the whole program with the standard system utilities, like time on Unix-like systems. But you also could measure the time from inside the program. In any language, there is a system function which returns elapsed time. So you just store the time before, and in the end, subtract from the current time. In this way, you could measure not only the time the whole solution takes, but some particular parts of it. And it's really useful if you want to know which parts are actually slow and which are fast. There are also special programs called profilers, which measure running time and the number of calls for each function in the code. And that's just another case when well-structured code benefits, because if you have no functions, then it will give you no useful information. But if you structure it well, each function contributes some amount of time, and you'll see it. So, we've talked about the time limit. But there is also the memory limit. Your program should not take more memory than it's stated in the statement. We could do something like big annotation here. But in fact, the memory limits are usually much weaker than the time limits. For example, if you do too many appends to lists, it would most likely break the time limit first, not the memory limit. The only common cause of getting a memory limit exceeded verdict is too large an array. But you could explicitly calculate the size of an array by just multiplying dimension and the size of the variable. You just need to know how much each variable takes. So, to summarize what we've learned about the time complexity. Your solution should work fast on any test, including the worst case one. Now we know how to get bigger bounds on a number of unit operations, and you should always obtain such bounds before implementing a solution. Otherwise, you could waste much time on a solution that clearly couldn't pass. To check if the solution is fast enough, you should take the limits on the input variables from the statement and plug it inside the bigger bound, and compare that number with the number of operations that could be done per second. That's a coarse estimate, but nearly always it's enough. Speed up only performance important parts. Even if you could greatly improve something else, it will not affect the running time. First of all, try to make solutions fast asymptotically. Optimize constants only as a last resort. Sometimes it could be useful to not just estimate the number of operations, but to actually measure the running time, especially when dealing with constants. And that's all for this lesson. So, good luck! Hi, in this video we'll talk about numbers. Numbers are the most fundamental units of your programs, but numbers in a computer do not always behave the same as your usual numbers in math. And this could lead to very subtle bugs, which are very hard to find if you do not know beforehand. So in this lesson, we'll learn how numbers are stored in a computer, what are the most common issues with them, and how to deal with it. So, in this video, we'll begin with integers and their most common issue, the integer overflow. What could possibly go wrong with such simple data type? Well, let's look at the following code in C++. It just takes two integers and multiplies it, prints out the result. What do you think the output will be? It turns out the result is not 2.5 billion, but some totally unexpected negative number. And in Java it will be the same, but in Python everything will be fine. So what happened? To know, we need to learn a bit more about how numbers are stored in a computer. You could think of a computer's memory as a very long sequence of bits, binary digits, each taking value of 0 or 1. And when you write integer constants at 13, for computer it is in fact 1101, as everything should come in binary. And indeed, 13 is 1 plus 4 plus 8. But in fact, the bits come in chunks of 8, which are called bytes. So the memory looks more like this. And it's because you could not take the value of an individual bit. You must take the whole byte. So when you create an integer variable in languages like C++ or Java, it always takes 4 bytes in memory. And when you assign some value to it, these bits are set so that the whole 32-bit number is equal to this value. So for example, for 13, there will be many zeros in the beginning and 1101 in the end. So that's the most common integer type, int. It has 4 bytes or 32 bits. So it could store at most 2 to the 32nd different values. And that's clearly not all integers. All integers are infinite. And in fact, it stores just a consecutive range of values. And half of them are negative. So it's the range from -2 to the 31st up to 2 to the 31st minus 1. Since it's simpler for us to work in decimal, we could just think about 2 to the 31st as a number slightly more than 2 billion. Now, it's easy to see what's wrong with our example, because 50,000 times 50,000 is 2.5 billion, and that is more than 2 to the 31st. So that's what is the integer overflow. When the result of some operation do not fit in the range, in fact, some other value is stored. And of course, getting incorrect value somewhere could lead to an incorrect answer. So we would like to avoid that. In fact, fixed integer variables are true for languages like C++ and Java. In Python, integers are arbitrarily sized, meaning that the result of some operation is too large, the variable size is expanded as needed. So in Python there is no overflow, but you should still think about the magnitude of the values, because larger values mean more space and time. What could help us outside Python is some larger integer type. And indeed, most programming languages have 64-bit integer type. In C++, this type is called long, or int64_t. In fact, the first one is not guaranteed to have exactly 64 bits. But in fact, in any popular platform, it's so. So in competitive programming, the first one is used more often. In Java, this type is called long. As it has 64 bits, it could take 2 to the 64th different values. And as with integers, it's the range from -2 to to the 63rd up to 2 to the 63rd minus 1. A simple calculation shows that if we multiply two ints, then the result will always fit in a log-long. And that is very useful. And even more so, if you take two values, each not greater than a billion, then the result will also fit. So, in this video we learned what is overflow and what integer variables do exist. And in the next, we'll finally learn how to avoid it. In this video, we'll talk about how to avoid overflow. So how can we do that? The most obvious and in fact useful approach is just take the values that do overflow into some larger type. So fixing our previous example could look like this. If the product of A and B doesn't fit in an int but fits in a log-long, let's just put it in a log-long. The code given here and later is considered as C++, but in Java it will be the same, only instead of long-long, they will be long. However, that doesn't solve a problem. If you run this code, the result will still be incorrect. Why is that? Because assignment works as follows. First, the value of the expression on the right is calculated, and only then it's put in a variable on the left. And when you multiply two integers a and b, the result has type int, because a and b also have type int. And so the overflow does happen, but before the assignment and in the computation. And so the result will still be incorrect, because we put in a larger value already overflowed result. Well, what if we write the product like this, without any variables, just two integer constants? Maybe it will help. In fact, no, because integer constants also have the type int, and it happens almost in any language. Well, how to avoid overflow correctly? We've seen that if you multiply two ints, the result will be an int. So if you multiply the long-longs, the result will be a long-long. So a possible solution could look like this. We just make our variables a and b of type long-long, and the product will also be a long-long. And so everything will be fine. In fact, it's enough to do this with only one of the variables. But it's safer to put everything long-long, so as to not forget it somewhere. There is another option. You could still have both variables of type int, but before the multiplication, cast one of them to long-long. What happens there is that the variable a is put in some temporary variable of type long-long, and then multiplied by b. As one of the factors has type long-long, the result will also be a long-long, and so there will be no overflow. So we've learned a way to beat overflow. Just use the 64-bit integer variable where needed. Some further remarks about that. Of course, large values do not come for free, as the 64-bit integer type has twice more space as the int type and is also likely to be more slower. The most obvious sources of overflow are products. In fact, you should always think about overflow when multiplying two integers. You could just take the limits on the variables from the input and see if in some particular operation there will be overflow or not. However, sums could also lead to overflow. Take a look at the code on the slide. It's the same as the previous one because multiplying 50,000 by 50,000 is the same as adding 50,000 times. But the variable that stores the result here has the type int. And as we know, the actual result could not fit in there. So there also will be overflow, even if we don't use the products. The solution here is like previous, just make the variable which stores the result of type long-long. For now, the only option we have is to use 64-bit integers. But what if the result doesn't fit even in there? Luckily, in competitive programming, nearly always 64-bit integers are enough. If somewhere your value does exceed this range, you should think again, in fact. Most likely, you don't need this value at all. You could reorder computations or get rid of these large values in some other ways. Of course, there in fact could be problems where even 64-bit integers are not enough and you need some really large values, but they are uncommon and advanced. So, to sum up what we learned, when multiplying or adding integers, you should always think about possible overflow. To check whether overflow happens or not, you should take the worst case values of the input variables, which you can find at a statement, and see if the result of some operation fits in an int or not. If the result of some operation doesn't fit, use 64-bit integer type. But remember to use it before the computation, not after. So, that's all for this video. In the remaining part of the lesson, we'll talk about non-integers, and there the things are even more interesting. In the following several videos, we'll talk about issues of non-integer arithmetics. They could be far more involved than just simple integer overflow. Let's start with some simple math. If you take a divided by b and then multiply by b back, you will get exactly a. But of course, we want such basic equalities to hold in our programs too. But do they? It turns out, if you take 1 divided by 49 and then multiply back, you will get something which is not equal to 1. So why does this happen? And what to do if even such basic properties do not hold? For that, we'll need to know how non-integers are stored in computers. Well, we know how to store integers. So what could we do with non-integers? First of all, consider rational numbers, numbers of the form a over b, where both a and b are integers. They arise naturally when we try to divide integers, like 1 over 49. So, storing them is pretty straightforward. As the numerator and the denominator both are integers, we could just store them as integers. Knowing a fraction by its numerator and denominator, we could do basic arithmetical operations. On the slide, you see the rules for adding and multiplying values of this form. And a good thing about this approach is that the numbers are stored exactly. There is a one-to-one correspondence between different rational numbers and different numerator-denominator pairs, if you consider them reducible. So, our example would be alright. If we divide 1 by 49, we will get a fraction 1/49th. And by multiplying back, we will get a fraction 49/49th, which is equal to 1, if we reduce by the common divisor. But why numbers are not implemented in this way? At first glance, this approach seems very good, but in fact, there are some issues. First, remember the implementation of integers. The maximum value we could store is bound, because there is no way to store infinite values in some finite space. But with rational fractions, we also could net as close to 0 as we want, because the denominator is an int, and so is bound by 2 to the k minus 1. The k is equal to 31 if it's an int. So we limit not only the magnitude, but also the precision. In fact, there is also no way of storing arbitrarily close to 0 numbers, because even numbers of the form 1 over k are infinite. So limit precision will be an issue for any approach, although we'll get much better precision with the same space. However, there are issues special to storing rational numbers. Both numerator and denominator are integers. So we have to store them in some standard integer type, like int. But even short sums of small fractions could have large values. For example, the sum from 1 to 1/25 has the numerator and denominator of several billions, and so there will be overflow if the type int were used. This happens because ordinary fractions also feature multiplication of integers. We need to get to the common denominator. And that is a big problem, in fact, as we would like to have more than a dozen additions in our programs. Second, there are many irrational numbers, those which just couldn't be represented as a ratio of integers. Important examples include square roots, they appear every time you want to calculate some length, pi, which is needed for arc length and trigonometry, the base of natural logarithm e, and so on. Next, let's look at the concept of decimal fractions, numbers like 2.37 or 0.125. They are just a special case of rational fractions, where the denominator is some power of 10. In general, a decimal fraction is just the number without the point divided by the 10 to the power of how many digits there are after the point. For example, 2.37 without the point is 237, and we divide by 100 because there are 2 digits after the point. The good thing is, any real number could be written as some decimal fraction. But there is a problem. These fractions are often infinite. For example, the square root of 2 is 1.414 and infinite digits more. And 2/3 is 0.666 and so on. With that, we have a way of representing any real number as some decimal fraction, by rounding. Say, we want to have 3 digits after the point. So we round anything we get up to the 3rd digit. Square root of 2 becomes 1.414. 2/3 becomes 0.667. Of course, after rounding, it's not the same value anymore, but it's pretty close to it. The error, the absolute difference between the actual value and the rounded, is not greater than 10 to the thirds, 10 to the minus thirds, over 2. And if we keep more digits, the error will be even less. In fact, that's the key idea of non-linear arithmetic in computers. We could round any value to some fixed number of digits after the point, but at the cost of errors. However, for computers, base 2 is far more natural than base 10. So it makes sense to consider binary fractions instead. They behave pretty much the same as decimal fractions, only the base is 2. For example, 1.01 in binary is 101 in binary over 4 is 5/4. And 0.001 in binary is 1 over 8, 1/8. And the general scheme remains. We need to take the whole number without the point and divide it by 2 to the power of how many digits there are after the point. The only thing changed is base, from 10 to 2. The number 2/3 will be written as the infinite fraction 0.1010101 and so on. And we could also do rounding here. If we round up to the 3rd digit, we would get 0.101. And similarly, the error will be now more than 2 to the minus 3rd over 2, which is 2 to the minus 4th. So, in this video we've seen how integers help represent non-integer numbers in fractions. In next video, we'll cover in more detail how the binary fractions are used and how the errors behave. Now in binary fractions, we've got another way of representing real values, by the binary fractions with a fixed number of digits. For example, if we use 64 bits, we may say that the point is always in the middle, and so the first 32 bits are the integer part, and the other 32 bits are the fractional part. In fact, we could just store 64-bit integer a and think of it as the number a over 2 to the 32nd. Let's think a bit about what properties such a type would have. The maximum value will be when the first part is the maximum value of int, and the second part is all ones. So there'll be something about 2 to the 31st, or slightly more than 2 billion. Similarly, the minimum value will be when the first part is the minimum value of int, and the second part is all zeros, and that will be minus 2 to the 31st, or slightly less than minus 2 billions. So we could store any value from the range from minus 2 to the 31st up to nearly 2 to the 31st with the error of 2 to the minus 33rd, as we're rounding to 32 binary digits. Of course, we could add our numbers, and in fact, it will be the same as adding 64-bit integers, because the point always stays 32 digits from the end. And as for adding integers, there could also be overflow. We could also multiply, but that has some issues. As we're multiplying two 64-bit integers, the result will have 128 binary digits. So there are 64 extra digits, 32 at the beginning and 32 at the end, as the point is right at the middle. The 32 digits at the end is not going to be the problem. They're just going to be rounded. But the digits at the beginning are like overflow. They just couldn't fit in the value that we're storing, but ignoring them will change the value very much. So we could multiply only small enough values, or rather there will be overflow. Now, as there are always errors with rounding, let's take a closer look at them. We already know one type of error, the absolute error, which is just the absolute difference between the actual value and the value we have. Say we are storing some real number a in our fixed point representation, so that we number it, we round it to the number a hat, which has exactly 32 digits after the point. And as we know, the absolute error of this will be not greater than 2 to the minus 33rd. If there are values a and b, and we store the rounded versions a hat and b hat, and we want to sum a and b, we would sum our values a hat and b hat. So what will be the error after that? It turns out that the error of the sum is not greater than absolute sum of the absolute errors of the values. So the errors do sum up. If we just round it, a hat and b hat from a and b, the errors in each will be 2 to the minus 33rd, and the total error will be 2 to the minus 32nd, which is not much. But the more operations we do, the larger error will accumulate. We could also bound the absolute error of the product. By subtracting and adding a hat times b, we could group as follows. The absolute error will be no greater than absolute value of b times the absolute error of a plus absolute value of a hat, which is close to the absolute value of a, times the absolute error of b. So the errors do not only sum up, they also get scaled by the magnitude of the values. And that is bad potentially. If a is equal to billion, and is stored without error, so a hat also is equal to billion, and b is equal to 1, but is stored with an error of 1 billionth, then the product will have the error of 1, a billionth time greater than it was before multiplication. So the absolute error does not go well with products. From that point of view, it's natural to consider another version of error, the relative error, which is just the absolute error divided by the magnitude of the exact value. So it's not about how big the number is, it's about how big it is relative to the exact value. And it turns out that this new definition goes well with multiplications. The relative error of the product is not greater than the sum of relative errors of the factors. In our previous example of multiplying billion and 1, the relative error of A is 0, and the relative error of B is 1 billionth. The relative error of the product is also 1 billionth. However, the relative error is not that good with sums. Consider the values of A and B from the slide. The relative error of the sum is just 1. But the relative error of A is 0, and that of B is 1 billionth. So the error has grown a billion times with summing. So in fact, we want both the absolute error and the relative error be bounded. So the errors will be tractable both in addition and multiplication. Let's see how a fixed point data type behaves with errors. With absolute error, it goes pretty well, at least while storing. The problem is the relative error depends highly on magnitude. When we are about maximum possible value, we use all 64 bits to store actual digits. And so the relative error is about 2 to the minus 64th. But when it's about the minimum possible positive value, we use only the last digit to store something. And all others are just zeros. So the relative error will be about 1/2, which is big enough. At an average by the order of magnitude value, about 1, we use only half digits to store something, and the other half is just zeros. So in fact, we could do a bit better. And we'll do that in the next video. In this video, we'll finally learn how non-integers actually work in computers. Remember that the problem with fixed point numbers was that some values were stored with very high precision, while others with very low. Let's take a look at some arbitrary non-zero real value, written as binary fraction, either finite or infinite. In the beginning, there are many zeros. Then there is the first non-zero digit, which is 1, because each digit is either 0 or 1. The zeros in the beginning are not important, they're just zeros. The first one is important, but it will always be 1, as there are no other digits. And the digits which follow that first one are what actually defines our number. So the key idea is, let's store some fixed number of digits after the first one. These digits are most valuable in defining our number. But storing only them is not sufficient. We also need to know the position of the first one, because otherwise we would treat values differing by the power of 2 as equal. So in fact, we will store our number in the form 1 point some digits times 2 to some power. As multiplication by 2 is just shift of the binary fraction to the left, the power is just the position of 1, considering the position of point as 0. So for example, we could say that we are always storing 8 digits after the first one, and in 4 digits more, we store the position of that one. In that way, we could store any fraction from 1.8 zeros to 1.8 ones with any shift from -8 to 7. The largest value is when fraction is all ones, and the shift is 7, so it's nearly 2 to the 8. The minimum possible positive value is when the fraction is 1 and all zeros, and the shift is -8, so it's 2 to the -8. As any number is rounded to 9 first digits, 8 are stored explicitly, and the first is always 1. So the relative error of storing is not greater than 2 to the -9th. Let's see how arithmetic operations are performed with values of this form. Say we want to sum these two values. First, as they have different shifts, we need to align them, so the point is at the same position in both numbers. After that, we could add them and store the result as we always do. We store the 8 digits after the first one and the position of that one. Note that as we are keeping only 8 digits, the tail of the smaller term could get rounded, and some digits of it could even not affect the result at all. But that is fine, as we always keep in 8 the most important digits. And in this example, the result is substantially larger than a smaller term. Now to the multiplication. It's somewhat simpler, as we could separately multiply fractions and get the result in the form 1 point some digits, and separately multiply the powers of 2, which is just odd in exponents or shifts. Of course, the product will have more than 8 digits after the first one, but that is fine, as we just round them as always. We are still keeping the 8 most important digits. Note that there can't be overflow when multiplying such numbers. We always take 8 first digits. But there could be overflow in exponents, as we're just adding 4-bit integers. And we've basically scraped the floating-point numbers which are used by computers. Only, of course, they have more than 12 bits. The most popular type, double, has 64 bits. It's called double in C++ and Java, and it's also the standard floating-point type in Python. Out of these 64 bits, 52 are the fraction, which is digits after the first one, 11 after the exponent, and 1 is a sign bit, as we also would like to store negative values. So the whole number will be -1 to the power of the sign bit times 1 point digits which are stored as fraction times 2 to the power of the integer that is stored in 11 bits of exponent. Now, let's estimate properties of this type. The maximum value is about 2 to the 2 to the 10th, which is about 10 to the 309th, and that is quite big. Symmetrically, the minimum positive value is about -10 to the 309th. And the cool thing is, it's a very huge range for this small space. If we wanted to store such range in a fixed point number, we would need to store 2 to the 11th bits instead of just 64. Our win is that now we are storing only the order of magnitude in the exponent, and that is exponentially better. Of course, we get only so many digits as we store, and that is 53 binary digits or about 16 decimal. So the relative error of rounding is about 2 to the -53rd, or about 10 to the -16th. Well, we've learned how floating point numbers, and particularly the type double, work, but where we should and shouldn't use them, and how to not let errors spoil everything. We'll find out in the next video. From the previous video, we know how awesome the double type works. But let's compare it with a 64-bit integer, the same size. Of course, not everything could be done with integers, but there they suffice. They turn out to be much better than doubles. First, double has less bits for actual digits, 53 versus 64, as the exponent should be stored separately. Doubles could be noticeably slower than integers, 1.5 or 2 times. The good thing is that doubles are not susceptible to overflow, because the fractional part is always the first digits. There could be overflow in exponent, but it will happen at magnitude about 10 to the power of 300. So in practice, that's really not a problem. But the worst thing is, with doubles, there are always errors. We've already seen how the values like square root of 2 or 2/3 are stored with errors. But even decimal fractions also have the errors. For example, if you add 0.1 and 0.2, you won't get exactly 0.3. Of course, it's nicer with integers, where all values are exact. So you should use floating point numbers only when they are really necessary. And when integers suffice, use integers, because with them you don't need to treat errors. The first example, when doubles are not needed, is with rational numbers. As we've seen, we could store the numerator and denominator as integers. But there is a problem of overflow. Second, if you need to work with decimal fractions, where the number of digits after the point is fixed, you could just think of them as integers, multiplied by the corresponding power of 10. For example, if you work with prices like $2.49, you could just think of it as 249 cents. There are situations where square roots are necessary, but you don't always need to explicitly compute them, especially if you need just to compare them. For example, if you want to iterate over all integers which are less than square root of n, in a loop, you could replace the statement I is less than square root of n by the equal statement I squared is less than n. If the numbers are non-negative, then the statements are equivalent, but the second is always integers. And in other example of the roots, if you need to compare length and the coordinates are integers, you might just compare the squares of lengths. The length is like the square root of x squared plus y squared, and its square is x squared plus y squared, an integer. And as lengths are non-negative, the square root is less than square root is equal to the value is less than value. However, sometimes you can get away with integers and are forced to use doubles. The most common case is when you need to output some value which is not an integer. And also the statement should specify with how much an error you could output the value, because we know that with doubles there are always errors. Usually it sounds like the absolute or the relative error should be now greater than 10 to the minus 6. It means that if you output the value which has either the absolute difference to the actual value or the relative difference not bigger than 10 to the minus 6, then this value will be considered as correct answer. A dangerous pitfall there is that your number may have enough precision, but on the output it could be automatically rounded, and so have error more than needed. So it's safer to always output some fixed number of digits after the point. On the slide, you could see how to do this in C++, Java, and Python. However, even when doubles are absolutely necessary, you should still try to stay in integers for as long as possible, because the less floating point operations, the less are errors. First example, say you need to sum 3 fractions. The straightforward way is just divide each to a double and then sum them up. That will be 5 floating point operations. But there is another way. You could just sum them as rational fractions and only at the end divide two integers to a double, and that will be 1 floating point operation. A similar example, you need to do 3 divisions in a row. You could just divide in doubles, and so there will be 3 divisions, each a floating point operation. But you could also multiply all divisors and then divide by this value. Because divisors are integers, only one operation will be floating point. Now, imagine you need to calculate a square root of something, multiply it by some coefficients. You could just take a root and double, then multiply by the first, then by the second. That will be 3 floating point operations. But you could also take everything inside the square root, multiply that as an integer, and only after that take the square root. And it will be only 1 floating point operation. On the other hand, with integers there could also be overflow, so you need to watch for it and switch to doubles where it could happen. So, if we decided to use doubles, we need to know how to do it correctly. Earlier we've seen that due to errors, some usual things do not work. For example, the equality operator tests if the values are exactly equal, and even small errors render it practically useless. The solution is, let's consider a and b equal if their absolute difference is not greater than some small value epsilon. This way, even with small errors, we would consider equal values as equal. The other comparisons also need to change. For example, a is strictly less than b should become a is less than b minus epsilon, because the numbers from b minus epsilon to b are now considered equal to b. A is less than or equal to b should become a is less than b plus epsilon, because the numbers from b to b plus epsilon are also considered equal to b now. For now, we've learned about equals to is strictly less than, and is less than or equals to, but is greater than is defined symmetrically. Using epsilon when comparing is necessary, but it also increases errors. So you might want to just use a is less than b if it's good enough. For example, if you are sorting values and it doesn't matter if some are close or not, you might just use the standard less than operator, and so reduce errors by some. There are other operations which are bad with errors. For example, rounding. Floor, which rounds the value to the nearest smaller integer, and ceil, which rounds to the nearest greater integer. The problem here is that even the small change of argument could change the result by 1. The floor of 1 is 1, but the floor of 1 minus 1 billionth is 0. So, if our value is an integer, but we store it with some small negative error, we would get our value minus 1 if we use floor. And that is bad. So, you may want to write, instead of floor of a, just floor of a plus epsilon. And if the epsilon is big enough, it will overcome all errors. And if it's sufficiently small, there never be such that a is less than some integer, but a plus epsilon is greater than it. So, we need the epsilon constant for comparisons in rounding. But how to choose that constant? In fact, we could just take each operation in our program and carefully bound the error which arises here. In the end, we could take the highest of the bounds and take it for the value of epsilon. Then all our errors will be not greater than epsilon, and it must likely be sufficiently small. But it would be tedious and very time-consuming, so it's hardly ever done on the contest. Instead, people just take some feasible value, like 10 to the minus 8 or 10 to the minus 9, and hope that it works. But what if you set some value of epsilon and it doesn't work? Using debug, you could find the first place where the error appears. It may be that the bug is completely unrelated to the epsilon. But if it is, it should be something like comparing two values which are calculated correctly but compared incorrectly. Then it's one of two cases. Either unequal values are treated as equal, and that means our epsilon is too big. We should make it smaller. For example, we could take the next power of 10 and see if it's small enough. Or the errors get too high and equal values are treated as unequal. That means our epsilon is too small and we should try to increase it. We could take next power of 10 and see if it works. So, we've learned to use doubles only when they're really needed. And we've learned to overcome errors by using epsilon. In the next video, we'll cover some more practical issues. This is the final video of the lesson, and we'll learn 3 more practical things about floating-point numbers. How to reorder computations to minimize errors, what alternative the double type has, and what are the special values of double. Usually, there are several ways to compute something. Mathematically, they could be equivalent, but as the errors grow differently when we use floating-point numbers, it could make sense to reorder computations as to minimize the errors. Let's look at an example. If you try to compute 10 to the 18th plus 1 minus 10 to the 18th, you won't get a 1, but a 0. Earlier we've seen that when adding floating point numbers, the precision of the smaller could get rounded. And here, 10 to the 18th is so relatively big that the 1 is lost completely. So, the conclusion is, try not to add values of different magnitude. Think of the following equality. X squared minus y squared is equal to x minus y times x plus y. Mathematically, the equality always holds. But for doubles, there could be a difference. If y is equal to a billion and x is equal to y plus 1, then the left part gives us 2 billion and the right part gives us 2 billion plus 1. The latter is correct, but why is 1 lost in the former? When we compute x squared minus y squared, it's in fact 10 to the 18th minus 2 billions plus 1. And we've already seen that in such additions, 1 would be lost. So that's an example of how we can reorder computations as to minimize errors. Because when we compute x minus y times x plus y, the much smaller values get ordered and subtracted, and so there are smaller errors. Although double is the most standard floating point type, there are other types in different languages. In fact, the word double didn't come out of nowhere. It means double precision, as opposed to a single precision. In C++ and Java, the single precision floating point type is called float. It has 32 bits, twice less than the double, and it stores only 24 leading binary digits and 7 bits of exponent. 24 binary digits is nearly equal to 7 decimal digits, so it's rather small. And in fact, you should never use this type on competitions. Only if you need very little precision and very high performance. In fact, there is also a chance to get a larger version of double. In C++, there is a long double, which has the size of either 80 bits or 64 bits as the usual double. It depends on the version of the compiler. In GNU C++ compiler, it's usually 80 bits, and in Microsoft Visual C++, it's usually 64 bits. You could tell what actually is it on your compiler by looking at the following constant. It tells you how much leading digits are stored in this type. So it will be 64 for 80 bits double, and it will be 53, as we already know, for the usual double. So the long double stores 11 extra digits if it has 80 bits. And 11 extra digits could be useful. You could be slightly less careful with choosing epsilon or with order computations. But of course, in general, the issue of errors still remains. Also, in Java and Python, there is arbitrary precision floating point type. It's called big decimal or decimal correspondingly. It could store as many leading digits as you set. But of course, the more digits we are storing, the more space and time it takes. And you can't just take extremely many digits, because then operations would take a long time to complete. In fact, in competitions, the usual double type nearly always suffice, if you keep in mind how errors behave. Due to the structure of the double type, it could keep some values which you can't find in integers. For example, if you divide integer 1 by integer 0, your program will crash. But with doubles, it will divide all right, and you get a special value, positive infinity. Both these values satisfy some natural properties, like the positive infinity is greater than any number, the infinity plus 1 is infinity, and so on. But what if you subtract infinity from infinity? What will you get? It's hard to imagine some reasonable result. But in fact, there is another special value for that, a none, which stands for not a number. There are other ways to obtain this value, but in all cases it means that the result is somehow undefined. It also has kind of natural behavior. For example, every operation with none will return a none, and any comparison except checking non-equality will return false. Although those values can be useful, you probably do not want inf or none appearing in your output, as the answer is usually a regular number. So if you see inf or none, it usually means that you have a bug somewhere. And the most dangerous are bugs where a regular value turns to inf or none because of errors. For example, square root of a negative value is always a none, even if that value is close to 0. So if your actual value is 0 and you store -1 billionth instead because of errors, square root of -1 billionth is a none. So in fact, to avoid this, you could just write, instead of square root of x, write square root of maximum of x and 0. And as you probably wasn't going to extract the square root of a negative number, the only change will be in that very case, when, because of errors, extracting square root of 0 becomes not a number. So let's summarize what we learned about floating-point numbers. First of all, with doubles, there are always errors. So you can only expect that your stored value is not far from the actual, but never that they are exactly equal. Because of that, you should always use integers where possible. But you need to watch for overflow. If you decide to use doubles though, any comparison you made should admit an error of epsilon. And in particular, you should never use the equality operator with doubles. Try to minimize errors, for example, by reordering computations, and avoid to odd values of different magnitude. Also, avoid inf and none in your output. If they are, you most likely have a bug. And that would be all about floating-point numbers. So, see you in the next lesson.
In this lesson, we will touch on the very important topic for all programmers: how to get your code to work. We'll take a closer look at the situation in which you thoroughly studied your code, but you still don't understand what is wrong with it. We will also learn to spend less time looking for bugs. Except for thinking over the idea of a solution, there are two standard and simplest ways of finding bugs in your code: critical observation and testing and debugging. Competitive programmers use both of them at full power. Probably you know advanced testing and debugging technologies, but during the contest there is usually no time to use them. And it's a cool skill to be able to manage small resources in most situations and resort to powerful instruments only in truly difficult situations. But what if the usual application of these techniques doesn't lead to success? For example, you run the program in debug mode on several tests, and either the program works, or it doesn't work from time to time, or doesn't work at all, but the program is so big that you can't understand where the bug exactly is. At the contest, all these cases are rather stressful and critical. Therefore, it is important to be able to deal with them. Let's revisit the task that we considered in the structuring code lesson. In this task, we wanted to compute the number of people in the list that are employed at this moment and compute the sum of all ages of all people in the same list. We saw an example of well-structured code, in which the actions were performed in the following sequence. We initialized all variables, read the array of people, computed the number of employed people, computed the sum of all ages, and finally printed all answers. Suppose that your code doesn't work, and you found a test on which, in your opinion, the sum of ages is computed incorrectly. This is already a small victory, because if you just send your code to the testing system and see the verdict wrong answer, then you do not know what exactly is wrong. In this case, you can say that you need to consider the countSumAges function in detail. Such conclusions severely narrow the space where bugs can be, but only well-structured code can give such advantages. Now, you have only one function for debugging. Consider the general situation and name it f. Is it easy to debug only f? You can act as usual. successfully examine all lines of f, certainly you can start a debugger and watch what f does with the data. You can also display auxiliary intermediate data. At some point, there happens a contradiction with your expectations. You become convinced that the code is incorrect and fix it. This is the most common scenario. But imagine that there are another functions before f, and they may contain bugs too. In our example, initData, readData, and countEmployed can play the role of such functions. Let's assume that there are bugs in the readData function. In general, let there be some buggy functions before function f. Name it g. Note that if g affects data which f uses, we will only see the incorrect result of the function f, and we will not even think that something is wrong with g. In our example, function that computed the sum of all ages could be absolutely correct. But if the data is read incorrectly, our function doesn't stand a chance of giving the expected results. If we are debugging our function just by looking at its code, it will be difficult to get out of this trap. If we use a debugger or if we log some intermediate data, it will be easier to notice something wrong and switch to other functions. Actually, this is what sometimes happens during the contest. Such a situation can be avoided if we completely isolate the function we are interested in. For example, we can write a separate function for debugging. That's how it can look. Consider the function debug some ages. At first, we carefully set or read test data on which our algorithm doesn't work. Note that this data should be in the form in which the considered function must see it, as if all the code before this function had already worked correctly. Then we call the suspicious function and print its result and maybe other useful information. So now, to test the countSomeAges function, we can just call the debugSomeAges function. If even after this the result is incorrect, our suspicious function is buggy with huge probability, because now all other code doesn't get a chance of spoiling anything. In this video, we will talk about simplifying code. Most often, when we try to solve a task, we want to come up with at least something. Until we have no solutions, we try to find any of them, and the first solution we came up with is not always the simplest one. That's why it is always worth to think if your solution can be simplified. But at some point, you stop thinking about the solution and start thinking about its code and writing it. And certainly, the very first code you wrote is not always the easiest and the clearest one. If your code works and passes all tests, all these thoughts doesn't matter, and you should think about other tasks. But if not, returning to thoughts about simplifying is a good idea. Consider a simple example. Suppose that in some task, your goals are to do something with some integer numbers. For example, sum up or print. And you thought about the task in this way. I am interested in several numbers, so a loop is needed here. I don't need numbers that are not less than 10, so I can stop when I see 10. I should skip numbers that are less than 5. By this, I illustrate a consistent approach to solving the task. You gradually understand what is required in this task and come to the solution. This logic is acceptable. However, when you understand the whole solution, you can make it and its code simpler. In our example, you can write a usual for loop. Both codes do the same, but it's easier to analyze and debug the second code. So we see that the same idea can be implemented in different ways. It is important not to tie yourself to an already written code, but change the structure of code when it is reasonable. In our example, we didn't change the idea of the code. Now imagine that you are in another situation. one of your function doesn't work and it is hard to debug it. But at the same time, you know that you can fully rewrite this function and it will become clearer. So, why not do it? Competitive programmers sometimes rewrite all solution because they realize that they are totally stuck in it. Thus, we exploit a simple truth. Deleting all code removes all bugs in it. You may find it strange, but the shortest code is not necessarily the clearest code. Consider a simple task. There are n floors in the house. There are n apartments on each floor. 2 of them are corner apartments, other n-2 apartments are usual apartments. There are 3 windows in each corner apartment and 2 windows in each of the other apartments. Your goal is to compute the total number of windows in the house. So, in this task, it is required to find only one formula. You can come up with the following formula: n, number of floors, by n-2, number of usual apartments on each floor, by 2, number of windows, plus 2, number of corner apartments on each floor, by 3, number of windows. This formula obviously gives the correct answer. But we can also remove all parentheses and simplify this formula. Then we get 2 by square of n plus 2 by n. The new formula looks more compact. However, when we see the first formula in the code, it is easier to understand where it came from and why does it look like this. But every time you see the second formula in the code, you need to remember where it came from and convince yourself that it is correct. So here, we've gained at the length, but lost at the understanding, which is far more important. Let's look at the idea of simplification on the other hand. No task has a unique solution. Every problem can be solved in different ways. Solutions can have different advantages. Some of them are faster, some of them are simpler. In fact, it can be difficult to find a solution that fits in the time limit but is not incredibly complex. You always need to look for a balance. But now, we consider a situation in which only one solution fits in the time limit. Imagine that in some task, you need to sort an array of size n, for example, an array of integers. And you know 2 algorithms that can sort an array. First algorithm, name it fast sort, performs big O of n log n operations, but is hard to implement. Second algorithm, name it easy sort, performs big O of n squared operations, but is very simple. An example of the first algorithm is quicksort. An example of the second algorithm is bubble sort. Suppose that only fast sort fits in the time limit. For example, if n equals 1 million, fast sort finishes working in a reasonable time, but easy sort works very long. So you used fast sort, but your code doesn't work. Like before, assume that you have got a test on which your code gives the wrong answer. And you don't know, should you look for bugs in the sorting algorithm or in other places? To understand this, you can replace fast sort with easy sort. Since these algorithms do the same thing, nothing more is needed to change. If your code still doesn't work after this, it means that you should find bugs in other parts of code. If your code works, it means that your implementation of the hard algorithm was incorrect. Even if such replacing didn't help to find bugs, you can debug simplified code instead of rollbacking changes. Probably it will be more comfortable. But don't forget to replace easy sort with fast sort after debugging. A possible pitfall here is that you can accidentally write code of easy algorithm incorrectly. It can be very confusing for you because you can start looking for bugs in the hard algorithm that might not be there. So you should be very careful with simplifying in this case. By the way, the same idea is used for stress testing. We will cover it later in the course. You may also notice that brute force algorithms can almost always play the role of simpler algorithm. But remember that sometimes brute forces are very hard to implement, and in such cases you shouldn't use them. Until now, we learned to check our code ourselves. Let's talk about forcing the computer to do this work. But first, let's talk about invariants. In this course, we have already encountered loop invariants. Now we will generalize this concept. Invariant is a correct statement about data you are working with. You don't need to come up with invariants specially. They always arise naturally. As a loop invariant, every invariant corresponds to some place in your code. Consider the first example. Here we have an array of integers. We simply iterate over it, and each time we find a negative element, we change its sign to the opposite sign. We also compute sum of all elements in an array after applying this operation. In the end, we print the sum. It is obvious that after the loop, every element in the array will be non-negative. That's why we can define the invariant, which you can see on the slide. Note that we can't put this invariant before the loop. Consider the second example. Here we also have an array of integers. All we do is reading it, sorting it, and printing it. Suppose that functions with appropriate names do this. And we have an obvious invariant after sorting. When the array is sorted, all elements in it are in non-decreasing order. So for every I from 0 to n minus 2, ith element of the array must be not greater than I plus 1th element of the array. It is reasonable to expect that in the working code all invariants must be satisfied. So we can check all of them, and if we find a non-satisfied invariant, we can conclude that there is a bug nearby this invariant. But checking invariants in two previous examples by hand is a big and unreasonable work. So let's entrust this work to a computer. There is one special function in each of the main programming languages. It is usually called assert. It takes an expression as an argument, computes it, and throws an error if its result is false. For example, the expression 2 is less than 3 is always true. So if we pass it to this function, it will do nothing. But the expression 2 plus 2 equals 5 is false. So passing it to this function leads to error. With asserts, we can automatically check any calculable expressions. So we can automatically check invariants. When we use asserts, our code is actually checked twice, by testing and by checking invariants. Now, a few words about Java. You can assume that in every language, an assert behaves like a conditional operator if a statement is not true through an exception. Certainly, we use asserts for simplicity, but in Java, asserts are checked only with the compilation key EA, that means enable assertions. You can use this key on your computer, but on the server, the compilation keys may be different. That's why on Java, it is recommended to use the mechanism of exceptions. Let's see how we can use asserts in our examples. In the first example, we expect that after the first loop, all elements will be non-negative. So we can iterate over all elements and check this assertion for every element. In the second example, we expect that after sorting, all elements will be in non-decreasing order. So we can iterate over all pairs of neighboring elements and check this assertion for them. As it was said earlier, if some assertion fails, it usually means that there is a bug in the code before this assertion. Consider a more complicated situation. You know that your code doesn't work. For example, you sent it to the testing system and received a verdict wrong answer. And you don't know any test on which your code works incorrectly. In this case, you can add assets to your code in the same way and just send it to the testing system. And if you see that your code crashes with a runtime error on some test, it can mean that some assertions have failed. You can find them one by one. Comment out all assets except the first, comment out all assets except the second, and so on. Unfortunately, returning an error doesn't always mean failing of assertion. There are a lot of cases in which an error can be returned. Array indexes out of bounds, division by zero, infinite recursion, and so on. So you should be careful with this method of finding bugs. Now, let's talk about absolving. Absolving is a word often found in competitive programming communities. It can be translated as solving tasks after the end of the contest. I will give an analogy from life of a usual programmer. Imagine that a programmer creates a project. This project has to be done in a week. The programmer can finish it completely, but there also can be some imperfections in it after finishing or missing functional. In the last case, the programmer can work with this project after the deadline and then release patches or new versions. But what about contests? Programming competitions are usually prepared in such a way that very few participants solve all problems. This is done so that programmers at all levels can find suitable tasks for themselves. That's why you even don't have time to read all tasks. But most likely, in each competition there is a task such that you have time to read it, but you can't solve it. Let's imagine that you didn't solve one of the tasks and figure out why this could happen. Firstly, you have just been solving other tasks, and this task ostensibly didn't exist for you. Generally speaking, it is best to always read all tasks. Otherwise, you can miss a task that is simple for you and maybe hard for others. There is even a strategy to read all tasks at the beginning of the contest. But in some contests, tasks are sorted by complexity, so it's not critical not to read last tasks. Secondly, the statement of the task could be incomprehensible for you. In such cases, it is worth to ask for clarification, or if you are completely stuck, you can move on to other tasks and then reread this task later. This is not the most interesting situation. And two last reasons. You understood the statement of this task, but didn't understand how to solve it. You came up with the solution of this task, but it either didn't work at all or it didn't pass all tests. In fact, you can learn a lot in these situations. For example, suppose that you don't have enough time to finish your correct solution. After the end of the contest, there is less motivation to finish your solution. The result of this contest will not change. But on the other hand, after the contest, you can calmly remember what problems did you have during the contest, pay attention to them, and successfully finish your code. You can do it without pressures of a contest, such as the constant feeling that your time is running out. Certainly, speed is very important on the contest, but after the contest, it means not so much. For example, if you had problems with implementation of known algorithm in the contest, you can think what exactly were the problems, think how to avoid them, finish your code. And most likely, the next time you will write the same algorithm faster. Now suppose that you didn't solve the problem because you didn't come up with a solution. Contest authors almost always post the editorial of their contest. There, you can find a detailed solution of each task. Even if the editorial is not detailed, you can always ask the authors questions about the solutions. But why do you need other people's solutions? Furthermore, why do you need them after the contest? Of course, it's useful to come up with ideas yourself. But some ideas can be so extraordinary that it can take a lot of time to figure them out independently. Therefore, if you can't come up with a solution for a long time, it is reasonable to read the editorial and learn new ideas. Generally speaking, all ideas in our world are repeated. It is rare to find something completely new. Therefore, the more ideas you know, the more tasks you can solve. Also, with the help of editorials, you can understand which algorithms are most often found in contests. If you learn these algorithms well, your results on contests will also improve. On the one hand, all the tasks that you see on contests are different. On the other hand, they are usually divided into groups of topics. Here are examples of such topics: strings, geometry, brute force, graphs, greedy algorithms, data structures, and so on. And it is a normal situation when you do well on some topics and do not so well on other topics. We all have strengths and weaknesses. When we participate in a lot of contests and absolve them, we understand our strong and weak points better. And, perhaps, weak points deserve even more attention. Consider the following point of view. If you could solve a task during the contest, it means that it was simple for you. You managed to solve it in a very limited time. That's why it isn't actually valuable for you. If you couldn't solve a task during a contest, it means that it is hard for you. So it is very valuable for you to try to solve it. And in this case, your level will definitely rise. For example, if tasks about strings are hard for you, you can search for more such tasks and solve them. And after some time, you will realize that your skills in solving these tasks have been improved. On the other hand, it doesn't make sense to find and solve a lot of tasks that are easy for you. In fact, there is a known rule. If you have drawbacks, they always find them out on interviews. So it's very useful to know about your weaknesses and work on them. Thus, absolving makes you really stronger. If you want to show good results in competitions and raise your level, absolving will lead you to success. To summarize this lesson, we have considered a lot of ways to get unstuck. It makes sense to analyze the code in parts, to simplify it, and to add assets in it. And if you spend really a lot of time on the task, it is worth to look for tasks of the same type and solve these tasks too.
Hello everybody, welcome back. In this video we're going to start studying greedy algorithms. So this is a natural class of algorithms. They build a solution piece by piece, and at each step they select the most profitable piece of a solution. Let's illustrate this strategy with two toy problems. The first one is the so-called largest number problem. The input to this problem consists of n integers, of n single-digit integers, d0, d1, and so on, dn minus 1. What we would like to do is to compose the largest possible number out of these digits. For example, for the input 23932, the largest number composable out of these digits is 93322, right? There is a natural idea for solving this problem. Of course, we would like to start our number with the largest possible digit. This is just because we know that all possible such numbers have the same length. So it is just natural to start with the largest possible digit. Okay, and what is left is essentially the same problem. So for our toy example, we would like to start with the number 9, and then what is left are digits 3, 3, 2, 2, and we would like then to arrange them somehow to get the largest possible number, right? And this leads us to the following code. So we're given a sequence of digits. We first declare the variable result, which is just an empty array in the beginning, and then we keep repeating the following. We select the largest digit, we remove it from the sequence of digits, and we append it to the list result. Right. Finally, in the last line of our code, we just join all our digits by empty spaces, and we get a string consisting of all the digits in the same order as in the list result. The running time of this code is n squared, just because there are at most n iterations of the while loop, and inside each iteration we need to find the maximum, which actually amounts to scanning the current list of digits. And again, it takes a linear amount of work. The next problem is a so-called miny change problem. In this case, we're given a non-negative integer m, so some amount of miny m. And what we would like to do is to change m with the least possible number of coins with denominations 1, 5, and 10. For example, for the input, when m is equal to 28, the result should be equal to 6. Indeed, 28 can be represented as 10 plus 10 plus 5 plus 1 plus 1 and plus 1, so 6 coins. Again, there is a natural greedy strategy for this problem, and it is actually used by cashiers all over the world. So to change the given amount m with the least number of coins, just keep repeating the following procedure. Just first take the coin with the largest denomination that does not exceed m. Then take this coin, subtract it from m, subtract its denomination from m, and repeat. Right? This gives us the following code. So in this code, the parameters taken to the procedure are m and the set of coins, the list of denominations of coins, and then we proceed as follows. First, we declare the variable result. This is just an empty array in the beginning. Then, while m is empty, we do the following. In the fifth line, we find the maximum denomination that does not exceed m. Then we subtract it from m, and we append this denomination to the result. And finally, we just join all these coins by the plus sign. So, for example, for the input 28, again, this procedure will return 10 plus 10 plus 5 plus 1 plus 1 plus 1. The running time of this procedure is m time coins. Times the size of coins, And the reason is simple. So there are at most m iterations, because at every iteration of the while loop we decrease m at least by 1. And at every iteration we need to find the maximum denomination of a coin, so we need to find a maximum in an array of size coins, right? So this is definitely can be done in time big O of coins. So now when we've seen two examples, let's analyze them. First of all, we know, we've seen that it gives us very compact solutions, and they are also efficient solutions, right? At the same time, it is more frequent in the sense that these two solutions actually work correctly in all cases. To see this, let me mention the following two interesting facts. So if instead of considering digits in our problem largest number, we consider arbitrary positive integers, then the corresponding algorithm might fail. For example, if we consider the input consisting of two numbers, 2 and 21, then our algorithm will first put 21 and then append 2, just because 21 is larger than 2. This will give us the number 212, 2. But this is a suboptimal result, because in this case it is much better to put 2 in the beginning and then to append 21 to the end, because this will give us a number 221 instead of 212, right? Similarly, if we consider other denominations of coins, for example, denominations 1, 4, and 6, our greedy algorithm might produce a suboptimal result, as illustrated by the following example. If we ask our greedy strategy to change 8, it will return 6 plus 1 plus 1, that is 3 coins, instead of just 2 coins, 4 plus 4. So, a priori, indeed, there should be no reason why just the naive greedy strategy produces an optimal solution. So it turns out that for our largest number problem and for greedy change with denominations 1, 5, and 10, the greedy strategy works correctly, but it is important to always prove the correctness of greedy algorithms. And this is exactly what we're going to do in the next video. In this video, we are going to show how to prove that a particular greedy algorithm works correctly. That is, it always returns an optimal solution. So recall that at every step, a greedy algorithm chooses the most profitable piece of a solution. So in a sense, what we're doing at this point is that we're restricting our search space. So for example, in the largest number, when we say let's start our number with the largest digit, we essentially say instead of considering all possible numbers composable of our digits, let's consider only those that start with the largest digit. In the money change problem, when we say let's take the largest coin, that does not exceed the given amount of money, we say instead of considering all possible ways of changing the given amount of money, let's consider only those that contain this largest coin. So essentially, to prove that such a greedy algorithm works correctly, what we need to show is that the restricted search space contains an optimum solution, right? In turn, to prove that the restricted search space contains an optimal solution, one might follow the following template or the following pattern. So start with some optimum solution. So if it belongs to the search space, then we are done. Then there is nothing to prove. If, on the other hand, it does not belong to the restricted search space, then what we need to do is to tweak it a little bit, so that it is still optimum, and at the same time it belongs to the restricted search space. Okay, let me illustrate this with proving the correctness of the two problems considered before. So formally, what we need to show for the largest number problem is the following. What we need to, in this case, the solution is actually unique because this is just the largest number. So we will prove that not just that there exists an optimum solution in the search space, but that the solution lies in the restricted search space. Namely, we will show that the largest number actually starts with the largest digit. And it is not difficult to show. So assume, for the contrary, that the largest number starts not with the largest digit, but with some other digit, dj. So dj is not the largest digit, and di, the largest digit, is somewhere in the middle of our largest number. Then just by swapping these two digits, of course, we get a larger number, which contradicts to the fact that our initial number was indeed the optimum one, right? Okay, so this was not difficult. Let's proceed to the money change problem. In this case, the statement is the following. For any positive integer m, there is an optimum way of changing m using a coin which is the largest coin that does not exceed m. Okay, so we prove it by considering a few cases. So first of all, if M, so let's denote the coin which, the largest coin out of 1, 5, and 10, which does not exceed M by D. So what we need to show is that there always exists an optimum way of changing M using a coin of denomination D. So now let's consider three cases. If M is smaller than 5, then D is equal to 1. So 1 is the largest denomination that does not exceed M in this case. So what we need to show is that there exists an optimum way of changing M using coin of denomination 1. But this is easy since M is at most 5, we can only use coins of denomination 1. So essentially there is nothing to prove in this case. The second case is when M is at least 5 and smaller than 10. So what we need to show is that there exists an optimum way of changing M using coins of using a coin of denomination 5. So in this case, we can only use coins of denominations 1 and 5. So if we do not use a coin of denomination 5, then all the coins should be of denomination 1. And since M is at least 5, there should be at least 5 such coins. And we can replace them by a coin of denomination 5, and we will improve the solution by doing this, right? And this shows that, of course, actually in any optimum way of changing M, in this case, there must be a coin of denomination 5. Finally, assume in the third case that M is at least 10. What we need to show is that there exists an optimum solution that contains a coin of denomination 10. This in turn can be shown by considering a few sub-cases. So first of all, consider some optimum solution. If it contains a coin of denomination 10, then we are done. There is nothing to prove. So assume that there is no coin of denomination 10. Then consider a few sub-cases. If it contains, for example, at least 2 coins of denomination 5, then we can replace them by 1 coin of denomination 10. This will improve the solution. If it contains just 1 coin of denomination 5, then it must contain at least 5 coins of denomination 1. Right? Just because M is at least 10. And we can replace all these coins with 1 coin of denomination 10. Finally, if there are no coins of denomination 10, of denomination 5, then there should be at least 10 coins of denomination 1. And all of them can be replaced with just a single coin with denomination 10. Okay? Which finally proves our lemma. Let me finally also mention that it is exactly the last step of this proof where it would break for denominations 1, 4, and 6. So recall that for such denominations, the greedy algorithm actually does not work because it will change the amount 8 with coins 6, 1, and 1, while the optimum way of changing this is by using just 2 coins of denomination 4. The next problem we're going to solve is called the activity selection problem. In this case, the input consists of several segments on a line. And what we would like to find in this case is the maximum subset, the maximum size subset of them, such that no 2 of the selected segments overlap. So the real-life application of this problem is the following. Imagine that we have a meeting room and we have several groups of people that would like to organize a meeting in this room. So for each meeting, we know its start time and its end time. And we would like to satisfy as many such requests as possible with a natural constraints. So 2 meetings cannot overlap. So 2 time intervals should not overlap. Okay, so let's consider an example. So assume that we're given 4 segments, from 2 to 6, from 1 to 4, from 7 to 9, and from 3 to 8. So in this case, the maximum number of non-overlapping segments that we can select out of these 4 segments is equal to 2. For example, we can select the second segment and the third one. it is not difficult to check that they do not overlap. Let me also show you another example. So in this case, we are given 11 segments. So they are all segments on a line, but we show them at different heights just so that they do not overlap. Okay, so out of these 11 segments, it is possible to select 5 non-overlapping segments that are shown here in red, and we will soon convince ourselves that it is indeed the optimum way. Okay, so unlike the previous two problems, the previous two problems that we considered, namely the largest number problem and the money change problem, in this case, it is not even straightforward. What is a greedy strategy? Right? But let's just try to guess. For example, one might want to take the shorter segment into a solution, just with the hope that a shorter segment has as few conflicts with other segments as possible. Or on the other hand, we might also want to take the segment with the minimum left endpoint. I mean, the meeting that starts as early as possible. Another guess is probably we should take first the segment with the smallest right endpoint. That is like the meeting that ends as early as possible. So it turns out that the first two strategies do not work in this case. So let me give you a counterexample for the first strategy. So let me remind you, the first strategy is that we should first take shorter segments. So consider this small data set consisting of just 3 segments. So if we take the shortest segment into our solution, in this particular case, this is a middle segment, this will not allow us to take any other segment because the shorter one here intersect any other segment, right? So if we take the middle one, we get a solution of size 1. At the same time, it is not difficult to see that there is a solution in this case consisting of 2 segments, the top one and the bottom one. Okay, so in this case, the shortest segment intersects all other segments. So it actually doesn't make any sense to take it into our solution. As for the second strategy, which suggests us to take a segment with the smallest left endpoint, consider the following counterexample. So the top segment here has the smallest left endpoint, right? And if we take it into our solution, we will lose the possibility to take any other segment into a solution, right? So if we take the top segment into a solution, we get a solution of size 1. And again, it is a suboptimal solution in this case, just because we can take into a solution 2 other segments, okay? So as you might probably guess already, the third greedy strategy actually works. So let's just prove it formally. So what we're going to prove is that there exists an optimal solution that contains a segment with the minimum right endpoint. In other words, so if we just take it into our solution, then we can still extend it into an optimal solution. Okay? So let's prove it formally. Let's denote by AB the segment with the minimum right endpoint and consider some optimum solution S, and assume that CD is the segment from this solution S with its minimum right endpoint. So CD is the segment from S whose right point is minimum. Okay? So we would like, first of all, there is a case when AB coincides with CD. So in this case, there is nothing to prove, right? So assume, there is even a more general case. So if D is equal to B, then this means that CD is also a segment whose right endpoint is minimal. And in this case, there is nothing to prove. So assume that D is actually greater than B. So what we need to show is that there still exists some other optimal solution that includes, for example, the segment AB. Okay, and you might probably already guessed what we're going to do. So let's just remove the segment CD from S, and let's instead add the segment AB into our solution. So in other words, let's replace the segment CD with the segment AB. Okay, so what I claim is that, first of all, the size of the resulting solution is the same as the size of S, right? Because we just replaced one segment. What I would like to also claim is that it is still a solution, is that the new segment AB does not overlap any other segment. So why is that? This is just because CD does not overlap any other segment in S. And for this reason, AB also does not overlap. So why is that? Well, AB lies, B is smaller than D, right? So this means that AB, in a sense, lies to the left of the point D. On the other hand, all other segments in the solution S, they lie to the right from D. This is just because CD does not overlap any other segment. So if CD does not overlap any other segment in S, then for sure AB also does not overlap any other segment, which actually proves that there is an optimum solution that contains a segment AB whose right point is minimum. Okay, let me also illustrate the last part of this proof visually. So consider this data set, and now consider two highlighted segments. The first one, the red one, is from our current solution of size 5, and the blue one is the initial segment whose right point is minimum, that does not belong to the current optimum solution. So what you see here is that if you swap these two segments, I mean, if you include the blue segment into our solution, and if you exclude the red one, then the resulting solution is still a solution, and its size is still 5, right? So replacing this red segment with a blue segment cannot introduce any conflicts. Okay. Now let me briefly mention how to implement this idea. Well, this can be done in a straightforward fashion. So we know that there exists an optimal solution containing the segment with the smallest right endpoint. So we just scan our n segments, we find a segment with the smallest right endpoint, we then include it into our solution, and then we scan the whole list of segments once again and remove all the segments that are intersected by the current segment. Okay, and we repeat this procedure while the current set of segments is non-empty. This gives us an algorithm with a quadratic running time. Why is that? Well, just because we need to repeat this procedure n times, and at each iteration we need two scans. First to find the minimum right endpoint, and then to remove all the segments that are intersected by the current segment. Let's now consider the maximum scalar product. In this case, we're given two sequences of integers of the same length, namely the sequence A of length n and the sequence B of length n. What we would like to do is to find a permutation of the second sequence so that the scalar product of A with this permutation is as large as possible. So the scalar product of sequences A0, A1, and so on, A(n-1), and the sequence C0, C1, and so on, Cn-1, is defined as just the sum of products A0, C0, A1, C1, and so on, An-1, Cn-1. So put it otherwise, what we would like to do is to pair each element of A with each element of B, with an element of B, such that the sum of the product of pairs is as large as possible. For example, if we're given two sequences, 2, 3, 9, and 7, 4, 2, then the optimum number that we can get in this case is equal to 79. This can be revealed by the following scalar product. So we pair 2, the element of the first sequence with 2, the element of the second sequence. Then we pair the element 3 with the element 4, and finally the element 7 with the element 9, with the element 7. Okay, so the result is 79, and we will soon find a way of finding this particular solution. So the greedy strategy in this case is again quite natural. So the idea is to pair the largest element of the sequence A with the largest element of the sequence B. So if we prove that this indeed leads to an optimum solution, then we can do the following: select just the maximum value of A, select the maximum value of B, pair them, remove them from A and B, and repeat. Okay. Now let's prove that there always exists a solution where the maximum element of A, we denote it by AI, is paired with the maximum element of B. We denote it by Bj. Okay, so for this, consider some optimum solution. Okay, so first of all, if it pairs AI and Bj, then we are done. So we know that there exists an optimal solution which pairs these two particular numbers. So now assume that it pairs AI with some different element of B. So assume that S looks as follows. It is AI times BP plus AQ times BG. So AI is paired with BP and AQ is paired with BG. What we need to prove is that there still exists some optimum solution, some other optimum solution which pairs AI with BJ. So when there is a natural tweak in this case, let's just swap these two pairs. So instead of S, let's consider a solution S prime, which looks almost the same as S, with the only difference. Instead of using AI BP and AQ BG, it uses the following two pairs, AI BG and AQ BP. So again, we just swap these two pairs. Instead of pairing these two guys, we pair these two guys. Okay, so what we need to show now is that S prime is not worse than S. And for this, we just subtract the value of S from the value of S prime. So since these two solutions are almost the same, what is left are only these four products. So it is AI BJ plus AQ BP minus AI BP minus AQ BJ. Then it is not difficult to see that it can be rewritten as follows. It is equal to AI minus AQ times BJ minus BP. And this is in turn non-negative for a simple reason. So we know that AI is the largest element of A, which means that AI is at least AQ. Just for exactly the same reason, Bj is the largest number of B. So which means that Bj is greater than BP, is at least BP. So this is a product of two non-negative numbers, so this is non-negative, which finally proves that this gives us an optimum solution which pairs AI and Bj. Okay? So then what remains to be done is to convert it into an algorithm, and we've already discussed the algorithm actually. So what you see here is a simple Python code. So we first check whether the lengths of the given two sequences A and B are equal. We then declare the variable and initialize it with 0, and then while the length of A is while there are some remaining elements in A, we repeat the following step. We find two maximum elements in A and B. We denote them by AM and BM. Then we add their product to the result, and then we remove these two elements from A and B. Finally, when there are no elements left in A, we return the result. Okay, so the running time of this algorithm is quadratic, that is big O of n squared, for a simple reason. So at most, there are exactly n iterations of the while loop, and inside every iteration, what we need to do is to find the maximum, to find two maximums actually, and to remove two elements. And all these operations can be done just by a simple linear scan in a linear amount of work. let us now summarize. So as we've seen, in many cases, a greedy algorithm defines some greedy ordering in a natural sense. So for example, in the largest number, what we've discovered is that that it makes sense to first take larger digits, right? In the money change, again, we realized that it makes sense to first take larger coins. In the activity selection, we've proved actually that the activity or the segment with the minimum right endpoint is better in a sense, right? And in the scalar product, in a sense, what we've also shown is that the element of B, for the element of B, the larger it is, the better, right? And in many cases, such a strategy can be also converted to a sorting algorithm which sorts with respect to some implicit ordering that we have implicitly in our solution. So let me show you more compact solutions, more compact code for the three problems considered previously. In the largest number problem, what we essentially would like to do is to arrange our digits in non-increasing order. Right? So, and this can be done just with one line of code. So, given a sequence of digits, we first sort them. So here we use the flag reverse in order to sort them not in the non-decreasing order, but in non-increasing order, and then we just concatenate all these digits. Right? For the money change problem, what we would like to do is to first, in a sense, go in the decreasing order of denominations. So we first would like to take as many coins with denomination 10, then as many coins of denomination 5, as many as possible, and finally as many coins as needed of denomination 1. And this can be even done without sorting or without any loops, because it is easy to compute the number of coins of denomination 10 that needs to be taken. This is just m divided by 10. Right? More precisely, the integral part of this. So we just divide m by 10, and this is the number of coins of denomination 10. Then what is left is the remainder of m divided by 10. If we divide this by 5, this will give us the number of coins of denomination 5 that is needed. And this is actually always either 0 or 1. And finally, if we take the remainder of m divided by 5, this will give us the number of coins of denomination 1 that are needed in our optimum solution. Okay. Finally, in the maximum scalar product problem, what we've proved actually is that we need to multiply the largest element of A with the largest element of B. Right? And what is left is essentially the same problems. And we would like to multiply the second largest element of A with the second largest element of B. And this gives rise to the following solution. Let's just sort both sequences A and B and then multiply them pointwise. So multiply the first element of the sorted A with the first element of the sorted B, the second element of A with the second element of B, and so on. And again, this can be done just with a few lines of code. For the activity selection problem, we can do the following. We first sort all our segments by their right endpoints. This gives us a sorted sequence of segments. Then we scan it from left to right, and we keep repeating the following procedure. We take the current segment into our solution, and then we scan the sequence from left to right and remove all the segments that are intersected by the current segment. After we removed all the segments, we continue doing the same thing. We take the current segment into our solution, and we scan the sequence to remove all the segments that are intersected, and so on. So we have such an ordering in mind, and usually what is also important for such an ordering is that it is transitive. Then usually to prove that such an ordering gives a correct greedy algorithm, what we need to prove is the following. If we have some permutation of our objects and some two objects actually violate the ordering, so we have an ordering which is specified by binary relation at most, and if some element in our sequence is greater than the next element, then if we swap these two elements, that we can only improve our solution. So once again, in many cases when we have such an ordering at most and it is transitive, it is enough just to sort the given objects with respect to this ordering. Okay? Finally, let me summarize what we've learned in this lesson. So a greedy strategy usually constructs a solution piece by piece, and at each iteration it just naively selects the most profitable piece of advice. So in many cases this leads to very efficient and compact solutions. This is an advantage of a greedy strategy. The main disadvantage is that this strategy actually rarely works. What is worse is that there are optimizational problems for which greedy solutions seems to be natural and correct, but they are not correct in fact. So remember to always prove the correctness of your greedy approach.
Hi, my name is Andrei Lopatin and I am ACM ICPC coach at St. Petersburg State University. Our today's topic is about range sum query. Range sum query task is about finding some segment of an array. So the easiest case, if the array is constant, it can be easily done just like calculating so-called prefix sums, which are sums on the prefixes, as you can see from its name. When you need to sum of some segment, you find the corresponding prefixes and just calculate the difference between two values of the prefix sums. But the harder case, if it's when the array is modified dynamically. So you need a more complex data structure. It's called a segment tree, and the very popular way to solve the range sum query problem is by using a segment tree. The segment tree also precalculates sums on some segments, but the segments are not just prefixes. It can be some other segments which are selected by some formula. The powers of 2 play an important role in building a segment tree. So at first, the easiest way is to expand our array to such that its length will be also a power of 2. So just pad it with the zeros from the right side. So let's assume the length is some power of 2. The whole segment is divided by 2 parts. Each part is divided also by 2 parts, and so on. And because we selected the length of array is a power of 2, the process will terminate with n segments of length 1. So in fact, there's just one element segment. It's just an element of the original array. You can see the segment tree is represented on a picture. This picture shows the tree. Its root is on the upper side, and the leaves are on the bottom side of the picture. The segment tree is also stored in an array. This is a larger array, which size is double of the original array. You can use 0-based or 1-based array because the cell number 0 will be not used. The cell number 1 will store the root of the tree, which corresponds to the whole original array. And the children of some node will be easily evaluated because it's number multiplied by 2 and the number multiplied by 2 plus 1. Sum of a segment corresponding to a cell can be easily calculated by summing the numbers of its children. One can easily deduce formulae which specify the left and right boundary of a segment, but in fact they are not so often used. But you can see that each segment has a length of some power of 2. And in fact, in real code, somebody uses a dynamic evaluation of boundaries, just recalculating if one going downwards or upwards on a tree. Now we will discuss how to calculate a sum on a segment. You store some segments in the segment tree, but not every segment. So if you have some different segment as a query, you need to partition this segment to segments which are stored in segment tree. As you know, they all have a length of power of 2 and starts in a cell which is some multiple of this power of 2. There are two ways, in fact, you can go upwards on a tree or downwards. Going upwards is the fastest way, but it's less universal. Some operations are harder to implement, but for basic operations, both ways are okay. Let's consider some query, and you can just easily move this query into the tree because the leaves of the tree are stored in successive cells and they represent just an original array. You can just add the lengths of the original array to the positions of the query. Now the new task is to calculate the sum inside the tree. How to solve this task? This task is solved, as I said, we'll go upwards and we will just need to reformulate the task so you can move just one level up. Now we will solve the task inside the tree. So the left and right boundaries, there are some easy cases when the left boundary is larger than right boundary. There's just an empty sum which is obviously equal to 0, and if the boundaries are equal, the sum is just one element of the tree, which is obviously the answer. The general case is the case when there are at least 2 elements, and let's look at the left boundary. There are just 2 cases which the left boundary can be odd or even. If it is even, the next cell is just another child of the same parent. So we can start and in the level up and just divide the number of left cell by 2 and move level up. But if it's not even, it can be odd. Just accumulate the value of this cell to some variable s, and then just increment the left boundary, so we can always be in the case when the left boundary is represented by an even number. The same can be done with the right boundary. If right boundary is even, we can make it odd just by accumulating its value to the variable s and then decrementing its value. So when the L is even and R is odd, just divide them by 2 and we move one level up, and the segment inside the tree is exactly the same segment. It is exactly the same segment of the original array you had and the one level down. When the process is terminated, it is terminated when there are 1 or 0 elements. You will have the answer to the query in the variable s. The complexity of this algorithm is obviously logarithmic, because there is a logarithmic number of levels. If we consider the size of the array as n, the k is a binary logarithm of n. You can prove that the case of one element is unnecessary you can just terminate when L becomes greater than R. So you can see the code. The code is very simple. It's just one while loop. Inside you just modify the variables L and R in the way we described. So maybe the picture also can easily illustrate this process to you. Calculating the sum downwards is more universal way, because when you go downward the tree, all functions look very same, they are almost the same. So let's consider a query, and we will solve the task at some node V, and we will support its boundaries. So the original task is finding the intersection of the query with the segment which is described by the node, and you just take the elements which lie in this intersection and sum those elements, and this is the answer. So the original task is about doing this at node 1 at the root of the tree, and then we will descend this tree, and the number of nodes will be maybe some other value. We need to go one level down, and what are the easy cases? The first easy case is when this intersection is empty. It's just a few simple conditions you can check and then return 0, because the sum is obviously 0. Another case is that the segment represented by a tree cell is contained in the original query segment. In this case, you just return the value stored in the tree cell. The general case is that neither the empty intersection, neither the cell is contained in the queries. There is some non-empty intersection, but it's not the whole cell. So just divide this cell by 2, because the segment tree is arranged such way that each cell is divided by 2, and then solve the task for each cell which is a child of the cell we had. So it is also a logarithmic algorithm, because there are no more than 2 segments of each 3 kinds on each level, because there are no more than 2 empty intersections, no more than 2 intersections that is completely in the cell of a tree on this level, and no more than 2 general cases. You can easily prove this. You can look at the code. The code is also very simple, but slightly larger, because we need some variables to modify. And you can also look at the picture, which illustrates the process of descending the tree. The segment tree is designed not only to answer some queries or some other queries, but it also allows you to modify the value of some cell also in logarithmic time. To modify the cell, you need to modify all segments inside the tree that contains this cell. The easiest case is just to add some value to a cell. You need just to find the path in the tree that contains the cell, and then add the value to all the segments in this path. Also, you can just assign a value to some cell. It's a little bit harder, but you can solve this task by calculating the difference of the new value and the old value, and then you have the task you can easily solve, just the task of adding some value to a cell. You can also use the 2 ways of traversing the tree. You can go upwards and downwards. To modify an element upwards, you start from the leaf and then continue to the root just by going one level up. You can look in the code. You can see in this code we modify the value to a cell. We're adding the value of p and then just dividing the number of cell by 2. You always must stop after processing the root. It's the cell number 1, and when you divide 1 by 2 you get 0 and the while loop stops. You can look also at the picture. Here you can see the path you modified, and then there is another way to modify an element. You can go downwards. It's almost the same as if you calculate the sum. The recursive function is almost the same, but you need to pass the value of p, or also you need to pass the value of p, and for each passing cell you must add the value of p to the contents of this cell. Also, there is a more general method. You can add the value or maybe assign the value only if the tree segment is fully covered by the query. In this case, the query is just a segment of length 1, so it can be only in the leaf cell. And for other cells, you just need to recalculate the sum in the cell just by adding the values of to its children. You can look at the code. The code illustrates the assignment function. Here the value of q is passed, and you can see the second case of fully covered segment. Here is just an assignment, and for other cells on the path, you just sum 2 children, and the tree is processed correctly. You can look at the picture. You can see the assignment is done in the leaf cell, and then you just adding the value of 2 cells and modifying the parent cell. So we consider it a segment tree and its basic operations. So we can now modify an element and calculate the sum on any segment of the array in just a logarithmic time. You know there are 2 ways of traversing the tree. You can go upwards and downwards. Also remember that you need the tree only if you have modification operations, otherwise the prefix sum are better, obviously. And there is a very useful exercise. You can not only calculate the sum on a segment, but you can use it for some other functions such as minimum and maximum, and maybe some other ones. So good luck in using segment trees in your everyday life.
Hi! In competitive programming, it's crucial not to only invent a solution, but to also implement it. And that is done in a programming language. So, in this lesson, we'll identify the most helpful language features so you could study them more closely. We'll also learn specific features and pitfalls of C++, Java, and Python so you won't be caught. And we'll see what advantages and disadvantages different languages have so you could choose one of them. In this video, we'll start with the common language tools. To excel in competitive programming, you should really learn how to operate with them in your language. First, we'll cover standard data structures. The most basic is an array, which is just a fixed-sized sequence of values. With an array, we could set or take an element by its syntax. That's basically the only thing we could do, but it's quite useful. And the cool thing is, addressing an element is really fast, because an array is just a sequence of values in memory. The natural improvement of arrays are dynamic arrays. They are also called vectors or lists. With them, you could do all the same as like the usual array. But you also could change its size. So it's quite useful when you don't know how many values you need to store beforehand. And you also could just append values one by one at the end of the dynamic array. However, that's not for free. A dynamic array takes up about twice as much space as the usual array of the same size. And the usual array takes about the sum of spaces of all elements in an array. Another useful structure is a string. It's in fact just an array of characters and some specific operations implemented for it, so you don't have to write them yourself. The most basic operations just move around string parts. For example, concatenate two strings, extract a substring from a string, or find a given substring in a string. Another kind, those which treat whitespace characters. The most useful just splits a string by whitespaces, like a sentence in a list of words. Another one trims whitespaces from the end of a string, if they was stuck by reading. It's often useful to convert a number to its decimal representation, a string with digits characters, and vice versa, from a string to obtain an integer, which is written as a string by digits. There is also a powerful tool of regular expressions. You could not just search for a given substring, but rather search for a match for a given pattern. Although they are not frequently used on competitions, but sometimes they help in some hard implementation problems. Next, there are other structures built on top of arrays. A bit set is just a sequence of bits. But if you take an array of Boolean variables, each variable will take 1 byte, because one Boolean variable takes 1 byte. But in a bit set, each bit takes exactly 1 bit. So that's 8 times less memory. That's because a bit set is in fact an array of integers, each consisting of several bits, and all those bits are enumerated as if those integers were concatenated in a single long line of bits. And the useful thing is that it not just takes less space, you could also do operations on the whole bit set faster. For example, ending 2 bit sets or counting ones in a 1 bit set, just in about n over 32 operations with integers. If values do not fit in standard data types, it's nice to have big integers, which could have arbitrary size. And in fact, they work similar to bit sets, because a long integer is just a sequence of bits. There are also arbitrary precision floating point numbers, and then just in fact big integers shifted by some power of 2. In problems, often arises the queue structure, where you put new elements to the back and take away elements from the front. Of course, it could be implemented by arrays, but it's good enough to have the structure already implemented in the language, to make the code simpler and easier to understand. If you take away elements and put elements both from the front, it builds a stack structure. It's also useful. For example, the active function calls form a stack. And if you allow to put and take elements from both ends, it will be a DAG, standing for a double-ended queue. It's more powerful than both stack and queue, and so in fact, stack and queue are implemented through DAG in languages usually. So, we've covered simple array-like data structures. In fact, it will be enough for most of the problems. But there are more complicated ones, and we'll cover them in the next video. We'll also cover input and output. Now, to where the language really saves a lot of work. Let's consider a set structure. It's a very natural mathematical concept, and it could do 2 operations fast. First, insert an element, and second, check if some value is contained in the set. Of course, you could also append new values to dynamic arrays, but there is no way to quickly check if some value is contained. only iterating through all elements of the array. There is an extension, another set, which also stores values in increasing order and allows binary search for a value. For example, a query like find the greatest element in a set, which is less than 1 billion. The set without the structure is called unordered set. In fact, ordered and unordered sets are implemented in completely different ways. Unordered set is internally a hash table and also called a hash set. So the operations take constant time, and if you want to use the hash set for custom class, you need to implement a hash of functions for this class. An ordered set is internally a binary search tree. So the operation takes logarithmic time, and to use set with object of the custom class, you need to implement a comparator for this class. Although the big bounds differ, in practice, unordered set is like at most 2 times slower than unordered set, because the constant under the big O of unordered set is much larger. But both are internally quite involved, and so operations with them are much slower than operations with usual arrays. But of course, usual arrays could not do specific operations fast. Another, actually very similar structure is a map, or it's also called a dict for a dictionary. In usual arrays, you could look up values by their keys, which are non-negative integers, not smaller than the array size. And in map, you could look up values by any key. So it could be any data type, a string or large numbers or anything. And the space of the map will be proportional to the number of elements in it. In fact, from inside, a map is just a set of keys to which the corresponding values are attached. So maps here inherit properties that sets have. In particular, there are unordered maps, also called hash maps, and ordered maps, also called tree maps. The first are slightly faster, and the second allow to binary search for a key. But both are much slower than usual arrays. So in fact, the bottom line about sets and maps is use them only if they could make a solution like really faster. For example, asymptotically from big O of n squared to big O of n log n. And if not, then just use usual arrays, because operations with them are much faster. Aside from structures, there are also useful algorithms available in languages. Probably the most important are fast sorting algorithms. They sort a sequence of values in big O of n log n time. There are different algorithms: quicksort, merge sort, and so on. Different algorithms differ not only by performance, but also by stability, whether they preserve their order on equal elements. With standard types, it's not that useful notion. If elements differ, then they are not equal. But with custom classes, where objects get compared by several fields, elements equal in terms of sorting could actually be distinct. For sorting elements, you also need to implement a comparator if you sort objects of custom class. Another useful thing are various implementations of binary search. They typically allow to search for a value in a sorted array in time big O of log n. Next, there are random number generators. They usually work as follows. There is a special function that sets the seed, and by default the seed is either 0 or system time. And then next random numbers are generated by using that seed. And so if seeds are equal, then the sequence of random numbers is identical, and that is useful for debugging. There are also some useful functions like return some random number from a segment or randomly shuffle a sequence. Another important language feature are input-output tools. In problems, it might be useful not only to read integers or strings, but also the following operations. Read from file until the end of it. when no input size is given. Read whole lines. Keep formatting in white space characters. Do a formatted output, like print integers, and if they are too small, append zeros or spaces to the beginning of them. Print floating point numbers in a format, like with fixed number of digits after the point. With input and output, there is also an issue of performance. The input-output operations are rather slow compared to other operations like summing integers, for example. And some ways to do input-output are super slow, so you need how to do it efficiently. The main issue is individual operations in files are very slow. So it's not a good idea to write to a file each time you want to print a number. Instead, fast implementations use buffers, temporary array of characters. And when you print something, it just gets appended to that array. And only when this array is large enough, it gets written to the file and cleared. Buffered input-output is excellent in terms of performance, but sometimes you do need to make the operation right away. For example, in interactive problems or when debugging, because it's maybe confusing to view the output happen not where it's actually done. And so there is a special command which just writes the buffer right away. It's called flush, and of course, the more flushes you do, the slower it gets. So that's all for the command tools. In the following 3 videos, we'll discuss specifics of C++, Java, and Python. Be sure to watch the one for your language, as it's very important to know the specific pitfalls. You must also watch others to get a wider picture. In this video, we'll talk about specifics of C++ language. First, about strings. There are in fact 2 completely separate sets of tools for dealing with strings in C++. The first comes from plain C, and here strings are just literary array of characters. In a second, string is a separate class which behaves like vector of chars and has some specific operations. The first difference is arrays of char have always fixed size, whereas objects of string class could have their size expanded as needed. And another more cosmetic difference is that in CWay, operations are implemented through functions, like strcat for concatenating strings or strcmp for comparing them. And with strings, operations are usually implemented as member functions. So, due to the low-level nature of array of chars, the CWay is usually slightly faster than C++ way. But C++ way turns out to be more convenient. And so, on competitions, people usually use strings. But if you want maximum performance, you could use CWay arrays of characters. Next, we'll cover how to do input and output. There are also 2 largely independent frameworks for it, plain C and C++. In plain C way, all is done by functions. The most important are scanf for formatted input and printf for formatting output. The good thing is they're actually really fast. And the templates in scanf and printf are very powerful in treating different situations. But there is also a large downside. Scanf just writes what it reads to a specific place in memory given by the argument. And it doesn't check anything at all. So if you place a bug in argument, it will just write to the wrong memory. And there are also no type checks. Another unpleasant thing is that templates for scanf and printf could differ in different compilers and even different versions of the same compiler, especially with long and floating point data types. The C++ way uses special classes called streams, so input-output looks like this. The good thing is, it's rather convenient when the input-output is simple. And it's also far more safe than C-way, as here a certain variable is set and not just some data is written to some place in memory. However, by default, the C++ way is rather slow. But there are fixes for this. First, much time is wasted synchronizing with C-way input-output. You can turn it off by placing a specific line at the beginning of a program. But after that, C and C++ way have separate buffers, and so you can't mix them. You should do everything with streams. Second, by default, cout flushes buffer at each time scene gets called. So it's useful for interaction with user in the console, but on competitions, it's really not needed. And if you have frequently interchangeable cout and scene in your program, this may eat up a lot of time. So it's better to turn it off, and that is done by another specific line, but in the beginning of the program. Another important thing, endl, which prints end-of-line character, in fact also flushes a buffer. So many of them could take much time. Instead, you might just output an end-of-line character directly. And if you do all this, the C++ way becomes just as fast as C way. So in fact, on competitions, people usually use such tuned C++ way with scene and cout. Next, to a very important issue in C++ called undefined behavior. Basically, it's any situation where some incorrect operation occurs and standard defines no particular way for compiler to act, and so anything may happen. The bad thing is, C++ is littered with examples of undefined behavior. Important examples include writing to a wrong place in memory, and particularly addressing an element in an array by wrong index, for example, negative or too large. What happens is that the value gets written in the memory before or after the array, and you couldn't possibly predict what will be in this memory. It may be nothing, or it may be something valuable. So the outcome is also unpredicted. It could be a crash, or it could alter your data and lead to a wrong answer, or it could just have no effect at all. Another example, using local variables before assignment. The issue is there is no defined value for the new variables, but it's often assumed that it's 0. And so when you define a variable but not set it, its value is just some random part of memory. And so it could either be something totally wrong or a 0 as it's assumed. So in the end, it could be either the wrong value or the correct value. Next, functions which should return something but do not do that. Maybe you just forgot a return in one of the cases. What will happen is some random variable from the memory will be returned, and it can be that it's some random value, or it even could be that that's the answer you needed, because your answer is calculated somewhere and placed in the memory. So the result is also totally unpredictable. It turns out signed integer overflow is also undefined behavior, but unsigned integer overflow is correctly defined and is safe to use. So the nice thing about undefined behaviors is that anything may happen. The program could crash, or the result could be wrong, or even everything will be fine, as if nothing happened. And it may depend on anything. Version of the compiler, compiler flags, state of the memory before the run. And so it leads to very subtle bugs. They could appear only from time to time, or they could appear on testing system, but not on your machine. And of course you want to avoid it. The most useful thing to know are examples of common cases of undefined behavior. If you know them, you can avoid them. Some work could be done automatically. Many cases of undefined behavior could be checked by different warnings. For example, functions with no return. So it makes sense to enable as much warnings as possible. In GNU C++ compiler, it could look like follows. There are also other ways to enforce checks from compiler, but they're usually pattern dependent. For example, address sanitizing could be turned on, meaning that writings to wrong places in memory get checked and shown you. There are also libraries with more pedantic implementations of basic structures, like vector, which checks if its syntax is correct. Finally, some additional remarks about C++. Another unpleasant thing is that when your program crashes, you won't see anything useful aside from the segmentation fault message. But in fact, the place of a crash could easily be found by debuggers. In some situations, one actual error could lead to a very long list of compilation errors. So when fixing them, always start from the first. In competitive programming, people often use using namespace as the line. With it, you could use names from here without prepending std and so on. But when mixing namespace, many meaningful names which are defined here, you can't use them after that anymore. For example, next. There are many compilers, and they could have differences, even versions of the same compiler. Performance may differ, or variable size, especially for long double, and as we've already seen, templates for CY input-output. Remember that objects are always assigned directly, meaning that fields get copied every time. It's also true when passing arguments to functions. So if you copy a long vector or set or something like that, it will be linear in size of the structure. And so it may impact the performance. So you need to be careful with it and use pointers or references when needed. It makes sense to use features from C++ 11 standard. There are new structures here, like unordered map or unordered set. And there are also many ways to write more compact and easy to understand code, like bracketed list initialization or for each loops. Of course, testing system needs to have it on it, but they usually do nowadays. So that's all for C++. In this video, we'll talk about specifics of Java. We'll start with input-output. The most convenient way to read values is by using scanner class. But the issue is it's very slow. It can only be used for small inputs, like 10,000 integers or less. And there is no ready alternative with the same functionality. So we need to construct it, which does read input fast is the buffered reader class. But it only reads whole lines without splitting on distinct numbers or ports. So we need to pass the lines read by buffered reader to an instance of string tokenizer, which will split them into tokens. After that, we could easily parse integers or what else we need with functions like integer.parseInt or similar ones. And so all that together makes a fast alternative for the scanner. It makes sense to put everything in one class and define methods with scanner-like names, like nextInt or nextDouble. It's also useful to write it once and then put it in your template code, so as not to write it every time from scratch. With output, it's simpler, as the standard printWriter class has all necessary functions and is fast enough. Next, Java has a large variety of containers, data structures, but they always store objects, and we would often would like to store primitives like ints. Of course, we could use primitive wrappers like capital integer, but as they are objects, they take much more space than just ints. For example, capital integer takes 16 bytes while int just 4 bytes. So, when using collections with primitives, we get substantial object overhead in terms of space and time. Thus, for example, array list of integers is much worse than just an array of ints, and so you should use arrays when you can, when working with primitives. Also, collections come in two kinds, synchronized and unsynchronized. For example, vector and array list. They do basically the same, only the first one is synchronized and the second not synchronized. The difference is synchronized collections are designed for multi-threaded performance, and the unsynchronized, on the other hand, are optimized for single thread. And so, on competitions, as it's always single thread, then we should use unsynchronized collections, like array list. Next, about string. The basic string class is fine enough. The only issue is its instances are immutable. It means that each time an object changes, a new copy of it is created. And particularly, if we append character by character to the string, each time there is a new object. And so, linear number of appends leads to quadratic time. In fact, there is another class just for that. It's called string builder, and it has append method, which just appends a single character, but it does it in constant time. Of course, we could also use like array list of characters, but the string builder, there is no object overhead. Finally, some other remarks. You need to keep in mind, when estimating memory of custom classes, that an object of custom class takes more space than just the sum of its fields, at least by 8 bytes. So you need to be careful with memory. Another thing, there are in fact two different sorting algorithms in Java. One is collection sort and the second is array sort. They are different. Collection sort is a merge sort, and so it works always big O of n log n time, and it's stable. In contrast, array sort is quick sort, and so it's not stable, but what's worse, there are special cases where it works quadratic time. So it makes sense to randomly shuffle an array before doing array sort, just in case. Next, as objects are always assigned by reference, do not forget to clone them when needed, because if you have several different pointers to the same object, then changing one changes also the others, and it could lead to very subtle bugs when you don't expect something to change and it changes. So watch for it. And that's all for Java. In this video, we'll talk about Python. It's very powerful and easy to use high-level language, but it could be 1-2 orders of magnitude slower than Java or C++. So it could be that some problems just can't be solved in Python, because the time limit is just too little for Python. But there are ways to speed up a Python program, and we'll start with covering them. First trick is that addressing local variables is much faster than addressing global. That's due to the interpreted nature of the language, because in each function, variables can be enumerated, and they are stored in what's like a list. And global variables can't, and they are stored in what's like a dict. And we know that dynamic arrays are much faster than dictionaries. So that's where speed up comes from. And if you use global variables frequently, replace them with local ones. If needed, pass as arguments. A special case of that is global code. In Python, your program begins with executing global statements, those with their intent. They in turn call functions, and so on. But the variables in global statements are also global. So to speed up, you may put all global statements in one separate function, and in global part only call that function. So it will be something like C++ or Java, when there is always the main function. Another danger is with appends. When you use the plus sign, a new object is created, and so this is linear in time. So use the plus assign operator or append method for lists. As we know, input-output operations are particularly slow, and in Python even more so. The fastest methods here could be slower than C++ or Java. But there are also some tricks. First, you should use file input-output methods, like read or write. In contrast to input and print functions, which are designed for user interaction, they are much more efficient. Another thing is to have as little input-output operations as possible. You may use read or readlines methods to read a whole file as a string or list of strings, and then parsing everything you need from them, without frequent readings from the file. You may also try to write larger chunks. For example, you could write a list not one by one elements, but, for example, with a join function. And here, the speedup will come not only from one writing to the file, but also from the list operations. And we'll talk more about that in the next slide. In Python, there are a lot of useful tools for managing lists and other sequences. For example, there is a function for summing elements of the list, finding a minimum element, joining a sequence of strings into a long one, and the powerful standard module itertools. These tools are very useful in writing compact and easy to understand code, but they also can make it faster. On the slide, you see two ways of counting the sum of elements on the list. First, with the standard sum function, and a second, by just a for loop. And it turns out, the first way is like 5 times faster. That's because, in fact, additions here are performed in a C code of sum, and not in the Python codes of for loop. So, in fact, list operations can turn your Python slow code into C fast, and you should always use them when you can. Finally, some general remarks about Python. There are two common versions of Python, Python 2 and Python 3. They may differ in syntaxes, but they also may have different performance in the same functions. For example, function range in Python 2 returns a literally list of n elements, whereas in Python 3 it's just a generator, and so is much faster. In Python 2, the same generator is returned by function xRange. There are cases when either version is better than another, but on average, Python 2 tends to be slightly better. There are another interpreters for Python. The basic is CPython, but there are also others. Most importantly, PyPy. It has some optimizations compared to CPython, and so sometimes it will be faster, especially the version for the second Python. To avoid Stack Overflow on applications, Python limits steps of recursion. If the number of nested calls exceeds 1000, a program is terminated. But on competitions, even much larger number is fine. For example, when traversing graphs, there could easily be 100,000 nested calls. So, as to not get runtime error, you may want to upper this limit. This is done by a special command, sys set recursion limit. In some implementation problems, especially helpful are functions like eval and exec, which execute correspondingly expressions and pieces of Python code on the run. They utilize the interpretative power of the language, because the code executed should not necessarily be written explicitly in a file, as there is no compilation. It could be also generated from input or otherwise. And so, you may utilize Python's internal parsing machinery instead of writing your own. Interpreting offers more flexibility, but also more options for bugs. Compilation by itself checks a lot about the whole program, the syntactic correctness, type matching, and many else. Whereas in Python, only a particular test gets executed, and so anything is tested only on these particular values. For example, if you have an if clause and on the test you go only in the first part, then the second part doesn't check at all. And so even if there is a complete nonsense here, it doesn't get run, and so it doesn't throw any errors. Thus, you need to test even more carefully. Another thing, compiled language could receive a compilation error verdict, the detailed error message. And in Python, any error is just a runtime error, without any additional information from the testing system. You also need to remember that objects are assigned only by references, and so there isn't any copy made when assigning. You need to clone objects by yourself if you need them to be different. You need to be especially careful with structures containing other structures, for example, list of lists. And that's all for Python. In the final video of the lesson, we will summarize advantages and disadvantages of C++, Java, and Python. It's useful to know how your language fares against others, especially if you are unsure what language you should use, so you could learn it or improve your performance with it. We'll start with C++. It's by far the most popular language in programming competitions. On ICM ICPC World Finals, for example, nearly every team uses C++ as their primary language. And why it's so popular? Mostly because of its performance. Basic operations in C++ are much faster than in other languages. So if you write a program in C++, you could be really sure that it will pass the time limit. Of course, if the solution itself is optimal enough. And also, there is quite a decent standard library in C++. But there are also disadvantages to it. You require great care and debugging skills when using C++, because cases of undefined behavior could be anywhere, and if you get a crash, you'll only see that it's a designation fault without any details about it, so it may be really hard to debug. Next, to the Java language. It's not as popular as C++, but people also use it with great success even on the highest levels. Java is actually a bit slower than C++, but not much, like 1.5 or 2 times. And sometimes time limits and problems are even adjusted for Java, meaning that for every language time limit is 2 seconds, for example, and for Java 3 seconds. And so Java is totally equalized to C++ in terms of performance. Java has a rather good standard library. There are even things which you won't find in C++, for example, big integer class. The downside of the Java standard library is that you need to implement fast reading by yourself. Next, code rules in Java are more pedantic than in C++. For example, function with non-void return type must actually return something. And also, there are additional checks, for example, for array indices. And all of that makes Java sometimes less vulnerable for certain kinds of bugs. Also, programs in Java tend to be longer because it's like a little verbose language. But with good IDE and features like autocompletion, it will not harm you very much. Finally, the Python language. The main issue here is performance. Programs in Python tend to be like 1 or 2 orders of magnitude slower than programs in C++ and Java. So, some problems couldn't be solved with Python at all. Standard library is rather good, but it still lacks some useful things, for example, sorted set or bit set. But still, Python is a good high-level programming language where it's rather convenient to write programs, and so programs could be a lot shorter than similar in C++ and Java. In all, Python may be not a very good choice for the primary programming language for you, but for some problems it could be very well. For example, when performance is not very important, like implementation problems of certain kind or math problems. Let's summarize what we've learned in this lesson. First, language features a lot of useful tools, and it will help yourself greatly if you learn how to use them. Second, we've seen some common pitfalls for Java, C++, and Python, and the things you just need to know so you won't get caught. And we've compared different languages. For your primary language, it's a good choice to have fast language like C++ and Java. But Python also could be useful when performance is not very critical, and it could save some time on debugging or implementing. So that's all for this lesson, and good luck with languages.
Hello, my name is Alexander Kulikov, and together we're going to study dynamic programming. Dynamic programming is a powerful algorithmic paradigm with lots of applications in areas like optimization, planning, scheduling, bioinformatics, and many others. At Contents, it is one of the most popular types of problems. A common feature of such algorithms is that usually a solution is easy to implement, but at the same time it does not mean that it is also easy to find. For this reason, one needs a lot of practice to be able to come up with dynamic programming solutions. And this is exactly what we're going to do in this part of the class. We start with a very soft introduction. Fibonacci numbers are defined recursively. F sub 0 is equal to 0, f sub 1 is equal to 1, and each subsequent number is equal to the sum of two previous numbers. Consider the following natural computational problem. Given n, we would like to compute f sub n. Since Fibonacci numbers are defined recursively, it is natural to convert the recursive definition into a recursive algorithm. And this is exactly what we are going to do. Namely, given n, we first check whether n is at most 1. If it is, we just return n. Otherwise, we just make two recursive calls to compute f sub n minus 1 and f sub n minus 2. And finally, we return the sum of the results of two recursive calls. What is good about this algorithm is that it is clearly correct. Indeed, it directly implements the definition of Fibonacci numbers. What is bad about this algorithm is that it is catastrophically slow. The slowness occurs because many computations are repeated by this algorithm. At the picture here, you see the tree of recursive calls. For example, to compute f sub n, the algorithm computes f sub n minus 1 and f sub n minus 2. In turn, a recursive call to f sub n minus 2 is unwounded into two recursive calls to f sub n minus 2 and f sub n minus 3, and so on. So, as shown on the picture, f sub n minus 3 is computed at least 3 times in this case. In fact, the algorithm computes f sub n as the sum of f sub n ones. And this is a disaster, because Fibonacci numbers are known to grow exponentially fast. In particular, f sub n is roughly equal to the golden ratio to the n, where the golden ratio is equal to 1.618 and so on. In particular, there are already 31 digits in f sub 150, and this makes computing this Fibonacci number completely infeasible with modern computers. As we have discussed already, the algorithm is slow just because many computations are repeated. At this point, it makes perfect sense to quote George Santayana: "Those who cannot remember the past are condemned to repeat it." And this also suggests a fix to our previous algorithm. Namely, we are going to remember the past. We are going to save all our intermediate computations. Okay? The trick is known as memoization. Here on the slide, you see the new code. Here, we first create a table T. In this Python code, this is just a dictionary. Then, to compute a Fibonacci number recursively, we do the following. We first check whether f sub n is already stored in the table. We only start computing it if it is not in the table yet. To compute it, as usual, we first check whether n is at most 1, and if it is, we just save the value n in the table. Otherwise, we make 2 recursive calls and then compute the sum of their results and store the resulting value in the table. Okay? So at this point, you are probably surprised. Why do we need all this fancy stuff like memoization, dictionaries, and recursion for solving such a simple computational task? And you are absolutely right. In fact, we can solve this problem in a straightforward way. Indeed, this is how one would compute, for example, the 5th Fibonacci number on a piece of paper. We first write down the zeros and the first values of Fibonacci numbers. We then compute f sub 2 as the sum of f sub 0 and f sub 1. We then compute f sub 3, then f sub 4, and finally f sub 5. And this strategy can be implemented in a straightforward way. Namely, we first allocate an array T of size n plus 1, we initialize its first 2 values, and then in a simple loop, we fill in this array with Fibonacci numbers. Finally, we return f sub n. And even this simple algorithm can be improved, and you have probably already guessed how. In fact, we do not need to waste so much memory. Namely, we do not need to remember the whole past. It is enough to store just the 2 current Fibonacci numbers. And this can be implemented as follows. So we are going to store the previous Fibonacci number and the current Fibonacci number. Initially, the current Fibonacci number is equal to f sub 1. Then, in a simple loop, we just move the current Fibonacci number to one position to the right n minus 1 times. So in the end, current is equal to f sub n. The resulting algorithm performs about n additions. At the same time, these are not additions of small numbers. Recall that Fibonacci numbers grow exponentially fast. From theoretical point of view, this means that we should not treat additions of such numbers as a basic operation. From practical point of view, this means that, for example, already f sub 100 does not fit into, for example, 64 bits. So we need big num arithmetic to store the results. To summarize, the main idea of dynamic programming is to avoid recomputing the same thing again. This is usually done by saving all the intermediate results in a table. We've used Fibonacci numbers to illustrate this idea. It should be noted, however, that Fibonacci numbers is probably a slightly artificial example of using dynamic programming, just because it was clear from the very beginning what we need to compute in order to solve the original problem. We will see more interesting examples in the next parts. Now we are going to design a dynamic programming solution for the so-called longest increasing subsequence problem. In this problem, we are given an array or just a sequence of n integers, and our goal is to find a subsequence inside this sequence which is increasing and as long as possible. Note that it should not be contiguous. So one example of an increasing subsequence in the sequence shown on the slide is 1, 3, 4, 6, 9. So it is not difficult to check that it is indeed increasing, and we will soon learn a way to convince ourselves that it is the longest possible. Another longest increasing subsequence in this case is 2, 3, 4, 5, 8. This shows in particular that an optimal solution for this problem needs not to be unique. So to start designing an algorithm for this problem, let's try to analyze an optimal solution. So consider a longest increasing subsequence and its last two elements, z and x. What can be said about z and x? So first of all, we know that z must be smaller than x. Okay, so what is much more important for us is the following property. The prefix of the longest increasing subsequence shown here, ending at the element z, must be the longest possible subsequence ending at this particular element. Why is that? Well, imagine that this is not the longest increasing subsequence ending at z. This means that there is some other subsequence which is longer than this prefix which ends at the element z. But this would mean that we could take this longer subsequence ending at z and append x to it. This would give us a longer increasing subsequence in the initial array than the one that we started with. What we've just shown is that the longest increasing subsequence problem possesses the so-called optimal substructure property. This means that in any longest increasing subsequence, any of its prefixes must be also an optimal increasing subsequence ending at this particular element. We have shown this by the so-called cut and paste trick. Namely, if this prefix is not optimal, then there is a longer prefix, and in this case we can cut this original prefix and paste a longer prefix. And this would give us a longer increasing subsequence, contradicting to the fact that we started with an optimal solution. And this leads us naturally to the following sub-problems. For all I starting from 0 to n minus 1, let's compute the length of an optimal increasing subsequence ending at an element I. As we've discussed previously, such a subsequence If it is not of length 1, it has some previous element j. So in this case, the length of an optimal increasing subsequence ending at the element I is equal to the length of its prefix ending at some element j plus 1, corresponding to the fact that we append element I. So this gives us the following recurrence relation. So the solution for a subproblem at I is equal to 1 plus a solution plus the maximum of all the solutions of all subproblems for j's, where aj is smaller than ai. So we only go through all subproblems such that I can be appended to their solutions. Okay? So if there is no such j, meaning that the set of all such j's is empty, then in this case there are no j's such that aj is smaller than ai, and in this case clearly the solution to our subproblem is equal to 1, meaning that there is just one increasing subsequence ending at the element I, and it is just a subsequence consisting of just this particular element. Okay. Also, there is a base case when I is equal to 0. The solution to our subproblem is also equal to 1, and in this case, again, our subsequence consists of just the zeros element. We are now going to convert our recurrence relation into a recursive algorithm. For this, we are going to use a table T, such that T of I is going to store the value of a subproblem LIS of I. The exact data structure behind the table T is not that important at this point. It could be an array, or a dictionary, or a hash table, or whatever. So, as usual, before computing LIS of I, we are going to check whether its value is already stored in the table. If it is stored in the table, we return it immediately. We only start computing it if it is not in the table yet. And for computing it, we actually follow our recurrence relation. So we first initialize it to 1, just to reflect the fact that we always have at least one increasing subsequence ending at the element I. It is a subsequence consisting of just element I. Then we go through all j's that are smaller than I, such that a of j is smaller than a of I. And we check whether appending I to an optimal increasing subsequence ending at j, whether it gives us a better solution that we currently have. If it gives us a better solution, then we update our current solution. Finally, we store the result of T of I, and as a result of the whole algorithm, we need to return the maximum overall I of LIS of I. This is just because we don't know where the optimal increasing subsequence ends. Okay? The running time of this algorithm is quadratic, and this is just because there are n serious recursive calls. By a serious recursive call, I mean a call which is not just a table lookup. There are at most n of them, just because each time when there is a serious call, we store its value into our table. And the running time needed to compute this value is also proportional to n. Overall, this gives us n squared operations. Okay? Then one can notice that what we need to store in the table are all solutions to our subproblems. They are indexed by integers from 0 to n minus 1, and in fact these are consecutive integers. This suggests that we can use an array to implement our table T. And in fact, we can actually fill in this array just in a straightforward fashion, So we are going to fill in this array iteratively instead of recursively. So for this, we first initialize this array, and then in a single loop going from left to right, we fill in this array with values using our previous recursive definition. What is important to note here is that each time when we compute T of I, all the previous T of j's for j's less than I are already computed. Okay, so the running time of this algorithm is also quadratic just because it consists of two nested for loops. Previously, we designed an algorithm for finding the length of an optimal increasing subsequence. Now we're going to show how to find the longest increasing subsequence itself. For this, we're going to store an additional array showing for each I not only the length of an optimal increasing subsequence ending at this particular element I, but also the previous element in this subsequence. Here is our previous code with three small additions. First of all, we allocate an array prev in the very beginning. Then, in the loop, we first initialize prev of I with -1. This basically means that at this point, we don't have any previous element in our currently longest increasing subsequence ending at the element I. Recall that at this point, the only increasing subsequence that we know that ends at the element I consists of just a single element I. So there is no previous element, so prev of I is equal to -1. Then, when computing the solution for the subproblem ending at an element I, each time when we find a better solution through the previous element j, we actually change prev of I to j. This basically means that at this point, the longest increasing subsequence ending at an element I has j as the second to last element. Okay, so let's give an example. Using this example, we are also going to show how to uncover a solution. So what you see here is the result of applying this algorithm to our sample array. Okay, so we see that the length of an optimal increasing subsequence is equal to 5, just because 5 is the maximum value of in our table T. In particular, since T of 13 is equal to 5, this means that there is a subsequence, that there is a longest increasing subsequence ending at the element 5. Okay, so we are going to unwind our optimal increasing subsequence from right to left. So we already know its last element. This element is number 13. So prev of 13 is equal to 9. This basically means that 9 is the second to last element in this subsequence. So let's go to element 9. At this point, we have already recovered the last two elements of an optimal increasing subsequence. Namely, the last element is element 13, the previous element is element number 9. To find out the element that goes before the element 9, we simply look at prev of 9. It is equal to 5, meaning that the previous element is 5. Then to find out the element that goes before the fifth element, we look at prev of 5, and so on. So this way, we will uncover the whole optimal increasing subsequence. We stop this process when we find that prev of our current element is equal to -1. This basically means that there is no previous element for this particular element. Now let's implement this. So for this, we first need to find the largest element in our table T. This can be done just by scanning the array T from left to right. Okay, then what we're going to do is to uncover our optimal solution. So for this, we are going to use the list LIS. So we start with the element where with the element k, where table is where the value of the table T is maximal. Then what we're going to do in a loop is the following: we put k to LIS, and then we replace k with prev of k. And we repeat this process until we reach, until pref of k, is equal to -1. This means that there is no previous element. So, and each time we append the current element k to our longest increasing subsequence, to the variable lis. So recall that in this case, we actually unwind our longest increasing subsequence from right to left. So in the end, we need to reverse this sequence and then to print or to return the result. Now let me also mention the following interesting fact. So in fact, we do not need the array pref in order to reconstruct the optimal increasing subsequence. So recall that the fact that the maximum value in t is equal to 5 means that the longest increasing subsequence in our sample array has length 5. So let's just stand at some position where t is equal to 5. So what we know is that this is the last element of some longest increasing subsequence of length 5. But what this means is that the prefix of this longest increasing subsequence is equal, its length is equal to 4. And this in turn means that to find the previous element, it is enough to scan the table T from right to left and to find the position where we have 4 in the array in the table T, such that the corresponding element of the initial array A is smaller than the last element of the last element of our longest increasing subsequence. So essentially, this means that what we need to do is to find a pattern like 5, 4, 3, 2, 1 in our table T, such that the corresponding elements of our initial array are decreasing. So they are decreasing because we go from right to left. And this can be done just with a simple scan from right to left, starting with the last element of the longest increasing subsequence. Let's now summarize. By analyzing the structure of an optimal solution for the longest increasing subsequence problem, we realized that it makes sense to compute the following values, to define the following subproblems. For every element I from 0 to n-1, we defined LIS of I as the length of the longest increasing subsequence ending at an element I. Using these subproblems, we can define a recurrence relation that allows us to express the value for LIS of I through the values of LIS of j for j's smaller than I. Then, when we wrote down this recurrence relation, we converted it into a recursive algorithm just by adding memoization, just by adding a table where we stored all the intermediate results. Our next step was to convert this recursive algorithm into an iterative algorithm. So we just filled in the table T from left to right, one by one. Okay, and finally, we were able to reconstruct our solution using some additional bookkeeping information, such that for every subproblem we stored not only its solution, not only the length of an optimal solution ending at this particular element, but also the choice leading to this optimal solution. So in this case, this was the previous element in the longest increasing subsequence ending at the ith element. We will now discuss an alternative way of solving the longest increasing subsequence problem. It is a common feature of many dynamic programming algorithms that the most creative part in designing such an algorithm is coming up with the right notion of a subproblem. When we have the right notion of a subproblem and the recurrence relation for subproblems, it is just a technicality to convert this recurrence relation into a recursive algorithm. In the previous part, we were able to find the right way of defining subproblems by analyzing the structure of an optimal solution. In this part, we are going to do the same by actually first implementing the brute force solution and then by optimizing it. Okay? So what is the most naive way of solving the longest increasing subsequence? Well, let's just enumerate all possible increasing subsequences and let's just select the longest one. Right? So this is once again the most naive way of solving this problem. So to implement this idea, let's do the following. Let's start with an empty sequence. And at each iteration, we are going to do recursively the following thing. So we have some, initially the sequence is empty, and at each iteration, we just try to extend it by every possible element, just by one element, and then we make a recursive call. So, and also we keep track of the length of our current subsequence, and if it is longer than what is currently known, then we update some of our global variable, for example. The resulting algorithm is going to be slow. For example, if our initial array is increasing, then we will be forced to go through all possible subsequences of this array, and there are exponentially many of them. But not to worry, we are going to optimize this algorithm later. Here is the Python implementation. So this is a recursive procedure that is going to extend optimally the current subsequence. Initially, the sequence that we pass to our recursive procedure is empty. Inside the recursive call, we do the following. We initialize the following two variables, last index and last element. The last index is the last index of our current sequence. So if the sequence is empty, then it is just equal to -1. If it is not empty, then this is just the last element of the sequence. The last element is actually the value of the corresponding index. If the sequence is empty, it is equal to -infinity. If it is not empty, it is equal to the corresponding element of our initial array A. Then, after initializing these two parameters, we try to extend our current sequence by one element. Namely, we go through all possible elements to the right of our current index, and if the corresponding element is greater than our last element, then we append it to our sequence and we make a recursive call. Okay, now let's start optimizing our code. So first of all, a closer look at our code reveals the following interesting property. In fact, what we do in our recursive procedure is trying to extend optimally our current sequence. At the same time, we are not interested in what is going on in the beginning of our sequence. What we essentially use is its last element and the length of the current sequence. So, which means that instead of passing the whole sequence to our recursive call, it is enough to pass its last element, and it's the index of the last element of the current sequence and also its length. So let's do this and let's optimize the code. And here on the slide, you actually see the optimized code. So in this case, we start by computing the last element, again, just by using the last index. And then we try to extend the current sequence optimally by making a recursive call to a sequence for which we append some new element. So we iterate through all the elements, through all I that are greater than the last index, and if A of I is greater than A of last index, we try to append the element I to our current sequence. So in this case, we increase the length by 1, and we use I as the last index of our new element. So this is the optimized code. So far so good. In this case, instead of passing the whole sequence, we pass only two parameters, the last index of our current sequence and its current length. Again, a closer look at the resulting code reveals that in fact we are not that interested in the length of the current sequence in order to optimally extend it. In other words, no matter what is the length of the sequence, we are going to extend it based on its last element in exactly the same way. Slightly more formally, if we subtract x from the seqlen in this recursive call and add x to the result, it would give exactly the same. And this suggests that we just replace seq length by 0. And this will give us the algorithm that you see here on the slide. So basically what we did here is just that we replaced the sequence length with 0. So again, this is a recursive algorithm, and in general it is going to be slow just because it is going to recompute many things again and again. But we already know how to make it more efficient. We just need to add memoization. So for this we might want to introduce a table T and to store all the results that are already computed in the table. And each time when we make a recursive call, we first check whether the result is already in the table or not. So if we add memoization to this recursive procedure, then what we get is almost the same algorithm that we got before in the previous parts. Okay, now let's summarize. So the most important message is that the most creative part in designing dynamic programming solutions is coming up with the right notion of a sub-problem. And there are basically two common ways of finding the right sub-problem. So the first one, as we've illustrated with an example of the longest increasing subsequence, is analyzing the structure of an optimal solution. Okay? The second one that we've just illustrated in this part is first implementing the most naive brute force solution and then optimizing it. This part is devoted to another classical problem, the edit distance problem. The edit distance between two strings or two words is the minimum number of single letter modifications needed in order to get the second string from the first string. By single letter modifications here, we mean insertions, deletions, and substitutions. The edit distance is also known as Levenshtein distance after Vladimir Levenshtein, who introduced it in 1960s. This is a natural measure of similarity between two words or two strings. For example, when a spell checker encounters a misspelling, it suggests a word which is close to the misspelled word with respect to typing errors. And insertions, deletions, and substitutions are exactly the well-known typing errors. Okay, so edit distance or generalizations of edit distance are also used in computational biology to align sequences. Now let's give an example. In our example, we're going to turn the word editing into the word distance. So for this, we first remove the letter E. Okay, so we then insert the letter S. Our next operation is to replace the letter I with the letter A. We then replace G by C, and finally we insert E. Okay? So another convenient way of showing this sequence of operations is the so-called alignment. So what you see here on the slide is an alignment of two words, again, editing in distance. In this alignment, any column is either a deletion or an insertion or a substitution or a match. So a match is a column where we have the same two letters. An insertion is, of course, a column where we have a gap in the top and we have a letter at the bottom. A deletion is a column where we have a letter at the top and a gap at the bottom. And the substitution is a column where we have two different letters. So in this case, we define the cost of each column to be equal to 1 for each column except for matches. So the cost of matches is equal to 0. So in this case, the cost of this alignment is equal to 5. It is not difficult to show that for any sequence of operations, there is an alignment of the same cost, and vice versa. For any alignment of some cost, there is a sequence of operations where the number of operations is equal to the cost of the alignment, of the initial alignment. So for this reason, what we're going to be looking for is the least expensive alignment. As usual in the design of dynamic programming algorithms, our goal now is to come up with the right notion of a subproblem. For this, let's analyze the structure of an optimal solution. So in this case, an optimal solution is an optimal alignment. In particular, let's focus on its last column. So what we know about this last column is that it is either an insertion or a deletion, or a match, or a mismatch. Okay, so assume for the time being that it is an insertion. Then what we know for sure is that it is the last symbol of the last character of B that is inserted, which means that in this column we have a gap at the top and we have the last element of B at the bottom. Okay, now let's consider what happens if we cut this last column out of this alignment. Then what is left must be an alignment of the word A with the prefix of length m-1 of the word B. And what is more, this alignment must be optimum. Why is that? Well, again, by the cut and paste trick. Because if this sum alignment is not optimal, meaning that there is some other less expensive alignment, then we can cut this initial alignment and replace it by a less expensive alignment here. Okay? So another possibility is that the last column is a deletion. Then what we know is that in this case we delete the last symbol of A. And what is left, if we cut the last column, must be an optimal alignment of a prefix of A and the word B. And the last possibility is that if in the last column we have two letters, then what we know is that if we cut this column, then what is left must be again an optimal alignment of a prefix of length n-1 of the word A and the prefix of length m-1 of the word B. Okay? This suggests that we define our subproblems as follows. Let's define ED of ij as the least expensive alignment, or just the cost of the least expensive alignment of the prefix of length I of the word A and the prefix of length j of the word B. Then our previous analysis shows that we can compute ED of ij as follows. So this alignment for prefixes is, again, its last column is either an insertion or deletion or a match or mismatch. Recall that we pay 1 for insertions, for deletions, and for mismatches, and we pay nothing for matches. Okay, this allows us to write the following recurrence relation for ED of ij. ED of ij is equal to minimum of ED of I minus 1j plus 1, or ED of I j minus 1 plus 1, or ED of I minus 1 j minus 1 plus the difference between the i's symbol of A and the j's symbol of B. And by this difference, we mean the following simple function. It is equal to 1 if the corresponding two symbols are different, and it is equal to 0 if they are the same. This basically corresponds to the fact that we pay 1 for different symbols or for mismatches, and we pay 0 or nothing for matches. Okay? So the base case for this recurrence relation is the following. When I is equal to 0, ed of ij is equal to j. And similarly, when j is equal to 0, then ed of ij is equal to I. Why is that? Well, in this case, we just try to find an optimal alignment of an empty prefix of some word and with some possibly non-empty prefix of some other word. In this case, obviously, an optimal way of getting one prefix from the empty prefix or getting the empty prefix from some other is either to insert all the elements or delete all the elements. Okay, and in this case, we need exactly I or j operations. Okay, so once again, when we have a recurrence relation, it is just a technicality to transform it into a recursive algorithm. So for this, we just introduce it, we just initialize a table, and then each time when we make a recursive call, we first check whether the solution for the corresponding subproblem ij is already in the table, and if it is in the table, we immediately return the result. If it is not in the table, we compute its value by making 3 recursive calls, or if it is just the base case, we compute it in a straightforward way, and when we compute it, we save it to the table in order to avoid recomputing the solution for the same subproblem again. Okay, now our goal is to convert this recursive algorithm into an iterative algorithm. So recall that the space of all our subproblems is all the values of ij, where I and j range from 0 to n and m respectively. This suggests actually that we can use just a 2D table for storing all the solutions for our subproblems, and this is what we're going to do. Now let's also realize the following fact. ed of ij depends on 3 previous values, or it depends on ed of I minus 1, j minus 1, ed of I minus 1, j, and ed of I, j minus 1. So our order of solving all the subproblems should respect this fact. So in other words, when computing ed of I, j, we need to make sure that all the previous 3 values are already computed. And there are actually 2 natural orders that respect this fact. We can either go we can either fill in the table row by row, or we can do this column by column. In both cases, it is easy to check that when computing some particular value, all the previous 3 values are already computed. Okay, and then it is straightforward to implement the corresponding iterative algorithm. So we allocate a 2D table. We first initialize its 0th row and 0th column, and then we fill in this table row by row following our recurrence relation. Let's now give an example of how this table looks like for our toy example of computing the edit distance between the words editing and distance. So we start by filling in the 0th row and the 0th column of the table. We then start computing the value d of 1 at 1, 1. It is computed as the minimum value of d at 0, 1 plus 1, d of 1, 0 plus 1, and d of 0, 0 plus 1. In this case, the minimum is attained as d of 0, 0 plus 1. and it is equal to 1. So we put this value to this cell, and this corresponds to the fact that the added distance between the prefix of length 1 of one word and the prefix of length 1 of the second word is equal to 1, which makes sense because these are different letters, D and E. We then go to D1 for computing the ED of 1, 2, and it is computed and it is equal to 1. And again, it makes sense because the added distance between D and ED is equal to 1. We just need to insert E, right? So we continue in the same fashion. And when the whole table is filled in, we see that at the bottom right corner, the value is equal to 5. And this basically says that the added distance between the whole two words is equal to 5. Okay, this convinces us that the sequence of operations that we considered in the beginning of this video is in fact optimal. Okay, as a final remark, let's discuss how to implement a brute force solution for this problem. So for this, we would extend an optimal alignment element by element. So at each recursive call, we will try to append a new column to our current alignment. And then it would remain to notice that in order to extend our partial alignment, it is enough to know only the last column of this alignment. Then again, just by adding the minimization trick for the corresponding recursive algorithm, one would get a similar algorithm that we've just designed in this part. In the previous part, we designed an algorithm for finding the cost of the least expensive alignment. In this part, we're going to reconstruct the optimal alignment itself. As usual, we're going to unwind it, going from right to left. Namely, we're going to go from the bottom right corner to the top left corner. Each time when we go up, there is a deletion. Each time when we go left, there is an insertion. And each time when we go to the diagonal neighbor, there is a match or a mismatch. So recall that when computing a particular value in our table, it was computed as a minimum among three of its neighbors: its top neighbor, its diagonal neighbor, and its left neighbor. So once again, its top neighbor, if it was attained through its top neighbor, then there is a deletion. If it was computed through its left neighbor, then there is an insertion. And if it was computed as a minimum through its diagonal neighbor, then the corresponding operation is either a match or a mismatch. Okay, so let's illustrate it on our toy example, where we computed the editing distance between the words editing and distance. So initially, we stay at the bottom right corner. So the value at this particular cell is equal to 5. Which means that the added distance between these two words is equal to 5. We see that this value is attained through two of its neighbors, through its top neighbor and through its diagonal neighbor. This in particular means that there are two optimal alignments, one whose last operation is deletion, and one whose last operation is actually a mismatch. For concreteness, let's focus on the one whose last operation is a mismatch or a substitution. So we add this substitution as a last column to our alignment and move to this diagonal neighbor. So what we see for this diagonal neighbor is that its value is attained through its top neighbor. Okay, which means that in this particular case, the corresponding operation is a deletion. Okay, so we add this deletion, we move to the corresponding top neighbor and proceed in a similar fashion. So we show here on this slide the detailed the path to the left top corner without a detailed walkthrough. So let me, as a final remark, let me just mention that what we're doing here is actually finding a cheapest path from this corner to that corner, where by the cost of the path we mean the following. Each time when we go up, we pay 1. Each time when we go left, we pay 1. Each time when we go to the diagonal number, we pay 1 if the corresponding two symbols are different. And if they are the same, we pay nothing. So what we see here on the slide is actually the least expensive path from this particular cell to that particular cell. And what you see here at the bottom of the slide is the corresponding optimal alignment. We conclude this part with a few final remarks. First of all, note that the running time of the designed algorithm for the edit distance problem is proportional to nm, so the length of the two given words. Also, the space requirement is also big O of mn. This is just because we need to store a 2D table. So for spell checking programs where we compute the edit distance between two short words, the space requirement is not an issue at all. It might at the same time be an issue in biological applications where we compute the edit distance between sequences consisting of thousands or even millions of symbols. So in this case, storing this table would require us to allocate gigabytes of memory. The good news at the same time is that it is not too difficult to tweak our algorithm so that to reduce the quadratic space requirement to just linear space requirement. For this, note the following property. When we filled in the table, for example, row by row, so each time when we compute the value of a particular cell, it only depends on the values in this row, namely from the left neighbor, and also from two values in the previous row, namely from the diagonal neighbor and from the top neighbor. This suggests that instead of storing the whole table, it is enough actually to store just two rows, the current one that we are currently filling in and the previous one. So instead of storing all n rows, it is enough to store just two rows. And the same trick actually applies to columns. We can fill in the table column by column, and instead of storing all possible columns, we store just the two current columns. Okay, so this allows us to reduce the space requirement from big O of mn to big O of the minimum of m and n, so from quadratic to linear. Okay, it should be noted, however, at the same time that for reconstructing a solution, we actually need the whole table because we need to trace the path from this corner of the table to that corner. So it is not so easy to reconstruct a solution without storing the whole table. But it is known how to do this, and the corresponding algorithm was designed by Hirschberg. So you can Google for Hirschberg algorithm, and let me just give you the underlying idea. In order to find an optimal alignment using only a linear amount of space, we are going to do the following. We are going to compute the edit distance between the corresponding two strings in the same fashion as we did in our previous part. At the same time, when computing this, we are going also to compute the value k such that in an optimal alignment, the first half of the word A is aligned to the first k symbols of the word B, okay? Which also means that the second half is aligned to the last m minus k symbols of B. So we will first compute this value of k, and then we will make two recursive calls. in order to compute the optimal alignment for the first half of A and for the second half of A. So in a sense, this is a nice combination of dynamic programming and divide and conquer techniques. So in general, it gives an algorithm working in more or less the same time, so big O of NM, and that uses only a linear amount of space and also is able not only to compute the edit distance between two strings, but even an optimal alignment. Okay? So the last remark is that our algorithm can be also easily transformed into an algorithm that computes the weighted edit distance between two strings. So in this case, we do not treat all operations as a unit cost operations. So we might want to assign different costs to different operations. For example, different costs to insertions, deletions, and different costs to substitutions of some pairs of symbols. So why we might want to use this? Well, first of all, in spell checking applications, it is natural to assume that some substitutions are more probable than some others. This, of course, depends on our keyboard layout. Also, in computational biology, it is also the case that some substitutions are more likely than others. And fortunately enough, our recurrence relations can be easily tweaked to reflect this fact. Namely, instead of adding just one for insertions, deletions, and substitutions, we need to add the cost of the corresponding deletion, the cost of the corresponding substitution, or the cost of the corresponding insertion. Okay? So this concludes the part on the edit distance problem. In the next part, we are going to design algorithms for the well-known knapsack problem. This is a classical problem in combinatorial optimization. Then for the chain matrix multiplication problem, and we will then review the whole part on dynamic programming. Hello and welcome to the next module. In this module, we are going to continue studying the dynamic programming technique. We do this by considering the famous knapsack problem. So this is a famous problem in combinatorial optimization. In this case, we are given a knapsack with a limited capacity together with a collection of items with known weights and values. And our goal is to select a sub-collection of these items so that their total weight does not exceed the capacity of our bag, while their total value is as large as possible. This is a classical problem in combinatorial optimization with hundreds of applications in areas like planning, scheduling, resource allocations, and others. It is important to note that in applications, weights and values may actually denote various things. To give an example, consider the following application. Suppose we're given a time interval and a set of TV commercials. So, for example, this interval might be just 100 seconds. What we would like to do is to select some set of these TV commercials with the following two constraints. First of all, we, of course, would like to maximize the total revenue from these commercials. On the other hand, we would like the sum of the lengths of these TV commercials to not exceed the length of the available time interval. In another application, another toy application, another example, suppose that we're given a limited budget, and what we would like to do is to purchase some set of machines to maximize their total performance. So in this case, our capacity is actually our budget, and the values of the machines are actually their performance. Okay, so there are two natural variations of the knapsack problems. First of all, the knapsack may be either fractional or discrete. In the fractional version, we assume that we can take any fraction of any item. On the other hand, in the discrete case, each item is either taken or not. Okay, so in turn, for the discrete knapsack problem, there are two further variants. Knapsack with repetitions or knapsack without repetitions. In the first case, we are allowed to take any number of any items. In the second case, knapsack without repetitions, we are allowed to take only a single copy of each item. As we already know, the fractional knapsack can be solved by a natural greedy algorithm. Namely, we just keep repeating the following step. At each iteration, we just take the maximum amount of item whose value per unit of weight is as large as possible. It is not difficult to show that this leads to an optimal solution in the fractional case. But this strategy does not work for the discrete version of the knapsack problem. So instead, we will design together a dynamic programming solution. So before going into the details of a solution, let's consider an example. So consider a bag of the total capacity 10, and assume that we have 4 items with weights 6, 3, 4, and 2, and with values 30, 14, 16, and 9 respectively. Then for the discrete version of the knapsack problem, where repetitions are not allowed, the optimal value is equal to 46. So to achieve this optimal value, it is enough to take the first item and the third item. Okay? On the other hand, if we do not allow repetitions, if we do allow repetitions, then the optimal value increases to 48. So in this case, to achieve this value, we can take, for example, the first item and 2 copies of the last item. Finally, if we are allowed to take fractions of items, then the optimal value increases again, and in this case it is equal to 48.5. And to achieve this value, we can take the first item, the second item, and 1/2 of the last item. We will now design a dynamic programming solution for the variant of the knapsack problem with repetitions. Recall that in this case, we are allowed to take any number of items, any number of the available items. Okay? So to formally state this problem, so denote the total capacity of our bag by capital W, the weights of the n items by W0 and so on, Wn minus 1, and their values by V0 and so on, Vn minus 1. So our goal is, again, to select some subset of these items, probably multiple copies of some items, so that their total weight does not exceed capital W, while their total value is as large as possible. As you remember, the most important step in designing a dynamic programming solution is coming up with the right notion of a subproblem. And one way of finding this right notion of a subproblem is to consider the structure of an optimal solution. So consider some optimal solution for our bag and assume that we have some item Wi in it. So a simple but crucial observation is the following. If we take this item out of our solution, then what we get is a solution for a knapsack of total capacity W minus Wi, and it must also be optimal solution for this particular capacity. Why is that? Well, for a simple reason. If this were not optimal solution for a bag of capacity W minus Wi, then the initial capacity would also not be optimal, right? So this allows us to define the following subproblem. For a parameter u, let's define value of u to be equal to the optimal weight, to the optimal value, of the bag of total capacity u, using the same items, of course. This allows us to write down the following recurrence relation. Value of u is equal to the maximum over all items I, such that wi is not greater than u of the following quantity. Value of u minus wi plus vi. So this recurrence relation just reflects the fact that in order to get an optimal solution for the back of capacity W, we can actually take some optimal solution for a smaller capacity, namely u minus wi, and add the ith item to this solution. This will give us a solution for a capacity u, and this will add vi to the total value of this smaller solution. Right? So when there are no such items, in this case the maximum is taken over an empty set, we assume that it is equal to 0. So another base case is also corresponds to the case when u is equal to 0, and in this case value of 0 is equal to 0 also, of course, right? Because we have no items to put in our back of capacity 0. So when we have this recurrence relation, as usual, it is just a technicality to transform it into a recursive algorithm. And this is what we're going to do now, and this is what you see now at the slide. So what we see here on the slide is a recursive algorithm that we get out of the recurrence relations that we've just discovered. As usual, we use a table T to memorize all the intermediate results, namely all the solutions for sub-problems for the back of capacity U, where U ranges from 0 to capital W. Okay, so the knapsack function takes 3 parameters, W, V, and U, where W and V are just lists of all weights and values of our items, and U is the current capacity of the knapsack. We only start computing value of u if it is not stored in the table. If it is not, then we do the following. We first initialize it with 0. Then we go through all n items, and for any item I whose weight does not exceed u, we try to improve our current T of u using item I. Namely, we consider a solution for the problem u minus wi, and we try to add the ith item to this solution. If this gives value which is higher than T of u, then we improve T of u. Okay? As you remember, it is usually possible to transform a recursive algorithm into an iterative one. In this case, it is particularly easy, since what we need to do is to solve all sub-problems for u ranging from 0 to capital W. We can do this just in a straightforward fashion by gradually increasing u. And we will use just an array for storing all the value of u. So what you see here is the corresponding iterative implementation of the same algorithm. Here, instead of using dictionary, we use just an array T of size capital W plus 1. Then for u ranging from 1 to capital W, we compute the value T of u using exactly the same recurrence relation. Okay? So the next before proceeding, let's consider an example, and let's review the examples that we've seen previously, and assume that we've already computed all the values in our table except for the last one. Namely, so what we're computing right now is what is the optimal solution for the knapsack of total capacity 10. So what we see here is that there are actually 4 possibilities. Either we add the first item to the solution of capacity 4, or we add the second item to the solution of capacity 7, or we add the third item to the solution of total capacity 6, or finally we add the last item to the solution of total capacity 8. For all these capacities, we already know the optimal solutions. So we just compute the maximum of 4 values, and it turns out that in this case the maximum value is equal to 48. which convinces actually that this is indeed an optimal value for this case. Okay, now let's conclude the lesson, the video, by revisiting the sub-problems. So as you remember, another way of defining the right sub-problems is to design a brute force solution and then to somehow optimize it. So when the brute force solution in this case is not so difficult to implement. Namely, since we need to find some optimal collection of items, let's just populate the current set of items one by one. And what you see here is actually an implementation of this approach. So this recursive procedure uses the parameter items, which actually exactly stores the items that we're going to put in our knapsack. So we start with an empty sequence of items, and then we recursively add the current item to the list items and make a recursive call, right? And we only add the item if the current, if adding it does not exceed the total weight. Okay, so this gives us just a brute force solution. We essentially go through all possible subset of items. So then finally, to get a dynamic programming solution out of this brute force solution, it remains actually to note that in this case we are not interested in the whole subset of items. What we're interested in is just in their total weight. So just by replacing the collection of items by their total weight, we actually get back our previous dynamic programming solution. In this video, we turn to the version of the knapsack problem where repetitions are not allowed, namely for the knapsack without repetitions problem. Recall that in this problem, once again, each item, there is just a single copy of each item, so we are not allowed to take more than one copy of any item. Before designing an algorithm, let's just try to understand whether we can use the sub-problems used in the previous version. So assume that we consider some optimal solution for a knapsack of capacity W, and assume that there is that we somehow know that it uses the last item of weight Wn minus one, and we try to extract this item out of this solution and to solve the remaining problem of capacity W minus Wn minus 1. So in this case, it is not excluded that the optimal solution for the resulting sub-problem of capacity W minus Wn minus 1 actually contains the last item. And since it contains it, we cannot add this item to this solution to get the solution for our original sub-problem, because it will create two copies of the last item, right? However, we considered the last, namely n minus 1 item here on purpose, because this will eventually lead us to defining the right notion of a sub-problem. Namely, assume that the n minus first item is used in an optimal solution. Then if we take this out from the back of capacity capital W, then what we get must be an optimal solution for the back of total capacity W minus Wn minus 1 that uses only items from 0 to n minus 2, right? Because we are not allowed to use the last item anymore. On the other hand, if the last item is not used in the optimal solution for the back of capacity W, then what we know is that it must use only the items with indices from 0 to n minus 2. This actually means that in both these cases we either reduce the total capacity or we reduce the set of available items, right? And finally, this leads us to the following sub-problem. So for two parameters u and I, where u ranges from 0 to capital W and I ranges from 0 to n, let's define value of ui to be the optimal value of the back of capacity u that uses only the first I items. Okay, so this allows us to write the following recurrence relation. So we actually start with the base case. When I is equal to 0, this actually means that we do not have any items. So value of u 0 is equal to 0 for any u. And also when u is equal to 0, this actually means that we have a back of total capacity 0. So value of 0i is equal to 0 for any I. And the recurrence relation that we get here is actually even simpler than in the previous case. So we either use the i's item in our, I minus 1 in our solution or not. So what we need to compute in order to find the value of value ui is actually the maximum of the following two values. The value of u minus wi minus 1, I minus 1 plus vi minus 1, or just value of u and I minus 1. So in the first case, we are going to use the I minus first item in our solution, and in the second case, we are not going to use this item. And also, among these two terms, the first one is used only in case the weight of the I minus first item does not exceed u. Okay, so this recurrence relation, as usual, can be easily transformed into a recursive algorithm that you see now on the slide. As usual, we use a table T, which is in this case just a dictionary, and we only start computing the value of ui if it is not yet in the table, and we do this just following our recurrence relation. So, namely, in the eighth line, we actually compute the second term in our recurrence relation. So we initialize T of ui to be equal to just actually the value of ui minus 1. And then in the case when the value of the I minus 1 item does not exceed u, we check whether the current value can be improved by actually taking an optimal solution for u minus wi minus 1 and adding this I minus first item to this solution. Okay, so this gives us a recursive algorithm. And as usual, it can be transformed into an iterative algorithm. In this case, instead of using dictionary for storing all the intermediate solutions, we actually use a two-dimensional table. So we use a two-dimensional table because our subproblem is actually specified by two parameters, by u and I. So for this reason, we need a table which is indexed, so rows are indexed by u, for example, and columns are indexed by y. Okay? Then we just fill in this table by gradually increasing the parameters u and I. This gives us an algorithm whose running time is equal to big O of n times capital W. The reason is simple. So in this case, we just have two nested loops, four nested loops. Or put it otherwise, we have n times capital W subproblems, and for each subproblem, it takes us a constant amount of work to compute its value. The space requirement is the same. It is big O of n times capital W, just in particular because we need to store a table of that size, right? At the same time, it is not so difficult to improve an upper bound to improve actually the space used by this algorithm by noting that we do not need to store the whole table all the time. Namely, when computing the values in the current column, it is enough to know all the values from the previous column. So instead of storing the whole table, we can actually keep storing the current row and the previous row. Okay? Then let's also discuss how to reconstruct a solution. Namely, what we've already computed is the optimal value. Now what we're going to do is to explain how to find the optimal subset of items, right? As usually this can be done just by reconstructing the solution somehow from right to left, or just to unwind the solution from right to left. So we start just from the last cell of our table, from the cell capital where U is equal to capital W and I is equal to N. And then we follow the following simple rule. So each time if value of ui is equal to value of ui minus 1, then this basically means that our optimal solution does not use the item I minus 1. So in this case, we just update I to I minus 1 and proceed. In the opposite case, when value of ui is equal to value of u minus wi minus 1 and I minus 1 plus vi, we actually know that the i's item is used. Okay, so we store this information somehow and we update u to u minus wi minus 1 and I to I minus 1. Okay, so this eventually leads us from the bottom right corner of our table to the top left column in our table. Okay, now as a final remark, let me also explain how it is possible to arrive to this dynamic programming solution by optimizing a corresponding brute force solution. So what is a brute force solution in this case? Since we have only a single copy of each item, we can do the following. We process items one by one, starting from item number 0 and ending with item number n minus 1. And for each item, we decide whether we take it in our solution or not. So what you see here is a recursive implementation of this idea. As you see, we have two parameters here, items and last. So items, just as in our previous brute force solution, denotes the set of currently used items. And the last is actually the index of the last item which we consider it. Okay? So in the seventh line in this code, we actually just decide not to use the item with index last. So actually we just increase last by 1 and make a recursive call. Okay, in the 8th line, if the item with index last plus 1 actually can be added to our current solution, namely if adding this item does not exceed the weight capital W, then we try to add it to our current set of items, we increase last by 1, we make a recursive call, and if it gives a better solution, then we actually store this result. So then by running this solution, you will find, by running this algorithm, you will find a solution for small data sets, but for large data sets, it will not work, of course, because it is too slow. It actually goes through all possible subsets of size 2 to the n. However, it can be optimized as usual. So it can be optimized just by noticing that the only thing we need to know about the current subset of items is actually the index of the last item that we made some solution about, and also the total weight of the current set of items. So just by replacing the collection of items just by their total weight, we actually get back our previous solution based on the dynamic programming technique. We conclude this lesson with a few final remarks. So first of all, let us discuss which approach is better, a recursive one or an iterative one. So in many cases, an iterative approach is slightly faster because it uses simpler data structures, well, for example, just an array instead of a dictionary, and also there is no recursion overhead. Right, so instead of making recursive call and putting some information on stack, for example, we just fill in a simple table, a simple array or two-dimensional array. At the same time, there are cases when this recursive approach pays off, and the knapsack problem is a nice illustration of such a situation. So imagine a case where the total capacity of a knapsack is divisible by 100, for example, and also all the weights of all the available items are also divisible by 100. This essentially means that we are only interested in sub-problems where the capacity of a bag is divisible by 100, because we are completely sure that all possible solutions that exist actually in our case, in all these solutions, the capacity is divisible by 100, right? So what will happen is that the recursive approach will only consider such solutions, right? Because it always makes recursive calls to smaller sub-problems, and in every such case, the current capacity of a bag will be divisible by 100. On the other hand, if we run an iterative approach, it will tediously go through all possible values starting from 0 and ending with capital W. So it will ignore, in a sense, the fact that it should only solve sub-problems where U is divisible by 100. So once again, this is a nice example where memoization pays off. And in this case, in the case of the knapsack problem, for some data sets, the recursive approach might be much faster than an iterative one. Okay, so the next remark is about the running time of the resulting algorithm. So as you remember, what we designed is an algorithm whose running time grows proportionally to n times capital W, which looks like a polynomial running time. So this is just a product of two parameters. At the same time, in fact, this is not considered to be a polynomial running time. And this is why. When we say polynomial, we mean a polynomial with respect to the input size. However, in our case, the input size is proportional to n, not plus w, but plus log of w. Namely, to write down the number w, you actually need roughly log w bits, or log w decimal digits. Right? This basically means that our input is proportional in size to n plus log w. And with respect to log w, the running time of our algorithm is expressed as n times 2 to the log w. Right? Just because w is equal to 2 to the power of log w. So put it otherwise, if you add just a single digit to W, if instead of considering a knapsack of total capacity, for example, 17, you consider a knapsack of total capacity 170, your algorithm becomes 10 times slower. This means that actually by adding just a single zero to the parameter W, you slow down your algorithm by a factor of 0. Or just as another illustration, if you consider W, if you consider some number W consisting of 20 decimal digits, this is just actually a short number, right? This is not gigabytes of data or something. This is just a number with 20 decimal digits. Then, if you run the corresponding algorithm on your laptop, it will require to perform roughly 10 to the 20 basic operations, which essentially means that it will never stop on your laptop, right? And finally, let me also mention that designing a truly polynomial algorithm for this problem is actually the essence of the famous P versus NP open problem. In a sense, this open problem asks whether we can solve whether the class of all problems whose solutions can be found efficiently, and by saying efficiently I mean in polynomial time, coincides with the class NP of all problems whose solutions can be verified in polynomial time. This is probably the most important problem in computer science, with a bounty of $1 million from Clay Mathematical Institute. The next problem that we're going to attack using the dynamic programming technique is the so-called chain matrix multiplication problem. The input in this problem consists of n matrices, which we denote here by A0, A1, and so on, an minus 1. And what we need to find is the minimum cost of multiplying these n matrices. We will now clarify what we mean by saying the cost. Okay, first of all, recall that in order to be able to multiply two matrices A and B, we need to ensure that the number of columns of the matrix A is equal to the number of rows of the matrix B. This basically means that the number of columns of the matrix AI should be the same as the number of rows of the matrix AI plus 1. Right? So this allows us to denote the sizes of our n matrices by m0 times m1, m1 times m2, and so on. So basically the size of the matrix AI is equal to mi times mi plus 1. Okay? Then recall that even for square matrices, matrix multiplication is not commutative. Namely, there are matrices A and B such that A times B is not equal to B times A. This means actually that even if our matrices were square, we would not be able to actually swap the order of matrices. The same holds for four matrices. So if we need to multiply A by B by C by D, then there are at least two possible orders. We may first want to multiply A by B, then C by D, then multiply two results, or we may first multiply B by C, then multiply A by the result, and finally multiply the result by D. Okay? So the cost of multiplying two matrices of dimensions P by Q and Q by R we define to be equal to PQR. This actually reflects the following fact. So the resultant matrix has dimensions P by R, right? So it has P by R cells. And to compute the content of each cell, we need to multiply a row of the first matrix of size Q by a column of the second matrix of size Q. So it definitely can be done in time big O of Q. So definitely we can compute the product in time big O of PQR. In fact, faster algorithms are known for computing the product of two matrices, but for the time being, let's just assume that the cost of multiplying two matrices P by Q and Q by R is just equal to PQR, even without any constants. And before designing an algorithm, let me illustrate you that even for small data sets, for example, for four matrices, the order of multiplication actually matters. So consider four matrices A, B, C, and D of the following dimensions. So 50 by 20, 20 by 1, 1 by 10, and 10 by 100. And in the first case, I assume that we are going to multiply their product as follows. So we first multiply B by C, then multiply it by D, and finally we multiply A by the result. So after the first multiplication, namely B by C, we get a matrix B by C of dimensions 2 by 10, and we pay for it 20 by 1 by 10. Right? Our next operation is multiplying this result by D. Then what we get is a matrix of dimensions 20 by 100, and we pay for it 20 by 10 by 100. Okay? Then finally we multiply A by the resulting matrix, and we pay for it 50 by 20 by 100. As a result, the total cost of this multiplication is roughly 100,000. Okay, now let me show you that in some other order of multiplication of the same two matrices, the cost is much lower. Okay, so I assume that we first multiply A by B and then multiply it with C by D. Okay, so for the first multiplication A by B, we pay actually 50 by 20 by 1, and you see that we have this very thin matrix. Then we multiply C by D, and we pay for this 1 times 10 times 100, and again we see that here we get a matrix whose height is very low. And finally we multiply these two resulting matrices, and we pay 50 times 1 times 100. So the resulting cost in this case is just 7,000, which is much lower than in the previous one, in the previous case, right? Now, an essential observation that will help us to design a sub-problem to define a sub-problem in this case and to finally design a dynamic programming solution is the following. Any order of multiplication of our matrices can be conveniently represented as a binary tree. Okay, where we have our matrices, our initial matrices at the leaves, and each internal node actually multiplies two matrices. So, for example, the first tree shown here on the slides corresponds to the order where we first multiply A by B, then multiply the result by C, and multiply the result by D. The second one corresponds to the fact corresponds to the order where we first multiply B by C, then multiply the result by D, and then finally we multiply A by the result, and so on. So in general, if we consider such a tree not for 4 matrices but for n matrices, and for example, let's consider its 4 subtrees. Okay, then what we see is that the left subtree here multiply matrices starting from 0 to, say, I minus 1. The next one will multiply matrices starting from AI minus 1 to AJ, from AI, to AJ minus 1. The next one will go from AJ to AK minus 1 for some K, and finally the last one, the rightmost one, will multiply matrices starting from K to N minus 1. Right? So the pattern that emerges here is that any subtree in such a binary tree multiplies matrices from I to J minus 1 for some parameters I and J. Okay? And this suggests that we define a subproblem as follows. So let M of Ij be the minimum cost of multiplying matrices from I to J minus 1. Okay? So we know that it can be represented as a tree, and in turn, if we consider this tree, then it has a root and 2 subtrees, right? And we know that in the subtrees, what is computed is the product from I to K minus 1 in the left subtree for some K, and in the right subtree from K to J minus 1. So what we basically need to do to compute the value of Mij is to go through all potential values of K. And this is what we do actually to define the recurrence relation. So finally, M of Ij is actually equal to the minimum overall K, which is greater than I and smaller than J of the following quantity. M of Ik plus this is the cost of multiplying matrices from I to K minus 1, plus M of Kj. This is the cost of multiplying matrices from K to J minus 1, and plus the cost of multiplying 2 results. And the results actually have dimensions Mi times Mk and Mk times Mj. So the cost of multiplying these 2 matrices is Mi times Mk times Mj. Okay? There is also a base case where J is equal to I plus 1. In this case, we have a single matrix, so there is nothing to multiply, so the cost in this case is equal to 0. Okay, so when we have a recurrence relation, as usual, it is just a technicality to convert it into a recursive algorithm, So when this, and you see this algorithm here on the slide, so again we have a table C, which is just a dictionary. Again, what we do is what we need to compute is M of Ij. We pass these 2 parameters to our procedure, and we only start computing it if it is not in our table yet. So if J is equal to I plus 1, then we are in the base case, then we say that then the result is equal to 0. Otherwise, we compute it using our recurrence relation by making recursive calls where K ranges from I plus 1 to J minus 1. So for each such recursive call, we check whether the resulting value improves our current solution. If it improves, we actually store it. Okay? So in order to convert this recursive algorithm into an iterative one, we need to actually make some little effort in this case, because in this case it is not immediately clear what is the right order of all subproblems. So, namely, what we need to do is to go from smaller size subproblems to larger size subproblems. Since in this case each subproblem is actually specified by two parameters I and j, it is natural to use a two-dimensional table to store all the results. At the same time, we cannot fill in this table, for example, row by row or column by column, because it will not give us a possibility to go from smaller size subproblems to larger size subproblems. And at this point, it is important to define what is the size of a subproblem. It is natural to say that the size of a subproblem is the number of matrices that needs to be multiplied, right? So the size of a subproblem is just j minus 1, which basically means that we need to start with the size equal to 1, then proceed to size equal to 2, then proceed to size equal to 3, and so on. So we fill in our matrix diagonal by diagonal, like this, right? And this gives us the following code. So in this case, we use a parameter s, which actually denotes the size. So s, when s is equal to 0, this is or equal to 1. This is just our base case. So we initialize all such cells with 0. Then we gradually increase s, starting from 2 to n. And for each such s, we consider all the subproblems whose size is s. And we do this just by iterating over all I, and j is computed as I plus s in this case. And then we compute the value using our previous recurrence relation. So this gives us an algorithm whose running time is cubic. It is n cubed. So this is basically just because we have 4 nested loops. Or put it otherwise, we have n squared subproblems, and for each subproblem we need a linear amount of work to compute the result. So finally, to unwind a solution, we basically need to go from the final cell, which is a cell with indices 0 and minus 1, and we need to go back to the initial diagonal. So we start with the cell 0n, and for each such cell, we need to find a choice leading to this cell. Namely, we need to find a k between 0 and n, which led to the result of this particular cell. So by unwinding a solution in this manner, we will actually construct this tree, right, which represents the optimal order of multiplying our matrices. Finally, to arrive to the right notion of a subproblem from a different side, namely by optimizing a brute force solution, one can implement the brute force solution as follows. So the brute force in this case is to enumerate all possible binary trees, and actually to go over all possible binary trees and to find the best one. And actually to optimize it, one just notice that when we find a subproblem, when we compute the value of a subproblem, we do not need to know the shape of this tree. We only need to know what are the matrices that are multiplied in this particular tree. Now, when we've seen several examples, let's summarize. So as we've discussed already several times, the most important and probably the most creative step in designing a dynamic programming solution is defining a subproblem and writing down a recurrence relation, allowing us to express a solution for a subproblem through solutions to smaller subproblems. There are two common ways of doing this. The first way is by analyzing the structure of an optimal solution, And the second way is by first implementing a brute force solution and then optimizing it. Okay, let me also remind you how sub-problems look like for all the problems that we considered in these two modules. So the first one is the longest increasing subsequence. In this case, we defined the sub-problem specified by a parameter I to be the length of an optimal increasing subsequence, the longest increasing subsequence ending at the ith element. Okay? In the edit distance problem, where we need to find the edit distance between two given strings, the sub-problem was essentially the same problem, computing the edit distance between two prefixes of the given two strings. Okay? For the knapsack problem, where our goal was to fill in the back of capacity capital W with items optimally, we were solving sub-problems for bags of smaller capacities. Okay? Finally, for the chain matrix multiplication, where we are given n matrices and we need to multiply them optimally, I mean in an optimal cost, what we were solving, our sub-problems were multiplying some contiguous subsequences of our n matrices. Okay, so in general, when you have a problem specifying a sequence or two sequences or three or something, in many cases the sub-problem is defined by considering subsequences or prefixes or subtrees of the initial sequence. Okay, still it requires creativity, of course, and practice to define the right notion of a sub-problem. So when the recurrence relation on sub-problems is written down, it is a technicality to convert it into a recursive algorithm. So for this, you store the results of all sub-problems in some table, and before computing the result for a particular sub-problem, you first check whether it is already stored in the table or not. If it is stored, you return it immediately. So you start computing it only if you haven't computed it so far. Okay? The next natural step is to convert a recursive algorithm into an iterative one. This usually requires just initializing the table and then filling in, going from smaller sub-problems to larger sub-problems. In particular, this usually requires one to specify an order on all sub-problems. Right? The next step is proving an upper bound on the running time of the resulting algorithm. In many cases, a reasonable estimate is just to compute the number of sub-problems and to multiply it by the time taken to compute the value, the solution for each sub-problem. Okay? The next step is to also implement unwinding a solution. So in many cases, your first dynamic programming solution only computes the cost of an optimal solution. And to find an optimal solution itself, you actually you usually use a table to unwind an optimal solution. You use a table of solutions of all sub-problems. Okay? The next step is actually exploiting the structure of the table of your iterative solution in order to check whether you can save space. For example, as you remember, in case of the knapsack problem or in case of the edit distance problem, instead of storing the whole table, one can store just the current row and the previous row, or the current column and the previous column. This reduces the space requirement from quadratic to linear. Okay? Finally, let's discuss advantages of recursive and iterative approach. So the first advantage of an iterative approach is that there is no recursion overhead in this case. So instead of making recursive calls, we just fill in gradually the table. And we're also using simpler data structure, just arrays instead of dictionaries, for example. Another advantage is that just by looking at the table and the way it is filled in, you can actually save space. Again, the example is the edit distance problem and the knapsack problem, for example, where instead of storing the whole table, it is enough to store the current row and the previous row, for example. At the same time, the advantages of the recursive approach are the following. It is still, a recursive approach can still be faster, and it happens in cases where not all the subproblems need to be solved. A good illustration of such a situation is the knapsack problem, as we've discussed already. In the case when all the weights are divisible by some common factor, for example 100, we are only interested in subproblems where the capacity of a bag is divisible by 100. And the recursive approach will only solve such subproblems, while the iterative approach in this case will solve just all possible subproblems, not only those where the capacity are divisible by 100. So in this case, a recursive approach might be faster. So this depends on the data set, but still. Another advantage is that sometimes it is easier to implement a recursive approach just because in this case you do not need to specify the order of subproblems explicitly. So the recursion will find its way to the answer itself.